Check, check.
Morning, everyone. Wait just a sec as people come in and get some seats. Great, so welcome everyone to the 29th annual CSM workshop. 29, a lot of years. Has anybody been here to all 29? I think there's a chance that Peter Gent maybe, who's I think out in the hall, he might miss his opportunity to claim all 29 if he doesn't get in here soon. So we're going to start off with Everett Joseph, the director of NCAR, is going to give some welcoming remarks. And so Everett, are you ready?
I am.
Great. Yeah, we can hear you. Go ahead, please.
Just
Thank you, Everett. Really appreciate those inspiring remarks, and sorry you can't be here, and I hope you have a productive Board of Trustees meeting and that you advocate for CSM, which I'm sure you will. So I'm going to then start here with the traditional state of the CSM or system model project talk. This is basically an impossible presentation to give. The scope of activities that CSM is engaged in makes it it's impossible to hit on everything that we're doing, but I'm going to do my best to cover as many topics as possible and be informative, hopefully. And there'll be lots of opportunities for the rest of the week to learn much more. So first, welcome to everybody who's here in person or participating online. It's really fun to see it. This is our second year post-COVID, actually in person, to see even more people here this year than there were last year. So that's really fun. And rewarding. I mean, the project is without the community that we're sort of serving and enabling and working with. This would be a much less interesting activity. Just a few reminders as you participate in the meeting. We have a code of conduct. Be respectful, be collaborative, consider differing opinions, communicate openly, and be mindful of others. And if you have any issues, you can talk to Elizabeth, myself, or reach out to the Office of Diversity, Equity, and Inclusion. Additionally, we have a nursing room if anyone needs that, and all gender restrooms are available throughout the building. A few workshop logistics before we get started. In addition to all the great oral science sessions, I just want to highlight a couple things. One is that there's going to be a group photo Monday afternoon break in the lobby, so please kind of be prompt as you finish that session, or not finish the session, take the break in the afternoon. We're going to take a photo out there in the lobby. There's a post reception this evening. We have a lot of great posters, and so please join us for that. And then tomorrow evening, we are going to Sanitas Brewery. It's about a 15-minute walk just south down the Foothills Parkway. And it's drinks and tacos will be there, but it's a self-pay, so it's just bring your own cash. And then finally, at the end of the workshop, we're going to have a summary session, which I traditionally have, and it's always been a little bit hard to know what to do with this. And so this year we're introducing something slightly new, which is we're going to ask for questions that you have that you're forming throughout the week. As you see something that you'd like to know more about, you can click on this QR code, go to a Slido page, and enter your questions. So you don't have to track it all the way. And then on Wednesday afternoon, we will go through, me and other CSM leadership. We'll try to do our best to answer the questions. If we can't get to all the questions, we will address them written after the meeting. We have quiet spaces, more than 200 people here. Some of us are not used to having so many people in the same space at the same time, so we have places where you can go if you need to take a meeting, outdoor seating, and there's a walking path. So please take advantage of being in beautiful Boulder. And Everett expressed thanks already, but I also want to express thanks. I've been working closely with Elizabeth Faircloth, especially, who's at the back there, to put this meeting together. It is a huge amount of effort. It's quite complex and diverse. So I'd like to give a round of applause to Elizabeth Faircloth. She basically anticipates every need before I even ask for it, which is amazing. The CGD administrative team, everyone really in CGD and admin team is involved in helping get this going. And then of course the UCAR multimedia event services who bring us the audio visual and all the food are amazing. They're getting quite good at this. I think they said they hosted 150 events here in this building last year or something like that. So it's all going to go really smoothly, I'm confident. I've already mentioned this, but we'd like to thank NSF and also the Friends of the National Center for their support. That allows us to bring or help support 25 early career scientists to come to this meeting. It's a really important venue for early career scientists as they're trying to build out their career, meeting scientists here at NCAR and from around the community and building out their relationships. And then, of course, thanks to all of you for coming and participating and engaging with us and helping us make decisions and build a better model and do better science for the benefit of society. And then final thanks here is to Gokhan, who just reminded me that he has organized 6 of these workshops, and after having gone through this process this year, I feel his pain. It's actually really fun, but it is a ton of work, and he went through 3 of them during COVID times, so even more, had to deal with the technical challenges. So this is our little tradition that as you transfer over the chief scientist position, we're passing around this little hamster wheel. So I am now on that hamster wheel with all of you, to be fair. It's not just me, obviously. We're all on this hamster wheel. And I will be here for the next several years until the next person gets to take over this hamster wheel. Hopefully I'm not doing 6 CSM workshops, but the world is a strange place. Okay, so now I get into the presentation. I think we're at a pretty interesting time in terms of Earth system modeling. I'm sure everyone is sort of sensing that there's a lot of pretty significant forces that are driving the future, I think, of Earth system modeling. And I want to just make it clear, these are not just my ideas here. This is sort of something that's coming out in the literature. I'm not going to cite everything. Talking with a lot of people, just my sense over the last several years about what's changing and how it's probably going to change how we're going to operate going forward. Everett really mentioned this and highlighted it really well. We've established that climate change is happening. We know a lot about why it's happening. We understand quite a few of the feedbacks. There's lots of room for improvement and more knowledge there, but we're not in that situation anymore where we're trying to convince the world that climate change is happening. But now the world wants information, right? And they need it urgently, they need it accurately, they need it at local scales about climate risks, and also asking questions about, what can we do to stop climate change if we can't mitigate, or if we do mitigate, how is that mitigation actually going to affect the local or regional or global climate? There's increased emphasis on, and I'm putting here and sort of highlighting Earth system prediction across time scales. Everett highlighted this. It's an NCAR priority. I think it's a global research priority. S2S, S2D, 30-year projections, all the way out to centennial scale projections, and ideally in a seamless framework. And here I think the role we can really play, especially with CSM, is really focus on the Earth system aspect. We obviously care about weather out at these timescales, temperature and precipitation and extreme events, but it's really the whole Earth system. What is the carbon cycle going to do? What's going to happen when the volcanoes go off? What happens as the ozone hole recovers? All these kind of questions that we are well placed to address with a fully functioning and complex Earth system model. There's an increasing demand and need for high resolution and ultra high resolution kilometer scale configurations, to build out our modeling hierarchy to help us understand climate change and climate variability through scales. There's the growth and potential of machine learning, hybrid modeling, and emulators that are definitely going to transform our models going forward and the way we're operating, I think. There's changing competing architectures. It's always going, but it feels like it's happening even faster. Probably we're going to need to do things like code modernization to be able to keep up with this. And then Everett also highlighted this, there's calls for really improved accessibility of the ESMs and ESM output, more equitable access from places like the Global South, and marginalized communities being more involved in the science and being able to use the models and the model output. And I think that's an important driver for us as well going forward. So I think CSM is well placed to sort of hit and move on all of these. They're all going to pose challenges. They're all going to pose really interesting opportunities. So I think that's what I want to talk about for the next few minutes before I get into some of the more prosaic, like where are we now. So what is the future, I think, that as far as I'm sort of seeing in terms of CSM. So in some sense, the future is now. We've produced this quite amazing data set now with the CSM1 high resolution version. So it's the quarter degree atmosphere, 10th degree ocean model configuration that many of you here have worked on to build. And it's actually quite impressive and I think unprecedented set of simulations that we've produced to help us understand climate change, climate variability at this sort of high resolution configuration. And in particular, I'd like to highlight the 10-member ensemble we have now, which I think really is unprecedented, from 1850 to 2100 for several RCPs, to really understand not just what's happening at high resolution, but also starting to get a sense of what happens across ensembles. And I think that's a really important feature. And that's the one result I'd like to highlight as the one that's kind of struck me that I saw recently this year. And so this is showing the linear trend in SSTs over the past 45 years or so. And across most of the world, it's warming, but there's a few places around the world where we're seeing some cooling over that time period. So that the tropical Eastern Pacific and the Southern Oceans are showing cooling. So this is a bit of a puzzle, maybe not fully what we would anticipate, and certainly not something that we're seeing in our low resolution model. So this is the average ensemble from the CSM1 large ensemble that shows that basically warming everywhere around the world. And basically, as far as I know, no CMIP6 model is showing a trend that looks similar to that one that we're actually observing. And then the bottom right here is what we see in the high resolution ensemble. So we have a 10-member ensemble now, and you see just a hint that maybe there's an evidence of cooling in some of those regions where we're seeing that in the observations, but it's not nearly as strong as what the observations are showing. But then here's what happens if you look at the whole ensemble. So the linear trends for each one of those ensemble members is shown here. On the bottom right is the observations again. What you see is, quite interestingly, is that there's at least one ensemble member on the bottom right there, CSM version ensemble member number 10. Luckily, the last ensemble member we ran in this ensemble happens to show, it's lucky we went to 10 and not 9. I said 9 would be plenty. We went to 10, and we being other people, not me of course, went to 10, and we see a signature that looks quite like the observation. So this is a really interesting thing to pursue and try to understand scientifically. And so, yeah, I'm not going to talk about this too much today, but I definitely think it's an imperative for us to develop a version of a high resolution configuration at this 10th degree ocean and quarter degree atmosphere for CSM3. We skipped it for CSM2 because we ran out of time. We're also moving towards ultra high resolution capabilities, kilometer scale capabilities, and the goal here, largely initially spurred by the Earthworks project, a collaboration with CSU and NCAR, but now there's many more players involved. The goal is to develop this global 3.75 kilometer resolution model. CSM is not really at the leading edge here in terms of building this. There's other modeling centers who have this capability already, but I still think that we are going to be able to. We're a pretty thoughtful bunch, and I think as we move into this, maybe slightly more slowly, we're going to find a lot of potential to really contribute to the discussion and the science at ultra high resolution. So the idea is just to enable research at the weather climate interface, understand and resolve deficiencies at lower scale, at lower resolutions, potentially and probably create data sets for machine learning, training data sets, investigate scale interactions, develop scale-aware parameterizations, ideally, which all groups are struggling with trying to do that work well at both 3.75 and 120 kilometer grids. And so now we're going to hear more about this and the high resolution efforts at a cross-working group session tomorrow, but there's a collaboration now that's building between the Earthworks project, a new project we're calling Storm Speed, which is bringing the non-hydrostatic spectral element dynamical core into CSM with University of Michigan and Texas A&M. There's the SEMA activity here at NCAR, and of course CSM scientists all involved in building out this capability. And we are excited to have this. And basically it's been a process of overcoming many technical barriers. CSM was not developed initially to work at this scale, and so there's a lot of things we had to overcome. But we do have a lot of stuff working now. We have MPass dynamical core running in CAM, and applications running from a regionally refined grid, 63 kilometers, that's working. We're testing and debugging a global 3.75 kilometer version, and Brian Dobbins has been instrumental in this, and he told me this morning he solved another problem over the weekend, and we are weeks away from being able to do this on Derecho. And the goal then is to run a diamond simulation as a first step in this process, and hopefully very soon, within weeks to months, we will be getting that run. And the figure there just shows that it's interesting that the physics didn't work straight out of the box, but with some relatively small changes to the CAM physics, we can actually reproduce, in this case, a squall line, which is an important high-resolution feature, and I'm not going to go into the details. And then, of course, we have a longstanding capability of variable resolution, regionally refined configurations, and we're building out, and I think Go kind of showed this in previous years, a family of grids that are now available for people to use, and we have the capability to produce new grids, and I'll show at least one result later where we've a new grid, even more crazy looking grids than these. Okay, and nothing is building towards a drawing on machine learning, and we have a nice plenary talk coming up after the break to talk about this more, but moving towards a hybrid version of CSM, I think I'm calling CSM 3 MLE for machine learning enhanced, and we're really drawing on the expertise and the progress that is coming out of the M² Lines project, which is a Schmidt Foundation supported project, and the LEAP NSF Science and Technology Center. Both of these are quite substantial financial commitments and allowing us to really think about how we can bring machine learning parameterizations in. And so the idea here is fairly straightforward, but still very difficult, which is to combine new machine learning algorithms with high fidelity model simulation output, training on high fidelity simulation output, or high resolution observations, or even low resolution observations to build new machine learning based parameterizations, fold those into CSM, and so hopefully resolve some of the most difficult or poorly performing parameterizations we have in the model. And the idea is that if we do that, we will hopefully have a more accurate projection. So this is really a hypothesis at this point to see whether we can get there. I was at the M² Lines meeting last week to see how progress is going and to sort of give them a little bit of a push to really focus on trying to bring these things into CSM. And here's a list of candidate parameterizations that they're working on. I'm not going to go through them all. That are there's some evidence that they might be able to be potentially brought into CSM sometime over the next several years. And then LEAP also has a set of parameterizations they're working on. I'm not listing them here. But LEAP, in addition to the parameterization development, is focusing on developing methodology to do systematic machine learning-based calibration for our system model parameters. And we have some evidence, and I'll show a few examples here, that this has some potential to work. And we've been running large ensembles, which we're finding for both CAM and CLM really useful to help us just understand our models. It's been really, even without the calibration, really rich data sets. In terms of our system predictability, it's a NSF NCAR priority, and we've been doing things like convening the community. There was the big workshop that Everett mentioned a couple months ago, where we're trying to define some near-term and long-term priorities, where CSM, from our community perspective, CSM can contribute to this conversation. And again, I want to stress that I think we have a lot of ability here to help drive the direction of this activity. And also, we have this unique capability to really look at the questions of predictability from a really full Earth system perspective. And I really want to push and focus on that to the extent possible. And it is really across time scale. So I think, century scale is included within this, but also pushing down to have a seamless model that can do S2S all the way out to century scale. And I think, in particular, we can ask questions around, what is the predictability in a changing climate, a non-stationary climate, and I think that's where our expertise can really come to the fore. And then in terms of actionable information, you're going to see, I think, a bunch of talks this week about actionable information. I'm just showing one example here. I'm not even going to go through the details, just to say that, there's a huge diversity of possible uses of CSM to provide actionable information. This is one where they're trying to use CSM large ensemble output to understand the vulnerability of coral in the Florida Keys National Marine Sanctuary. So a pretty cool project that's working with people who are specialists in conservation and conservation governance with the scientists here in the CSM community to help us understand the vulnerability of corals. But of course, that's hard to sustain or grow in a long-term way. We have only a limited number of scientists, even with 220 people or more here in the room. The number of people who need climate information is massive. And so we are trying to think about ways to kind of do something a bit broader than these individual one-off projects, which are really useful. And so the CSM Climate Justice Task Force, that's being led by Monica Morrison, is thinking about these questions around, how do we document and provide documentation and guidance on how to best use the models for these climate change actionable information purposes. How do we improve the accessibility of the model output, and how do we really bring the marginalized, underrepresented communities into the process of building these models and making decisions about how these models are built or the simulations that we run. And one slightly more concrete thing we're thinking we could do is to build out on the climate model, the climate data guide that Clara Desser and Dave Schneider and Adam Phillips and others here at NCAR have built, and it's one of our most useful I think tools we have, we support in CGD, where people can look and understand what is the utility of particular climate data sets, observational data sets. Can we build a model simulation and data guide? We think this would be one way we could have a bigger impact than just focusing in on individual projects. And here's just we've been talking with Monica about this and others about how we could possibly build this out. And so here's what an example guidance page might look like. This is just proof of concept. Say if you have a question, is the Lens 2 data applicable for atmospheric rivers? You could have experts come in and provide judgments about that. And here, in this case, if you look adequacy for purpose, the judgment would be not adequate. But then there's caveats that there's different ways you might be able to use this information and combined with other things. And so we're kind of looking towards building out a set of these, and at this point there's no funding to do this, but if we do find funding, I think we have some interesting ideas about how we could move this forward. Okay, so that's the future. Now I'm going to take a step backward to something more prosaic, but fundamentally what we do, and get back to the present, working towards CSM3. So this is traditional model. We're building a nominally 1 degree version of CSM to be used in CMIP, like we've done in the past. But the vision, I think, here is that CSM3 is really going to form the basis for all these other more advanced, more pressing needs that we have. And so we really need to build a good model as your foundation, the scaffolding for all that other work. Otherwise, that other work isn't going to have meaning. So where are we at? So we're working towards CSM3. Updates to all model components throughout the entire system. I'm sure you guys have all been sort of tracking this to some degree or another. I'm not going to go through all these things. There's a huge list of things that are coming into CSM3, like it's true with all model versions. A couple of big things, moving to the spectral element dynamical core, increased vertical resolution in the atmosphere, switching to the MOM6 ocean model, and a bunch of other features. I think I recently asked all the teams to put together a list of all the new features, and the list runs to 50 plus new features, and each one of those actually has sub-bullets in them. So there's a bunch of new things coming in with CSM3. So we're excited about that. And the CSM development team is hard at work. This is just a non-readable slide about what our weekly project meeting where we are tracking all the simulations that we do, and those of you who've been involved for a long time know that it's not easy to build a coupled model. And here we are, this is tracking the runs that we're running at this time. It was a couple months ago. We had 10 or so simulations that were running or recently finished. On the right is just showing the purpose. You can see there's all sorts of purposes, a lot of like coded things in here. There's the cold branch, there's the warm branch. What do those even mean? But this is the way that it works. And so we're really working very hard to, build the model, understand what we have here, bring in the last features, and get towards a really good and useful model going forward. So just going to show a few examples of some of the things that have come in, nothing like all the things, ones that were nice and kind of easy to explain. So and these are recent additions, the addition of convective gustiness parameterization that Meg Fowler has led in collaboration with Rich Neal. So basically taking into account that these convective storms are leading to sort of wind bursts near the surface, and showing some evidence that looks like it's improving El Nino statistics. So it's got a better phasing. The pattern correlation is looking a little bit better as well. So we don't really fully understand, I think, at this point, why these improvements are happening, but it does look like a interesting improvement. Another recent improvement in the last several months is working on the stratospheric jets, and Julio Bachmeister and others have been exploring a new source of gravity waves, which he's calling moving mountains, which is basically large-scale convective organization kicking off gravity waves and then affecting the stratosphere. Obviously outside of my area of expertise, so I'm going to try to not go into too much detail, but the idea here is that we were not getting, one of the problems we were seeing is that if you look at the tilt of the jet, in the stratosphere, it's tilted, and in CAM7 development version, it was not tilted. Adding these gravity waves is now producing a configuration that's agreeing with observations much better, this moving mountains parameterization. But the model is definitely not, probably it's fair to say it's not looking great. There's a lot of things we need to do to tune the model up, and here's one issue that's kind of particularly perplexing. It's the tropical precipitation. This is actually showing it in units of standard deviation, but what you see here is this weird, sorry, I'm going the wrong way. This weird dry patch that occurs here in the CSM3 development version in the tropical Eastern Pacific, and actually there's a weird kind of wet patch that occurs to the south of it. This does not show up in the atmosphere-only simulations. It ends up showing up a SST signature, and that SST signature does not show up in ocean-only configuration. So this is really something that arises in the coupled model. So we got a team of people now trying to understand and resolve this, but just one of these things that who knew this was going to happen, but it's there. I also want to spend just a little bit of time talking about the microphysics. Most of you are probably aware of the fact that CSM2 was one of the hot models, the Wolfpack models, with equilibrium commutativity greater than 5. CSM2 also scores at or near the best among the CMIP6 models for many metrics. It's a well-performing model across the CMIP archive. But then after we released the model, Zhang Zhu ran the LGM simulation and found out that CSM was far too cold. So ideally we would have run this before we released CSM2, but we didn't get around to it. Then we found this was true. So he made some preliminary corrections to what we're referring to as an inappropriate limiter on the cloud ice number. He found some time step dependence in the cloud microphysics, and produced basically a CSM2 paleo-calibrated version where the LEM cooling, if you look here on the, God, I hit the wrong button again. On the right here is now meeting the observed proxy estimates, and the ECS is reduced from 5.2 to 4K. So we've been trying to understand so we can sort of advise you all who are using the model, what the implication of this is for CSM2 use. And what we're seeing here is that after that fix, in terms of transient climate change response, basically it's exactly the same as a large ensemble. So it has not changed the global transient climate change response. And also in the 1% CO2 run, you can't see any divergence. You do see an impact at abrupt 4 times CO2. So really warm, really cold climates is where you start seeing a signature of this bug or these decisions that were made in CSM2 microphysics. So I think that's important to know. It's I think definitely usable for climate change science on the next century timescale without any problems. And we've also done some investigations to say, what happens in future minus present day climate. And this figure came out a little bit fuzzy, but what you're seeing is basically it's in general almost everywhere around the world it's well within the large ensemble, and virtually every point around the world it's the changes are well within the CMIP ensemble. So this is, I think you shouldn't be worried about using CSM2. And this is work that's been led by Margaret Duffy, pictured there, and Isla Simpson and others. And so we're working on a Perspectives manuscript to submit to probably James or the equivalent, where we will have this out in the literature so you can refer to it. And I'm not going to read through all the things that we're concluding there in the interest of time. We have now, we said, okay, we don't want to have this same mistake happen again, or a mistake, whatever it was. The way it worked out happened again, so we are now testing early and often the equilibrium climate sensitivity. And we found that in the CSM development version, it's looking like it's about 3.8. So, considerably smaller than it was for CSM2. And we've also done an initial test of the last question maximum. And that run had just started last week, but the initial results are implying that it's going to have a reasonable cooling. So that's good news, and we'll be tracking that as we go towards CSM3. In terms of a few other things, we're working on this parameter estimation methodology. generate a perturbed parameter ensemble, train a machine learning emulator, confront that emulator with observations, constrain the posterior parameter space, and then there's this thing called iterative refocusing. And so Lenny Hawkins, Daniel Kennedy, and Katie Dagan have been working on this project through LEAP, and we're focusing on the land model, or they're focusing on the land model. There's some particular challenges related to the land model. There's long simulations, they slowly vary in carbon cycle you have to deal with. It's a lot of parameters. Parameters have a plant species dimension. There's spatial explicit issues. And the good news is it looks like we're going to be able to reduce the bias. And in the testing out in CLM 5.1, we've reduced the mean absolute error from about 1.3, 1.4 down to about 0.6. And just so you get a context, the global mean is about 2. So it was a really big error in CSM2 and CLM5, and we have a potential to really reduce that. And so we're going to try to do that for CSM3. We're ramping up now as the model gets finalized to do a quick calibration. And then I want to say here that not all the features are going to that we're working on are going to go into CSM3, but here's one new exciting feature that will be a new functional capability, and that's simulating alpine glaciers with the community ice sheet model. And this is a cool result coming from Samar Manala, who is showing that if you look at trying to simulate the Bernese Alps glaciers, on the left there, that's what's happening in present day, and then on the right is what happens under committed climate change, so forcing the model for 200 years with today's climate. So this is what's happening even if there was no additional climate change. There's going to be significant glacier retreat. And this capability will be available in the next CESM release. So now we're in the process of assessing and tuning the model. We finalize the science configuration really soon. We'll be working to resolve issues like that weird dry patch and other things, tune the model, and run control simulations. But I feel like important to put a cautionary note here. CSM2 was and is a really pretty good model. It performed, this is the diagnostics package that John Facula developed, at or near the top of CMIP6 models. Good performance in a lot of things. I don't know whether we're going to be able to beat it or not. We've added a lot of things, so it remains to be seen. I think it's not necessarily going to be a lack of success if we can't beat it, but we will see, right? If you ask me, if we looked at our model today, it would not be this. I think that's fair to say. I'm looking at Rich, who's laughing. So I think that's a true statement. So we'll see where we go. Okay, so timelines and CMIP7 fast track. Here's the plan. So the CMIP7 deck and fast track are due by the end of 2026. So that seems like a long ways away. It's really not. We're aiming to start the CMIP7 deck and fast track runs in early 2025 when the forcings become available, which means CSM3 needs to be ready ideally by around late 2024. So we're aiming for our standard configuration to be the mid-top model with 93 layers out to 80 kilometers, fully resolving the stratosphere with a simplified chemistry for climate configuration, which was recently developed by the Atmosphere Chemistry Working Group. That's the one here on the right with a sort of, this pointer's not working, with a relatively simplified set of compounds that it's representing. So it looks like that configuration is going to be fast enough for us to be able to run more efficiently than we're able to last go around when we had to run a lot of things with the whole Wacom model and more complex chemistry. There's a bunch of open questions about what exactly the configuration is going to look like. The whole Earth system modeling community is trying to move towards emissions-driven configurations, and we will try to do that as well if the CO2 trajectory looks okay. There's a couple other new features that we could potentially include. That's interactive fire emissions. Peter Lawrence has developed a new initialization technique, which maybe makes this possible. And interactive ice sheets. We have the capability to run Greenland and Antarctica. It's only good to do that, though, if the surface mass balance is good enough to not have a really weird-looking present-day Greenland or Antarctica. So we are going to make decisions on those things as we get closer. So here's the timeline. Those who've been paying attention will know that the original timeline, that if you work backwards from when we need to have the simulations done, we need to have a configuration basically really soon. So around June 30 was the deadline that we were using for CSM 3 science developments, and then we'd have a period of tuning and final forcings. Now, I didn't want this to be a situation like this. Douglas Adams type of deadline. If you've seen this quote, she says, "I love deadlines. I like the whooshing sound they make as they fly by." So I didn't want that, and we were at high risk of that. So I did the logical thing and I moved the deadline. So we are now hopefully not going to go whooshing by that deadline, and we will hopefully not have to move that deadline again, but we shall see. So that's where we're going now, trying to finish our science improvements by the end of July. And then we'll have to do that process of tuning and coupling and then doing all the software engineering we need to do to release the model. So hopefully be able to release the model to the community sometime next year. Okay, so turning to a few recent CSM science highlights. This is a cool result looking at tropical cyclones using that CSM1 high resolution configuration, but looking at the paleoclimate. So, what do tropical cyclones look like in the Eocene, the Pliocene, the LGM, and really interesting features as you see that, tropical cyclones in high CO2 and low CO2, seeing really interesting signatures coming from that really cool data set. In terms of atmospheric chemistry, here's this example I was mentioning that I would show about this really unique new grid. So they've produced a new regionally evolved configuration to run with the Musica atmospheric chemistry, focusing on the regionally refined configurations, and they're basically trying to replicate the geostationary satellite constellation. So focusing on the regions where those satellites are monitoring and being able to simulate high resolution in those regions. And what they're finding is really interesting impacts on things like NO emissions and then obviously transport. And so can get those pollution plumes much more finely resolved in those regionally defined regions, and that leads to improved simulation of intercontinental transport. And I want to thank out there, they want to particularly highlight the role of Jim Edwards and Adam Harrington on this, really critical in getting these configurations working. We're working on constraining the parameter uncertainty on the land carbon cycle out of this CLM PPE project, and here's some simulation where we've run 32 parameters that control leaf area index and run a 500 member ensemble with a Latin hypercube sampling, and basically this is the accumulated carbon cycle, and you see by present day there's a pretty big range of about 150, 200 petagrams, but if you go out into the future that becomes quite intense, and it actually turns out to be more than 1,000 petagram range. It's as large as the uncertainty in the CMIP6 large ensemble. It's also equivalent to about 100 years of fossil fuel emissions. So this is, I would say clouds and the land carbon cycle are among the two biggest uncertainties in our climate change. And we have the capability now to run these ensembles, and then we're trying to look at whether we could potentially constrain that. And if we constrain on recent net biome productivity, which is not that well observed, but there's a few proxies for it, we can constrain a bit. If we constrain on leaf area, we get a little bit even further. So there looks like there's some potential to provide some constraints using this parameter estimation. And then the final science highlight I have is a result from LACM-X, showing simulations of, actually I just showed the future space climate. And so, they're really interested in what the temperature and densities are in the thermosphere, are really critical for understanding the space climate, including lifetime of orbital satellites and debris. And so this is an SSP 585 projection using LACM-X that shows a significant cooling of the thermosphere during the minimums. These are the solar cycle here, and the minimums is what you want to look at, and so you see a significant trend in the temperature of the thermosphere. Unique capability, I think, of the CSM infrastructure to really study these, basically all the way out to the thermosphere. Okay, and then I'm going to finish up for the last couple minutes on a few things we're doing to help with community engagement and user support. The first, I'm sure a bunch of you have seen this, maybe most of you, if not all of you, the CSM newsletter. It's a new thing we've done. GoCon, I think, initiated it, started coming out. We've had 3 of them now. It's an additional way for us to communicate with the CSM community, updates on events. And I think this is an important one for me. I was starting to realize that the capabilities that CSM has, it's actually quite hard to communicate to everybody what they are and how do you ever track them. So we're trying to roll out each time to say, oh, here's another thing you may not have known that CSM can do. And so it's a way to get a little bit of insight into things you can do, research highlights, and quick links to things like web pages and stuff like that. You can scan the QR code and please sign up for the newsletter. We'll be having about 3 of them per year, and give us any suggestions on how we can improve it. We just released a new climate variability and diagnostics package. This is work by Adam Phillips and Claire Desser. And this has a lot of new capabilities. The figure on the right here is a nice cherry-picked figure from Adam that shows CSM performing really well in the pattern correlation with observations. Presumably that was cherry-picked. There's other things we will not perform as well at, but might as well show something good. And this is the nice thing here is it combines the capabilities of the original climate variability diagnostics package and the package that we built for large ensembles. There's new detrending observations, and you can compare to observations or to other model simulations, and also you can deal with the CAM-SE and regrid natively. So it's a really powerful new tool that hopefully you all can use. In terms of tutorials and support, obviously We continue with running tutorials. There's the annual tutorial. Hopefully some of you are coming to join us for that. There's component tutorials, and now we have the ability, and we've been doing this for a few years now, to do fully cloud-based tutorials, all done through Jupyter notebooks. We do it at AGU and AMS, and then also we did one at the WCRP meeting in Kigali, and here's the tutorial on tour in Kigali, and I was even there in principle helping. Mostly not hurting, I guess, but and then a few of us went out there on a tour to see the gorillas, and this gorilla, I think, was confused about why do you have to run case setup before you run. We're also really trying to focus people on using Discuss CSM. So most of you are aware that this is our bulletin board where we try to help users with problems with the model, and we are really trying to push towards getting all of us, even our best collaborators, your friend and colleague, and you say, I'm just going to email whoever it is and get a quick answer to this. We're going to try to get away from that and try to push as much as possible to the Discuss CSM. So really, if we answer a question about something, it'll be to the benefit of everybody, right? So we're finding the support needs are growing. This is an increasing trend in the number of posts to Discuss forum. And we're getting 10,000 or something messages a year on the Discuss CSM forum. It's really, it's exciting. It's also a burden, but that doesn't even include all the individual emails. So we really want to push everybody towards this. We're hoping to implement this thing called the best answer flag. Another new activity is it's called Cupid, the CSM Unified Post-Processing and Diagnostics Package. Basically, all of our diagnostics packages were built on NCL. NCL is dying or dead, and Python has, for a long time now, been the thing. And so we are taking the opportunity to rethink about how we want to do post-processing. So it's a really nice kind of from the grassroots effort, from the ground up, building a really, hopefully sustainable, extensible package that allows us to do all the things we need to do from model assessment to post-processing, time series generation, summarization, et cetera. This is an activity led by Tegan King and Mike Levy. Almost on a volunteer basis, are getting a small amount of funding for this. So really thank them for doing this. I'm really excited about it. And we're looking for contributors. We actually already had a contributor from outside of the core group who made a nice addition. And then lastly, there's a new tool coming down the pipe for ease of use. It's called Visual Case Gen. It's worked by Alper Altuntis on a NSF CSSI proposal. Basically producing for the first time a user-friendly graphical interface to assist users in creating CSM experiments. And one of the really nice things about this is it actually allows you to sort of graphically and visually explore what the possibilities are. And you can kind of click through this and it'll tell you, if I click this and then I click this other thing, it means you can't do these other things. That wasn't a great way of saying that, but you kind of get the sense. I think it's going to be really a nice tool, especially for teaching. And here's just a few things you can do. You can choose comp sets and settings, and you can choose and create model grids. You can modify grids, which is cool, even individually. Create a new ocean point if you want to, or remove add a land point, or make a mountain higher, things like that. And then you can also, create the case and run the model. So this is going to be really cool coming down the pipe soon. That's it. I'm just going to show this final slide reminder with the sort of the exciting opportunities we have over the next several years, I think, for Earth system modeling. And I'll stop there. And I've gone exactly time, so I could take a question, but historically this has been too overwhelming for people to come up with questions. is my experience. But if anyone has something that really a point they'd like to make, otherwise please submit questions to the Slido for the end of the week. Yes, thanks. Cool, so I'm going to assume that there's not questions, because who could ask a question about the entire CSM activity and decide which is the one you want to know the answer to. But I'm happy to talk to people during the week, and at the end of the week we'll have the opportunity, and there's going to be so many opportunities to talk to people who are actually doing the work during this week. So now is a fun part of the meeting. We get to announce our award winners. And so we have the CSM Distinguished Achievement Award and the CSM Graduate Student Award. So we're going to start with the CSM Distinguished Achievement Award. It is my distinct pleasure to announce the award is going to Jim Edwards for his contributions to the software engineering. And so Jim, where is Jim? So, this is technically a secret, so this is the first time anybody knew about it. Nobody would have guessed when Jim walked in today that he was the winner of the award. This is how he dresses for work, if anyone who doesn't know Jim. Okay, so it's my distinct pleasure to announce the award of Jim Edwards. Jim's contributions to CSM are so vast. Thank you. Jim's contributions to CSM are so vast and integral to its success, it's hard to imagine how the model exists in any form without his contributions. His accomplishments are myriad, but they include over 30,000 contributions to its code, the porting of CSM to dozens of systems around the world, and tuning of comp sets for efficiency and performance. Much of CSM's core infrastructure traces to Jim. He's been a primary designer and developer beyond the coupling infrastructure, parallel I/O, and a number of workflow tools, including the CSM Silk workflow that we use for CMIP6 and SMILE experiments. He's also been central to the large ensemble efforts such as Lens2 and the S2S simulations. As if that's not enough, Jim also sits at the forefront of enabling our new capabilities in the model, such as high resolution and ultra high resolution novel architectures, Python machine learning capabilities, bridges, lossy compression, and much more. In short, Jim's work underpins basically every aspect of CSM, and I think it is fair to say that there isn't a single researcher using CSM that has not benefited from the foundational excellence that he has brought to the model or his unwavering commitment to the long-term success of the project. Jim, congratulations. And as everyone knows by now, the penalty for winning this award is a presentation. Jim.
You're going to make me talk. All right, how do you do this? Is it okay? So I want to start out by thanking Dave and the committee and the people that nominated me, and especially, let's see if this works. I want to thank Mariana Wertenstein, who's been my mentor, my supervisor, and my good friend for many years. And she's watching from her home in Oslo this morning, and I just want to say I wouldn't be here without her. How did I get here? Hey, I'm going to start with a picture of my family. This is 1979. I'm sitting in front, my two brothers, Jeff and Joe, and my mom, Sharon. My father passed away when I was 13, and my mom raised 3 boys through their teenage years alone. That was, it took me a long time to appreciate what a monumental event that was. My mom passed away last year, but I'm sure she'd be proud to see me here this morning. Okay. And then I'm going to go talk a little bit about how I got here. And I'm going to start with the Lorenzo tractor, and I'll explain why. Well, first off, the Lorenzo tractor, it's a good metaphor for life, right? Every decision you make is how you got here. And any one of those decisions, the good, the bad, or the ugly, and you'd end up someplace else. Not necessarily better or worse, but someplace different. Anyway, I was an undergraduate in math and physics at Boise State University in around 1988, and our physics club got some money from the university to take a trip to San Francisco and go to the Auditorium. We were going to, research the exhibits there and maybe go back to Boise and build a Auditorium type facility. At the time, in that year of '88, chaos theory and nonlinear dynamics was a very popular topic in mathematics, and I was very excited about it. And there happened to be a conference at the same time we were going to be in San Francisco, in Santa Cruz at the University of Santa Cruz, on chaos theory and nonlinear dynamics. So I talked my group, which was about 8 people, into going to that conference. Now, we had no idea of a scientific conference. We didn't know we had to register, or pay. We showed up at the door, and after a few awkward minutes, they actually let us in. So we were quite grateful to be there. And they even invited us to the banquet dinner that evening, and I got to sit at a table next to Dr. Ed Lorenz. And I was there, I was probably complaining about something and about trying to get into grad school, and he said, well, you know, why don't you try atmospheric science? They'll pay you to go to grad school. I had never, ever considered anything like that, never thought of atmospheric science before, but that's how I ended up at CSU, and yeah. Then in 2000, we'll skip forward to 2003, I was invited to work at NCAR as the IBM on-site applications analyst. And so I was the only IBM employee on site at NCAR full-time. My boss was in Austin, Texas at one point, and Poughkeepsie, New York at another point. There was one boss I had for 2 or 3 years I never met in person. That was a sweet deal. But when I came to NCAR, we had a machine called Black Forest. It had a peak teraflop of 1.96. And just for comparison, I put the ratio up here. It's 5 orders of magnitude more power. So I think we figured out that what you could do in a day of computing of Duratio would have taken something like 300 years on Black Forest. So we've come a long way. I don't know if many of you remember the commercial about the Maytag repairman. Often being the application analyst at NCAR was like being the Maytag repairman. You had to kind of go out and find something to do. And one of the things that I was able to do was work on the home decor with Mark Taylor and Rich Loft and others, and actually put it in the CAM model at that time. It's now called the spectral element decor, and it's going to be our primary decor for CMIP 7, so that's pretty exciting. In 2012, NCAR moved their high performance computing facilities from Boulder to Cheyenne, Wyoming. I really didn't want to go to Cheyenne, so luckily there was a job available in CGD, and I took it. I've been there ever since. One of the things I did when I first came to CGD was the SEAM in the case control system that's used in CESM2. Hello? Yeah. So with the case control system, you can create hundreds of cases at various resolutions with just 4 pretty simple steps. I think that's pretty unique amongst climate models in the world. This work was done in collaboration with DOE partners. After the DOE E3SM model and CSM had separated, we managed to continue a collaboration until this day on the case control system. And I want to thank my DOE partners, Rob Jacob at Argonne, Jim Fukar at Sandia, and Jason Boutte at Lawrence Livermore. Jason is going to be giving a talk in the software engineering meeting tomorrow about the case control system. But I don't want to talk about the technical stuff. It's boring and you don't want to hear it. So I'm going to talk about the elephant in the room. And I want to make it clear that the ideas and opinions expressed herein are my own and not those of NSF, NCAR, or anybody else, but maybe by the end of the talk, they will be. So the title of my talk is Unlocking the Power of CSM Climate Modeling for Everyone. And first, I want to talk a little bit about the immediacy of climate change, of the climate crisis. We all know that here, but I think I should reiterate. And why I think improving our educational outreach is important. Some current CSM projects that support education, Dave's already talked about them a little bit, and then new projects we might consider. How this will benefit the CSM community. Oh, there we go. So I'll start with, does it? Okay. This is 2023 annual CO2 emissions. I can't remember the total number, but it's something like 37 billion or 37 gigatons of emissions in 2023. Globally average temperature is about 1.4 degrees above what it was in 1850. We agreed in the Paris Accords to 1.5 degrees. I'm afraid we're going to blow past that in the next year or two. Daily sea surface temperature anomalies, they broke a record every day last year. And this year, I think they've broken that record from last year every day except 2 in May. And this is planetary heat uptake, and I show this one in particular because RCP 85 from CMEP 6, that was like our worst imagined projection of what the future might look like. And we are arguably outside the worst case that we thought we would get to. Sea level rise could put up to 250 million people at risk in the next 30 years. That's 1 million people for everybody in this room. Didn't get my notes. Oh well. And climate change is no longer a hypothetical future that we should try to avoid. It's a clear and present danger that we need to learn to navigate. I like this graph of tipping points. It's something that every middle schooler can understand and has probably experienced. This is a graph that the NCAR library helped me put together, and it's a list of CESM citations in peer-reviewed journals. There's something like 3,300 citations of CESM. So we have made a clear and important contribution to the science, but CO2 levels in the atmosphere continue to rise. So are we doing the right thing? We could, participate in protest and civil disobedience, and I hope that some of you will. You might even consider industrial sabotage. Boulder's own Danny Goldhaber made a movie based on that book, and you can rent it on Hulu and watch it today if you like. So what about education? Right. I had a bunch to say about education, but I can't find my notes, and darn it. I'm just going to, in the interest of time, go on. So the CESM tutorial is one aspect that we've been doing since about 2010. We reach maybe 150, 200 people a year with the tutorial. And in more recent years, through, sorry. In more recent years, we've been able to do this online and reach even more people. And the recent Kigali, Rwanda WCRP tutorial had students from all these places on the map. So we are reaching a number of people. But we could reach a lot more. CSM simpler models is one aspect of CSM that we should expand in education. In the atmosphere, we have everything from dynamical core, idealized dynamical core experiments, aquaplanet experiments, and single column models that are available as part of CSM. This tool set should be, I think, expanded and explored better. We also have pencil and slab ocean models and the SLIM simple land interface model, and we can couple all these together to do very simplified experiments in a coupled regime. Dave talked about Cupid, the CSM Unified Post-Processing and Diagnostics package. He also talked about how little funding there is for this package, but I think it's really necessary and we should consider supporting it more fully. SEMA, Dave also talked about SEMA, the System for Integrated Modeling of the Atmosphere. We're in the early stages of development of SEMA, and part of what we're doing is making the parameterization so that you can run them in isolation for testing and development. This is also ideal for education and for machine learning to compare a dynamic algorithm to a machine learning counterpart. So some ideas for improving our educational outreach is providing suggested curriculum incorporating CSM for classes at all levels, so high school, undergraduate, and graduate level courses. Educators in our country and in much of the world are overworked and underpaid. If we provided the curriculum for them to use, I'm sure they'd be happy to take advantage of it. I think we should appoint an education and outreach liaison to improve communication between model developers and educators, and encourage and support outside contributions to the CSM. All of these will require an increased investment in the CSM software infrastructure. A lot of the tools that I work on, the PIO library, the case control system, the CMEPS mediator, the CDEPS data models, they work best. When they work best, you don't even notice them. It's only when they fail that scientists tend to notice they're there. So it's hard to get support for these things, but I think we really need to consider supporting them better to support the science. The community Earth system model is a community model. It's the most portable, configurable, customizable climate model in the world. It's ideally positioned as an educational tool. And I think crowdsourcing has the potential to provide novel solutions to the myriad problems associated with a warming planet. The more people who know about climate change and understand the science behind it, the less likely we are to have political despots manipulating our population to make bad choices. Hang on. And growing the CSM community is our best hope of addressing those ever-increasing challenges with considered scientific policies. Thank you.
Any questions or comments? Yes. Country reminding me to give you your award. Yes. So this is the award.
Thank you.
It's nice and weighty.
It's heavy.
Yeah. It's heavy. We will get a photo, a proper photo afterwards. Does anyone have any questions or comments for Jim?
Well, after the photo, I started.
All right, thank you, Jim. So next up, before the break, our last thing before the break is the Graduate Student Award, and so I would like to announce the award. Actually, do we have the? Okay, the award winner this year is Samuel Mogan from the University of Colorado at Boulder for his outstanding contributions to ocean biogeochemical prediction research. So Samuel, where are you? Please come. Here's your award here, Will.
Thank you.
Okay, so Samuel is the winner of this year's award. He is a graduate student at the University of Colorado. He's been recognized for his contributions to research on seasonal to multi-year prediction using the CSM prediction ensembles in collaboration with researchers in Earth system prediction and biogeochemistry working groups. In particular, his work has contributed to fundamental advancements in our understanding of ocean biogeochemical predictability, and his work has direct actionable science implications, for example, is particularly relevant for marine resource management. So I look forward to hearing about Samuel's work. Take it away.
Thank you so much for having me. I'm really honored to be here. Again, my name is Sam Mogan. I'm a PhD candidate here in Boulder at the University of Colorado. Before I get started, I just want to say many thanks to all my collaborators listed on the screen, in particular my advisor, Dr. Nikki Lewandowski, and anyone in the Ocean Biogeochemistry Research Group at CU Boulder. Today I'll be talking about a study we have in review entitled Multi-Month Forecast of Marine Heat Waves and Ocean Acidification Extremes. Just a brief refresher to get started, climate change, we can think about it as a long-term threat for marine ecosystems, and in the context of today, we're going to think about two in particular. We're going to think about excess heat, so long-term ocean warming, threatening ocean ecosystems, and also an accumulation of carbon that we've emitted into the atmosphere, into the ocean, driving long-term ocean acidification. Both of these are big threats for marine ecosystems and big problems for marine ecosystem managers. But on top of these, and also I should note, warming and acidification are often closely linked, but can also vary on different timescales and driven by different climate features and climate variability. On top of these long-term threats, there's also a growing concern about the impacts of short-term variability, and in particular extreme events, in particular extreme heat and extreme carbon events. So when we think about these events, we can think about marine heat waves, short-term periods where SST anomalies spike, and ocean acidification extremes, short-term periods where acidification signals spike. A little more context on starting with marine heat waves. We can think about marine heat waves as SST anomalies, again, greater than the 90th percentile. In this case, we're going to remove long-term warming trends and long-term seasonal climatologies when we're defining these marine heat waves. I've picked one marine heat wave in particular to illustrate the impacts of these. So we're looking at SST anomalies in the Northeast Pacific in July of 2014 during kind of the peak of the blob, which was this really strong, long-lasting marine heat wave from roughly 2013 through 2016, 2017, which was forced by a persistent high-pressure ridge which sat over this region, leading to these really strong temperature anomalies. The hatching here is just indicating extreme conditions where the marine heat wave would have been defined. And the blob had negative impacts on marine ecosystems at all levels of the marine ecosystem, from primary producers at the base of the food web all the way up to larger organisms, more charismatic marine organisms. So there was an increase in sea lion starvation, an increase in whale beaching and starvation, an increase in seabird mortality associated with the blob. So really profound impacts on marine ecosystems. Marine heat waves are luckily pretty well studied. Lots of people are doing work on these marine heat waves, and we have a good understanding of what's driving a lot of these heat waves and their impacts on organisms and ecosystems. In contrast, ocean acidification extremes, or OAX, are relatively poorly understood and understudied. And in this case, we're going to define our OAX as aragonite saturation states less than the 10th percentile. Aragonite is a mineral form of calcium carbonate used to build and maintain shells for all the shell-building organisms that live in the ocean. So when this aragonite saturation state is really low, it becomes much harder to build and maintain a shell, which can have pretty profound impacts for organisms at the base and higher up in the food web. I've chosen an example here of an ocean acidification extreme associated with the 2000 La Nina. So this is aragonite saturation state anomalies in January of 2000, just to highlight that while we might expect at this period there would be relatively low temperatures associated with La Nina in the eastern tropical Pacific, we're also seeing really high acidification signals during this period. So they're not always going to be closely related. And what's driving these events is often enhanced vertical mixing. So if there's, for example, cooling at the surface of the ocean, or potentially increase in vertical mixing, more corrosive water from the subsurface ocean is going to be brought into the surface, driving an increase in the acidification signal. So again, these are relatively understudied, but potentially have pretty profound impacts on ecosystems. Really, across the global ocean, there's a limitation in the number of observations we have of biogeochemistry and ocean acidification. So the direct impacts of these are much harder to study, but you can imagine an increase in acidification just exposing a shell here, a vulnerable shell, to acidic conditions. You could see a degradation in the shell over a period of about a month and a half. So while these are relatively understudied, they do have profound impacts on ecosystems. So we know what we're trying to understand and how we want to predict them. This is how we're going to try and predict them. We're going to use this Community or System Model version 2, Seasonal to Multi-Year Large Ensemble, or CESM SMILE. CESM SMILE was developed for this subseasonal to seasonal prediction. And here we're just looking at temperature anomalies from the forced ocean sea ice reconstruction, which is used to initialize CSM SMILE. The forced ocean sea ice reconstruction just takes the ocean and sea ice component of CSM and forces it with historical atmosphere and terrestrial fluxes over the historical period. Here we're just looking at temperature anomalies at a random point in the Pacific sector. We don't need to dive too much into what's actually going on at this point. But at various points, we can stop providing this surface forcing to the ocean and sea ice models and allow the model to spin up as a fully coupled or system model run. We're going to slightly perturb the initial conditions to generate 20 ensemble members for each of these initializations. And the model is initialized 4 times a year, February, May, August, and November over the historical period. And each of these forecasts is then integrated for 2 years. So we have a lot of forecasts, and to verify and validate these, we're going to turn towards the observational record and see how well this works. So in this case, we're going to compare to an observational product developed by Greger et al. In 2020, which takes the relatively sparse ocean biogeochemical data that we have and the observations we have and uses machine learning algorithms to gap fill across the ocean in this historical record and does a really good job at recreating historical acidification signals. Jumping into our results, our forecast skill metric here, how well our model is doing at forecasting these events, is the Symmetric Extremal Dependence Index. This is a probabilistic forecast metric. It's going to look similar to an anomaly correlation coefficient on the color bar, but it's a different metric. Any value less than 0 is unskillful. The closer you get to -1, the worse the forecast is. And then theoretically, any value above 0 is a skillful forecast, and the closer you are to 1, the closer you are to having a perfect forecasting system. We also developed another metric of testing the significance of this, just using a bootstrapping method. So anywhere there's stippling on these maps, skill was insignificant relative to this bootstrap skill, the 95% confidence interval. So starting with our marine heat waves, 1.5 months after the model is initialized as a fully coupled or system model run, we see a few patterns pop out, but generally we're seeing high skill in the Eastern tropical and generally Eastern Pacific sector. But generally across the global ocean, we're finding high skill 1.5 months after initialization. And as we move further from initialization, we're generally seeing a degradation in skill as your system model spins further away from the real world. But even 10.5 months after initialization, we still find high skill, particularly in the Eastern and tropical Pacific sectors. These results are supported in the literature and echo previous results from Jaycox et al., for example, who found similar patterns using climate models, the North American Multi-Model Ensemble, to simulate and forecast these marine heat waves. So in contrast, our ocean acidification extremes have not been assessed for their forecast and their ability to predict them. So starting in the top panel, 1.5 months after initialization in the top right, we find high skill in the tropical and eastern Pacific Ocean in particular, especially in the Southern Ocean as well, but generally high global skill. And as we move further from initialization, skill tends to degrade, but even 10.5 months after initialization, we find high skill in a few key regions, including the tropical and Northeast Pacific sectors. We're particularly interested in this California current sector, which has high skill even 10.5 months after this forecast is initialized. So here, we're finding high skill for both these marine heat waves and ocean acidification extremes. And skill tends to be highest in the Eastern Pacific sector. Why is this skill so high in the Eastern Pacific sector? As a lot of you might have guessed, this pattern, especially if we just look at 1.5 months after initialization in the Eastern Pacific, it looks very similar to an El Nino event. So we find generally that skill is enhanced when our forecasts are initialized during INSO conditions. So if a model initialization is completed during an El Nino or a La Nina, we do find a gain in skill relative to initializations during neutral conditions of El Nino. Knowing this, a forecast of opportunity was generated in November of 2023. So starting in the top panel, we're just looking at the forecast Nino 3.4 anomaly as it was forecast in November of 2023. The solid black line is indicating the CSM SMILE forecast, and the dashed gray line on the board is showing the observational record through late March of this year. We generally find that CSM SMILE forecast the El Nino event pretty well and captured it was well within the range of the ensemble members. So this is doing well. And moving on, we also generated outlooks for both marine heat waves and ocean acidification extremes throughout 2024. Starting with marine heat waves, we find in December of 2023, so last year, we saw this El Nino event that was occurring. It was forecast and associated with marine heat waves in the eastern tropical Pacific and in various places across the global ocean. By June of this year, so right now, we are seeing very few heat waves in the tropics, but in the extratropics and subtropics, potentially some strong heat waves occurring there. And then by December of this year, very few marine heat waves associated with this. I should also note we're masking these maps by regions in the hindcast period that were skillful. So these are regions where we would be very confident in our forecast to generate a skillful forecast here. And then moving on to ocean acidification extremes, in December of last year, we would have expected high acidification events, especially in the subtropic Pacific sector and potentially in the eastern Indian Ocean. By June of this year, I just want to highlight we are expecting an ocean acidification extreme event in the Gulf of Alaska region here, and then by the end of the year, potentially some strong acidification extreme events in the California current and subtropical region, subtropical Pacific. In terms of verification of this live forecast, the SST anomalies that we have available SST anomalies pretty relatively live, so we could verify this marine heat wave forecast, but in contrast, our ocean acidification extreme events, we're not really going to be able to verify or validate this for another year and a half or two when these products for acidification come online from the relatively sparse observations that we do have. But generally, we're forecasting widespread marine heat wave and ocean acidification events throughout 2024. In the future, we're hoping to expand and continue working in the CSM SMILE framework, but starting to look at a high resolution framework. So what I'm displaying here is high resolution reconstruction, 10th of a degree developed by Cromhart et al. And these are just omega aragonite saturation state anomalies in the eastern tropical California current Pacific region in comparison to a low resolution reconstruction. So the 1 degree CSM FOSSI used to initialize a CSM SMILE. And what we really hope to do by increasing the resolution here is creating more actionable predictions on the scales that are actually needed for marine managers and fisheries. So if we look at this high resolution forecast, we're actually capturing coastally resolved, we're having coastal processes resolved here, and would actually be able to compare to direct observations of acidification, which we do have relatively up to date. So in conclusion, CSM SMILE is skillfully forecasting marine heat waves and OAX up to a year in advance. SMILE forecasts widespread marine heat wave and OAX in key regions in 2024. And in the future, we're hoping to generate high-resolution forecasts of regional biogeochemical signals, as particularly interested in the California current sector. With that, I will open it up to any questions. Our preprint is available at this QR code down here. Thank you very much.
Yeah, great job, Sam. Really cool stuff. Exciting. So I'm noticing the predictability in the coral triangle in the West Pacific for marine heat waves is bad. Yes. And that's where we need it. So thoughts about what can we do? Can we use one of these crazy new grids that were presented earlier? What do you think?
Yeah, we would be really interested in looking at a different grid and sort of different model configuration. I will also note a lot of, the Australian, basically scientists in Australia who focus on marine heat waves, which is where a lot of this marine heat wave research is occurring, do have models that function pretty well in the Pacific Triangle region and do provide relatively up-to-date outlooks for corals and coral bleaching events associated with marine heat waves. But I think this is definitely an area where we would be interested in trying to improve model performance because as you said, it is a very, very important region.
So if we're going to produce a CSM3 high-resolution configuration, which we would potentially use for these kinds of forecasts, or anything specific you would want to see in that particular ensemble?
Well, including ocean biogeochemistry, obviously, would be great. I think also potentially expanding and testing out more complex dynamics of phytoplankton and zooplankton, increasing the functional groups there to potentially provide more information and be really interesting for providing more relevant information associated with these extreme events.
Questions for Sam? Thank you, Sam. So we are a few minutes before our scheduled break. We can just go to break, but since I kind of rushed us through questions, I will just give an opportunity now. If anyone does have a more general CSM question, I can take that or put them into the Slido. And just so you know that if you didn't get the link to the Slido there, which it came by fast, it is going to be, if it's not already posted, into the agenda. So you should be able to go there and think about questions that come up during the week.
Obviously, I'm not shy. Dave, I think I speak for a lot of people where I just want to say we really appreciate your leadership in taking this on, and it's, let's just give him a round of applause for taking on the hamster wheel.
Thank you. I appreciate that, and also recognize all the huge amount of work that's gone into this project from the working group co-chairs and all the previous chief scientists. I look around the room and it feels like everybody I'm looking at is a chief scientist, former chief scientist. So it is an honor, though. I'm enjoying the challenge. So thank you. Okay, then I will take the prerogative to push us into break for a longer coffee break. After the break, we have three really exciting plenary presentations. They're going to give us some of these perspectives on some of these things we're thinking about in the future, and also we're going to learn from Jane Mulcahy at the Met Office about their experience in building an Earth system model, sort of a sister model to ours. So we'll see you after the break. I think we resume at 10:40. Okay, thanks everyone. So let's get started. We have a really fun set of plenary speakers, I think. I had slight stress because our second plenary speaker wasn't here, but she went to the Mesa Lab accidentally, showed up here. So, and we have one speaker online, unfortunately. But so we're going to start with Jane Mulcahy. She is a senior research scientist working in the joint NERC Met Office Earth System Model Development Core Development Group, where she is managing the science development of the UK ESM2 model. So effectively, she is the equivalent of me at the UK Met Office in terms of her role. Her background and research interests are in aerosols and interactions with the full Earth system, but as a head of the development team, obviously she has interests that are much broader than that. And in particular, she was here last week and she wanted to talk to us about fire emissions and interactive ice sheets and our plans for CMIP7. But I'm really excited to hear from her about their experience in developing their Earth system model. I think it's going to be really interesting and rewarding and for us to learn what the experience is from another modeling center. So I'll turn it over to Jane.
Great. Thanks, Dave. And yeah, many thanks for the invite. It's a pleasure to be here and share a little bit with you about our plans for UKSM2, our next flagship UK Earth System model. So obviously this, yeah, as I say, my background is in aerosols, so you know, I'm covering topics today that are really work done by a lot of my colleagues. So I didn't even dare put names on the title slide here because really I was afraid I'd miss people off. So it's a big group. It comprises our UKSM core group, which focuses on the Earth System components, as well as the physical model development team and our many collaborators outside the office as well. So I just thought I'd start by kind of describing our definition of an Earth system model from our perspective. I understand this kind of can vary in terms of what we mean by Earth system models across institutes and so on. So in our case, Earth system models really represent both the physical climate and really the carbon cycle and nitrogen cycles as well as other components of the fully coupled Earth system that we think are important for future climate change. So this is atmospheric chemistry, aerosols, obviously, vegetation, marine, biogeochemistry, and now into the future, cryosphere processes as well. So UKSM is the UK's Earth system model, so it's really our, I guess, our attempt at a CESM, and this is not just done by the Met Office, so this is done jointly by both the Met Office and the Natural Environmental Research Council and all the kind of research centres that sit under NERC. So at its core is the HAGEM3 global coupled physical climate model, and then we add on the Earth system components onto that, so the biogeochemical processes, the chemistry, the aerosol, vegetation, and cryosphere as well. So UKSM1 was our first attempt at building this kind of community model, and this was released back in 2019, and this played a huge role in our contribution to CMIP6. We then released an updated version at UKSM 1.1, and I'll talk about that in a little bit. So that we released last year, and now we're deep in the depths of UKSM2, so similar to you guys with your CSM3. And so this is the model that we hope will contribute into CMIP7 and also beyond that as well. So I'm going to start a little bit with CMIP7 plans. Dave thankfully introduced some of that earlier, so that will help me kind of speed up and not dwell too much on it. And these plans are fast evolving, so I'm sure many of you are probably over familiar with these schematics that are coming out of the CMIP IPO. So let's see if I get this cursor working. Oh, I'm pressing the wrong button, that's why. So here on the left-hand side, we've got the schematic, representing basically the planned experiment structure for CMIP7. And of course, the main change here relative to CMIP6 is the fast-track simulations that Dave referred to earlier. And on the right-hand side, we've got the kind of latest timeline from the CMIP IPO. So as Dave mentioned earlier, really that's challenging for all the modelling centres, I think, in terms of setting up and having simulations running kind of early to mid 2025 in order to have the data delivered to feed into the IPCC, through 2027 into 2028. So for us with UKSM2, this is presenting significant challenges. We're trying to build a big model, bringing in some key Earth system science capability that I'll talk about in a second, but we fear that mightn't be ready in time to deliver to the fast track. And so really, we were originally aiming to have UKSM2 ready more around the time of early first quarter of 2026. And so we're not, hugely comfortable in really putting ourselves under pressure to release the flagship model until we're totally happy with the performance of that configuration. So we've proposed a backup solution just in case we're not ready. And this is going to be called UKSM 1.3. So it's an updated version of our kind of CMIP 6 type model. And my understanding is that many other of the modeling centres are considering this type of approach as well, because many of us just aren't going to be ready with our new latest and bestest. The idea then, I'll just go back a second. The idea then is UKSM2 can feed into the kind of the longer timescale of the community MIPS, so the key science MIPS. And for us, we feel actually that these community MIPS are just as important, and particularly scientifically in terms of, delivering, key new science. And so we're hoping that UKSM2 can really feed into that process. So UKSM 1.3, what is it? So this is an updated version of our CMIP 6 model. So really it's UKSM 1.1. So this was the configuration that we released last year, and one of the key new science developments within that configuration is the improved historical temperature record. So many of you might be aware that UKSM1 struggled with a very cold pothole bias in the historical record with UKSM1, and that was particularly evident in the Northern Hemisphere, where we had an anomaly of 1 Kelvin relative to the observations. So UKSM 1.1 in the red here really compares much better against the observations right over the historical period. And the main developments that went in there was really an improved representation of our aerosol sulfate cycle. The developments didn't have much of an impact on the ECS, so we're still a high ECS model, so we had an ECS of greater than 5 as well with UKSM1. So you can see here towards the end of the historical period, we're still warming now too much compared to the observations. So in addition to UKSM1, UKSM 1.3 will then also include emission-driven configuration for CO2, but also methane. And we're also hoping to include the interactive ice sheets in there as well, which I'll talk a little bit more about in a second as well. So we already have a variant of this running in some of our UK-based projects, so we're fairly confident that we can deliver this model for the fast track if needed. I won't dwell on this slide much, just to say that in addition to an ESM-based model, we're also hoping to we'll probably have a physical model, a kind of a HAGEM GC5-based contribution at the low resolution, kind of similar to what we did with GC 3.1 in CMIP 6. And also we're going to have a high resolution frontiers simulation. So this is coming from Malcolm Roberts, the configuration they're going to probably call GC5 Erie. So that's just to kind of reflect on the different types of model configurations that will be feeding into the fast track. So now to UKSM2 and what we plan to do there. So this is a kind of a busy schematic, I apologize for that, but really it just really outlines the different components that form the basis of UKSM2. So in this we have the physical components here in blue, covering the atmosphere, the land surface, the ocean, sea ice, and simplified aerosol. And then in green we have the Earth system components, so the full atmospheric chemistry, the TRIFID and carbon cycle components in the land surface, the Medusa ocean biogeochemistry model, and for UKSM2 we plan to bring in the ice sheets as well. So in red I've tried to highlight what's coming in new for UKSM2, so the key bit there are the ice sheets obviously, Inferno in terms of interactive fire emissions, and also this closed cycle of the CO2 and methane cycles. The other thing I wanted to highlight here with this slide is really the level of prognostic coupling we try to have in our Earth system model. So we really try and maximize the level of couplings that we have between these components, where we feel those couplings are important from an Earth system and climate change perspective. I mentioned before that the physical component of this, I'm struggling to get my, I'll try and manage without my pointer doesn't seem to be working. The physical component of this will be the GC5 configuration, and the resolution will be kind of the same in terms of our workhorse model, will be the same as what we had in UKSM1. So that's N96L85, which is approximately about 130 kilometers in the atmosphere and 1 degree in the ocean. We do have other variants of UKSM1, particularly a hybrid configuration where we try and run the dynamics of the atmosphere and the ocean at a higher resolution and then degrade the resolution of some of the Earth system components to try and give us some benefit from resolution in terms of dynamics. But they're still kind of under development, but hopefully they will come into play with UKSM2 a little bit further on. I'll skip over this because really what I'm going to do now, this is just really highlighting some of the key new science capability and the kind of level, the kind of, I guess the traffic light system is really the level of scientific maturity of where we are with this new capability coming into UKSM2. So I'm just going to touch a little bit more now in the next few slides in terms of some of these examples. I'm going to start with GC5. So this is the global coupled atmosphere-ocean configuration that forms the basis, really the building block of UKSM models. GC5 is comprising of the GAL9 atmosphere and land configurations and the GOSI9 package for ocean and sea ice. And by all our kind of standard evaluation metrics, this model is generally performing much better than its predecessor model, which was GA8. So the histogram on the left-hand side here is yeah, no, it's not going to work for me. So I'll try and describe. The histogram on the left is basically showing the change in RMS error of a large number of metrics that we have in our standard evaluation package. So as that shifts to the right, so this is in red is a higher resolution, and in blue is a low resolution configurations. So shifting to the right shows that across most of these metrics, we are improving the performance of the model. At the bottom then, in the middle, we have the ACC transport in the ocean. And you can see here, this figure compares multiple resolutions with a 1 degree kind of in the maroony color and then the higher resolution in the cyan and blue, comparing against the observations in the black. And you can see that the 1 degree here is performing better for the ACC transport than actually any of the other configurations. However, when we started to run some transient simulations with this new GC5 model, you can see here the ensemble mean in black compared to the Hadcroft data in green, that the model is warming far too strongly in the late historical period. And we actually have an even higher ECS than we did in our CMIP6 model, so it's over 6 Kelvin. So this was deemed really to be unacceptable for climate simulation, climate application purposes. And so a project was initiated, which we call GC5 Central, so this is led by Alejandro Boda Salcedo, where we use a kind of a PPE, an emulator-based approach, basically to produce a parameter set of GC5, which basically brings the effective climate sensitivity to within the IPCC very likely range, and also targets this improved historical performance without then unacceptably degrading kind of the present-day climate metrics, which were all performing much better in the standard GC5 development. So the middle here basically shows the output of the PPE, where we're targeting basically a kind of feedback parameter below minus 1.4 watts per meter squared per Kelvin. And the aggregate error represents the kind of a basket of about 18 or so climate metrics, where basically they're trying to minimize impact on those climate metrics while shifting the feedback parameter to those more negative values. And on the right-hand side, then, we've taken some of those optimized runs in purple in the middle plot, and we've run some 4 times CO2 experiments with those to produce estimates of effective climate sensitivity. So here we're comparing variance in the orange against the CMIP6 models, but also the emergent, what we call the emergent configuration of GC5, which was over 6K. And you can see that we are able to get effective climate sensitivity values down to about 4.5 Kelvin. So the idea is that we try and take these parameter settings that are coming out of this project and feed that also into UKSM2. So that project is now kind of converging on a set of solutions, and they're spinning up new transient simulations. So the plot here on the bottom right is really only an example. I wouldn't take too much from that, as it's not really the final configuration. So the other key thing we want to do is move towards emission-driven simulation. So Dave mentioned this already also today. So really we're trying to do this and really push towards like minimizing really the amount of concentration CO2 simulations that we do. And this is really because running an emission-driven mode really allows us to capture the full uncertainty in the carbon cycle processes and important feedbacks that are really important, particularly for the future scenarios and when you come to think about carbon budgets. And this really allows us to understand the system response and reversibility of the system, particularly when you start looking at zero or net negative emissions. So the key climate metrics kind of in this space are really the transient climate response to cumulative emissions of CO2 and the ZEC, the zero emission commitment. So these flat 10 experiments, which I'm showing here on the bottom right, have recently now been approved for inclusion in the fast track. So they're kind of a simplified method for us to diagnose these kind of important climate metrics. So running an emission-driven mode isn't necessarily new for us. We have done that before, that's fine. So the plots on the top right show UKSM1 in the red, emission-driven configuration, and how it, reasonably well captures the seasonal cycle of CO2 at Mauna Loa and Point Barrow. But really what we're pushing now is really to do this as standard in our standard release configurations and our simulations contributing to CMIP. In addition to that, we want to simulate the global methane cycle fully interactively. So again, this has been developed on top of UKSM1 by Gert Folberth and others. And on the left-hand side here, we're looking at a simulation, a transient simulation of a concentration-driven methane simulation in black, and comparing that to an emission-driven simulation of methane in red. So you can see the model performs reasonably well, but we do have a little bit of an underestimation of the methane, particularly towards the end of the historical period as anthropogenic emissions ramp up. On the right-hand side, we're comparing UKSM on the top with GOSAT satellite data on the bottom. And again, here you can see that actually the model captures really well the kind of intrahemispheric gradient in methane and also the temporal evolution. So that really this allows us to capture kind of important couplings and feedbacks between the global wetlands, which we already include, and atmospheric chemistry. And this allows us to look at things like assess the impacts of mitigation policies, such as the Global Methane Pledge. So here Fiona O'Connor is looking at the impact of the Global Methane Pledge that came out of COP26 on forcing and things like air quality. So on the left-hand side here, she's computing the ERF in 2030 relative to 2020, so kind of present day, using kind of current legislation, which is reflected here in the counterfactual, and global methane pledge simulations, where they've implemented kind of a max feasible reduction in methane emissions. And so you can see in the bottom plot here on the left, the RF difference. So you can see that the global methane pledge can significantly reduce the RF in 2030 by just under half a watt per square metre. And also on the right-hand side, we're looking at changes in surface ozone concentration. So obviously methane is an important tropospheric ozone precursor. So obviously by reducing the methane, we're getting global mean reductions in surface ozone. So this is really a kind of a win-win for both climate and air quality. So this is the type of applications that we really want to apply this capability to. I've mentioned interactive fire, so we're hoping to implement the Inferno, the interactive fire and emission algorithm for natural environments scheme into UKSM2. So this is new for us and a bit scary, to be honest, from my perspective. But there's been a lot of development and evaluation that's gone into this. So on the left-hand side, these are some PI control simulations where we've switched on the interactive fire. So if you focus on the kind of dark blue curve on the top and compare that with the kind of pinky line where we've switched on fire, and a kind of representation of the global mean burnt area from GFED4, you can see actually that our model is simulating reasonably well the global mean burnt area. But when you move over to the right and start looking at the spatial distributions of the burnt area, you can see that obviously we've got some issues there, particularly maybe overestimations over North America, parts of South America as well, and also places like Scandinavia. And then we've got low biases, particularly in the northern hemisphere high latitudes. And this is, believe this is probably because we've got no representation of peat in there yet. So when we couple that through to the atmospheric composition, so you can see that feeding through to the aerosol optical depth on the bottom. This is kind of faded out a little bit on the screen, but we're getting low, basic strong reductions in our northern hemisphere high latitude AODs, as we're really just not capturing the emissions in those regions currently. And then we're getting some positive changes, obviously, in the tropical regions. And you can also see here the impacts of the fire emissions feeding back onto the vegetation, driving changes in dust emissions as well over the Sahelian region. On the left-hand side, I'm just showing an example, really, of changes in the tropical tree fraction over the Amazon. again, when we switch on fire. We're also including here another new development where we're implementing thermal acclimation of photosynthesis, which we're hoping to include in UKSM2. And you can see both of these changes are having often opposing changes in terms of changes in tropical tree fraction. And so in some cases, particularly the West Amazon, the changes with fire and acclimation are improving our simulation relative to the observations, which is represented here by the kind of dash line on the top, but in other areas we're degrading that bias. So these are kind of simulations, we're spinning up these simulations and evaluating them now quite actively. Permafrost is another thing that we're hoping to include in UKSM2. We don't have that in there yet, so this is work led by Eleanor Burke at the Met Office. And so she has implemented vertically resolved soil, carbon and nitrogen in kind of mainly in offline joules. So this is all up to now really been done in the offline land model. But really we're getting an overall pretty good comparison of the total soil carbon shown on the top here against the observations, and also in the vertically resolved carbon and nitrogen fields. And really the work now is really trying to get that technically coupled within the fully coupled system. So that's kind of an ongoing activity at the moment. With ice sheets, we're hoping to include the unicycles, which is basically interactive models for both Greenland and Antarctica. So we're hoping to simulate that in UKSM2, basically to enable us to start making projections of sea level rise with UKSM, and also increasingly looking in the realm of climate tipping points. So again, a version of the Greenland ice sheet was included in a configuration of UKSM1 and did contribute to ISMIP6 in CMIP6, but it wasn't really part of the standard configuration. So it was really a kind of a specialized configuration that really only Robin Smith could run. None of the rest of us could go near it. So these are some results on the right-hand side from Robin's work and Anthony Sheehan's work, where they've implemented the Greenland and Antarctic ice sheets in UKSM1 and looking at the surface mass, and they've run some kind of extended SSP 585 experiments out to 2100, or out to 2200 actually. And so here we're looking at the surface mass balance of Greenland and the surface and basal mass balance of Antarctica at 2100, and the resulting contribution of that to sea level rise on the right-hand side. Finally, a note on atmospheric composition. So there's lots of words on this, so don't worry too much. But just to say that we've got a whole package of changes coming in there, improving our representation of aerosols. In addition to the fire emissions, we're also including nitrate aerosols, which we didn't have in UKSM1, and also other improvements across the board in terms of things like the representation of IBOCs, boundary layer nucleation. And on the chemistry side, one of the key improvements we were targeting was the improvement of the stratospheric ozone biases. So if you look at the bottom there, the purple line is UKSM1 compared to the CMIP6 ensemble mean of the total column ozone. So you can see we had a really significant positive bias in our UKSM1 simulations. So the chemists have really produced a package of changes that have led to a significant improvement in that, which is represented here by the kind of purpley blue line. And so we're hoping to implement that. We still have too strong a decline, too strong a trend in the reduction of ozone, and so that's leading to some implications in terms of the ozone forcing. But we're hoping at least to have some better representation of the stratospheric ozone in UKSM2. And the right-hand side is really just showing a kind of an evaluation of our aerosol number concentrations at different size ranges, where we're bringing some of these packages together. So you can see in the control, which is a UKSM 1.1 configuration, we had very low biases actually in our aerosol number concentration. And so bringing these new processes into the system is generally improving those biases. So that's kind of some good news. And so that's it. So I'll leave you with a summary. Really just wanted to highlight some of the key new science capability that we were bringing into UKSM2. These are all progressing quite nicely. We haven't got to the stage of running transient simulations, maybe like CSM3 has at this point in time. And that's part of that's because we've got this shifting physical model really under our feet still. But really the aim is really, with UKSM, we really try to be as prognostic and as interactive as possible. And really where we feel those coupled feedbacks are important. And we can do this really because we do always have the kind of physical model as backup. So that's almost like a safe model configuration, which doesn't have that level of coupling. So we have that kind of traceability of what's the benefit of those couplings, or you know, what's the role of those feedbacks in our modeler system. Obviously, CMIP7 is very challenging for us. So we have, in many respects, it's disappointing, but we do have a model that can be used if we're not ready with UKSM2. Ideally, it'd be nice to have UKSM2 ready, but it is what it is. And really the main driver as well, in terms of highlighting our capability and our desire to really run with emission-driven configurations. And really, we don't really plan to run many concentration-driven simulations at all, really, in CMIP7. Pretty much the bare minimum. I think we're saying we'll run the 1%, the 4 times CO2, and the parallel PI control, and that's kind of it. So yeah, I'll leave it there, and I'm happy to take any questions.
Please come up to the mic.
So you've got there that to reduce the climate sensitivity, the parameters, are they all in the atmosphere model or are they elsewhere?
Yes, really good point. So this is all in the atmosphere. So the PPE, which is led by David Sexton and his team, they're really just running atmosphere only. It's an atmosphere only PPE. So they're just perturbing, I think, about 70 odd parameters across all the kind of physics in the atmosphere, microphysics, convection, aerosol, and that kind of thing. But yeah, it's...
Can you tell us what the most important parameters are?
I didn't check this before I came, but to be honest, there's stuff in the microphysics and I think within the convection scheme that are playing a strong role there, but I couldn't say exactly in terms of the final configuration. There's been playing around with a number of different options, and sometimes, but I think they have a fairly good handle from the work, and that's one. It's not ideal to try and take this approach and push your ECS down, by doing this approach, but hopefully we can also learn from that in terms of what based on what parameters we end up tuning, and kind of feed that into the future development as well in terms of understanding the kind of drivers behind the high ECS. So I'll get back to you on the key players.
I'd like to add just one small point here. I happened to meet the person who's leading the IPSL development last week, and they're considering for CMIP7 to having an ensemble of ECS configurations, essentially a small ensemble, 2 or 3. I think GIS is thinking about it as well. I think we could probably do that as well because we've been doing some parametric assessments, so it's an interesting thing for us to be thinking about as we move into CMIP7. I don't know if it would be an official thing or something we do on the side. So I just wanted to add that.
Yeah, I think that's a good point. We had always said we'd keep the original configuration in the pack as well and make that usable. Sometimes it boils down to practicality of trying to maintain all these configurations, but I know in particular for detection and attribution, they're still keen in just using that kind of higher ECS emergent model.
Actually related to my question, I'm really excited to hear you're planning to use emission-driven simulations as your primary mode. And I'm curious about land parameters as well, and if you're considering how differences in particularly land carbon uptake might vary with parameters when you're in emissions-driven mode that might be quite important for your emergent climate in the future, and if you have plans to sort of span that range in any way.
Yeah, I mean, not in the current space, but with the joules in the offline joules model, I know they are kind of looking towards running a kind of a perturb parameter ensemble in that space yet, but that hasn't kind of directly fed into our development. I know on the fire side, they're definitely looking at kind of optimization processes in that space as well. But I think it's definitely on the cards, but we've not seen any kind of direct output from those kind of PPE. So I think they're a little bit behind maybe what they're doing on the kind of atmosphere side. But yeah, really good point.
To follow up to Peter Jen's question, I mean, I think it's danger in treating IPCC AR6 or the Sherwood et al. 2020 as the absolute truth in tuning your model, because if every GCM decides to tune to be in the very likely range, that's exactly what you'll get. And you'll no longer be using models to predict ECS. And also the point about whether the fault is in the atmosphere, I believe the NOR-ESM, they found ECS was quite sensitive to the ocean. So without fully understanding, if you try to follow what you think is the absolute truth, it may be dangerous. And there have been recent papers questioning whether some of the assumptions in Sherwood et al. Were exactly right, so it could change.
Right, okay, yeah, that's interesting. So yeah, I mean, I agree with you in many respects. This isn't an ideal situation. I think it's a case of sometimes you're damned if you do and you're damned if you don't. So you get ridiculed maybe for being a high ECS model, and people want to throw your model out of the pack. So I think I think as long as we're transparent in what we want to do, I agree with you. There's a risk that CMIP 7 might be full of models that have kind of adopted this approach. But I like the idea of having ensembles of ECSs in there. I think we should, and I think we really need to be careful of how we kind of communicate in terms of what we're doing. In terms of the coupled and the role of the ocean, I kind of agree. We do definitely see a systematic difference between the feedback parameter in the using kind of AMIP plus 4K setup to when we run the fully coupled 4 times CO2. And that's something that's intriguing us, and we're trying to, definitely try and learn from that in the future. Obviously, we just can't afford to run fully coupled PPEs currently, but definitely there's, I agree with you, there's a role of the coupled system in there as well.
One last question, hopefully short. Do you have a threshold, CO2 concentration error that might dictate whether or not you're going to run in all the emissions-driven simulations?
That's a good question. I don't know the answer to that. I guess they do have, normally kind of a threshold in terms of, carbon uptake and fluxes. But I haven't, don't know the answer to that one actually. I have to.
We don't have an official one, at least. Thank you.
Great.
Thank you. Okay, so our next plenary speaker is Marie Rugenstein. She is an assistant professor in the Department of Atmospheric Science at CSU, Colorado State. She got her PhD from ETH in Zurich in 2017, and her research focuses on large-scale interactions between the atmosphere and the ocean and implications for climate change. I learned about her work at the March Clivar workshop on confronting Earth system model trends with observations, the good, the bad, and the ugly, and I just love the title of that workshop so much I wanted to be able to say it in this meeting. And I was really inspired by her presentation, so that's why I invited her here today to talk about some of the work she's doing in this realm of comparing Earth system model trends to observed trends. So one highlight I noted in her CV is that she has earned 2 awards for excellence in reviewing, which I think is excessive. Thank you.
Thank you. Okay, just to get the title right, I actually borrowed it from the workshop organizers. I didn't come up with this. So Isla Simpson is here and Tiffany Shaw is probably not here. They run this really nice workshop in March here, US Clivar sponsored, with 200 folks from all over the world, 120 here in a bad snowstorm. And it was a really nice workshop bringing together very different fields, and the overarching question was, can we, or the hypothesis is, now we are in an era where we can actually confront the climate models with real trends potentially forced and see how well they are doing. So I kept the title. And they are working on this paper, review paper, so if you're interested, keep looking out for it. I would like to first I would like to highlight folks from my group, Dirk Olandschenk, Shreya Dahme, Mark Alessi, and Zene van Loon, who contributed to what I will be showing. And I will stick with the general theme of trends and how well can the models simulate these observed trends. I hope I have enough time, and if I do so, I will for sure start with the top of the atmosphere radiation, which is only observable over the last 20 years or so, and the surface temperature trends and the pattern effect for the last 50, 70 years. And then what does it mean that the models are bad in both of these for future projections? So let me start with the top of the atmosphere radiation, but actually with the surface temperature over the time for which we have good radiation observations. So what is shown here and what I will be showing over the next couple of slides are large ensembles. And the question is, do the observations fall within the range of the large ensembles? I don't care whether the trend is forced or not. I think we don't know anyways. And and it's a very low bar to ask observations, please be comfortably within the range of the large ensembles. So here are the observations, the black line. This is the surface temperature trend global mean. The next couple of slides will be global mean only. And then there's a bunch of these large initial condition ensembles, and every single dot is one realization of the model for these 23-ish years. So they have a lot of chances to get things right, and actually all of the models, except the CAN-ESM ones, do get a couple of realization correct. So we are good. This is the good. Now comes the bad. This is radiation, top of the atmosphere, global mean, something very, very basic, right? These are the observations. Do you see the uncertainty bar? It's very thin. It's here. It ends here. So there's like 4 realizations of all these initial conditions which within the uncertainty bar. And you can discuss the uncertainty, but I think the main point is that all the models agree in the sign of the bias, right? Usually for things like clouds or precipitation, which we know we are not good at, the models are around the truth, and there's a couple of models doing too much in one direction and a couple of models doing too much in the other direction. And here they all agree in substantial, more than half an underestimation of that observed trend. So that's the bad, and now comes the ugly, which is you divide one by the other to assess radiative feedbacks. So let's first step back, and I walk you through this. I just sketch out what's spelled out in this paper. We look at where these problems come from spatially and allow the models to get the surface temperature trend correct. This is this axis here. 0 would be that in one location, our surface temperature is correct by chance or by the right reason. We don't differentiate. And then we say, if the surface temperature trend is correct, please TOA be also correct. Or you have a chance to be correct because you have 100 ensemble members of a model, right? You want a couple of them to be correct. So this is what you get. Every single dot is still one ensemble member. We don't really care about the general behavior. We just want the models to fall around 0, 0, right? And this is one location where the observed trends down here are the strongest. And this blob, so the fact that this a line here crosses below 0 means that even though the models occasionally get the surface temperature trends correct, they still do the top of the atmosphere radiation in that box wrong. So that's our new kind of bias measure, and it's really, it doesn't matter how exactly you measure this. If a model gets the surface somewhere right, the top of the atmosphere is still off. This could be because the forcing is wrong, because the local physics are wrong, right? The translation of the surface temperature to the top of the atmosphere doesn't need to be well connected, depending where you are, or the surface temperature patterns are wrong. So the top of the atmosphere in my box is wrong. So to jump ahead, we develop a measure of this bias. So this is the degree to which a model cannot reproduce the top of the atmosphere correctly for a correct given. It had the chance with 40 or 100 members to get the surface right, it's still off. So 0 is good and minus is bad. And now this is the radiative feedback, which is, and I don't want to go into too much depth, it's the radiative imbalance, which basically is what the satellites see, minus the forcing divided by the surface temperature. And here's what you get. Again, each single point is an ensemble member. So this one would be crazy. It's positive. It would run away. So this basically tells you that over these 23 years, you cannot really regress too much. It's kind of random. Models with very low bias or no bias of this coupling tend to have more stabilizing feedbacks, which would imply a lower climate sensitivity. And models with a large bias tend to have very, very little stabilizing radiative feedbacks, so close to zero. And now the interesting thing is that if you would use the observed radiative fluxes and temperatures, you could constrain and say, the unstabilizing, the not so stabilizing models are better. And if you use the bias measure, you say the more stabilizing models are better. So this basically is the ugly, that 23 years is just too short to even estimate that one number from observations. There's some estimates about this. Probably it needs 40 plus, maybe 50, 60 years to beat the noise in these regressions. So feedbacks are still ugly and we have to wait or come up with other measures to constrain them. So this would imply that a model with a lower climate sensitivity is better able to reproduce that coupling in the past. Doesn't mean that climate sensitivity is low because it changes in time and depends on the spatial patterns of the surface warming. I will end this talk discussing how this relates to ocean heat uptake, because I think it points towards either the forcing being really wrong or the ocean heat uptake being wrong. And there is a core problem here that the surface temperature is okay-ish and the top of the atmosphere is so off. This means we need a compensating bias. If the energy balance is so off, you cannot get the surface right if there isn't an exactly compensating bias. So that's actually really worrisome. Okay, next one is surface temperature trends. So I switch gears a little bit because now we have better observations farther back in time. And what people discuss a lot is trends since the 80s towards today, and you see this cooling in the Eastern Pacific and in the Southern Ocean, and the big discussion is that models cannot reproduce this. And there is almost a little fight in the literature. It's actually fun to follow with the two camps, and is this internal variability or not? Because we don't actually understand the physics of this pattern yet. We do not understand the timescales of the force response in the Pacific, which is kind of embarrassing. So we try to take a little more systematic look at these trend problems. And what I will be showing is two triangles systematically going through all possible trends. The horizontal axis will be the start year, starting 1950, and then the vertical axis will be the end year of a trend. And the minimum trend I show here is 20 years. So starting in 1950, ending in 1970 would be up here. And this would make the trends longer and longer. This one in the corner would be 1950 through 2020. This is what the observations look like. And what I show here is the gradient in the tropical Pacific, east minus west. And this is because it measures a lot of dynamics, which I won't go into. It's the east. You can do the same for the Eastern Pacific. 80, 90% of these features come from this Eastern Pacific box. And what is interesting is we have these long-term negative trends, but they are very slightly, they're basically zero, little positive, negative. So east minus west, east is cooler than the west. But here's the interesting thing. Through time, there's these decadal swings, and this is basically PDO, IPO, that the gradient was stronger around anything you capture the 60s, and then it got positive around the 80s, and then negative, and this is what people discuss now. And this is important, recently it gets positive. The East Pacific is warming, it's not cooling anymore since the mid-90s. And here's what the models do. Same thing, now we have 15 large initial condition ensembles, and again, the only thing they have to do is capture the observations in the distribution. I don't care where. It should just be somewhere in the distribution, please. We have 15 models, and it's kind of arbitrary where you say it's in the distribution. I just say for this purpose, it's 2 sigma. And they are actually not really normally distributed. It doesn't matter what threshold you use. Let's say Whenever I show a color, it means it's within the distribution, so we are okay. Dark means 15 models do not have the observations within their distribution. So dark is bad. And they're pretty bad. So all these long-term, weekly negative trends, none of the 15 large initial condition ensembles captures this. Period. Especially so in this recent strengthening of the gradient, but also in the weakening of the gradient. This is 50% of the models. It's a little subtle here, but they don't get it. And then when the gradient was strong again, around the 60s, also basically none of the models, or 80% of the models, didn't get it. And this is actually very nicely consolidated the discussion in the literature, because these different letters here are different papers arguing, oh, it's internal variability, the models can get it, and no, it's none of the models can get it, but we only use one model and whatnot. So it really depends where you sample this, and there's large, long time scales where the models are able to capture the observations. Okay, again here, since the mid-90s, we are kind of good, however, potentially for the wrong reason. So since the mid-90s, the Eastern Pacific, actually also the Southern Ocean is warming, and the models do get it, but potentially because they already want the forced response and warm since already some decades, and who knows what the observations might, it might be PDO, IPO, it might be the slow emergence of the forced response, we don't know. So now, the interesting thing is that the models who do not get these swings are the hot models from CMIP 6. I went into this with the hypothesis that the hot models always want their East Pacific to be warm already, because they want the forced signal they already show the forced signal in the 80s, let's say, and the forced response in the tropical Pacific is more, in 95% of the models more warming in the east than the west. However, it turns out that the hot models are unable to reproduce swings in the Pacific. They're not hot all the time. They're basically flat, more flat than other models all the time. So this shows you where in the distribution, in terms of standard deviation, the observations lay within the model. So this here would be GFDL, and the observations for this time scale here, where there was a strengthening of the gradient, were 1.5 standard deviation of the mean. Everything would be much nicer if CSM2 wasn't there, and we didn't figure out why. But it's great, it's, the observations fall within that range, but it's so variable, it kind of captures everything. So this is an example of a strengthening of the gradient, and the models which are hot for these models, the observations are much, much farther outside the distribution period than the models which capture it. So 4 is large, right? We are far away. Okay, now the interesting thing is that the opposite is true for a period in which the gradient was positive, in which the east was warmer than the west. That also the hot models do capture, are less able to capture the strengthening of the gradient or the weakening of the gradient. So that potentially this could lead us to some fundamental issue in why the hot models are what they're doing. My hypothesis is it's a mismatch between the SST, the sensitivity of the low cloud decks in the east to the local surface temperature versus the free troposphere induced lower tropospheric stability. But that's just a hypothesis. And there's still a lot discussion going on. It's kind of fun to follow this. Okay, surface. Can I do the future? Lost my time. Yeah, good. So what does both of this mean for the future? The fact that all the models we looked at don't get the top of the atmosphere radiative flux trends correct, and most of them, for especially longer time scales, don't get the surface temperature patterns correct. So we switch back to a feedback perspective now, and what I'm currently doing in my group is trying to get rid of climate models as much as possible. We still rely on them, but we want to strip down the parts we do not trust and see how far we can get, even doing projections with using the models for what we trust them. I'm curious for your feedback. So what I showed you before is the feedback over the observed period, 23 years. We know that we can take climate models and run them in an AMIP mode with observed sea surface temperature pattern, and they actually agree. All these lines here are different climate models. This is the same feedback parameter, so the more negative, the better for the world, the more stabilizing. That they wiggled around and got more and more negative over the last couple of decades, and now there's a little indication that they get more positive. I put in this black snapshot here, which is this situation for which we actually have observations. So the problem is we cannot verify this because we don't have radiation going back before the year 2000. But at least the climate models agree that they wiggle around, and they're much more negative for the pattern we observed over the last decades. Then the blue lines are the Gregory method, what we have seen before in the talk. It's like the standard way of estimating climate sensitivity. So in a sense, we were lucky over the last decades because the sea surface temperature pattern kept us much more stabilizing and cold than we could have been with a different pattern. And who knows how forced that pattern was, right? So the danger is if the pattern switches that our radiative feedbacks shoot through the roof, which I will show now might become the case. So the question is, how do we go forward from where we are? So currently we are here or here, depends on your timing. Models do agree that if you force them with a step forcing of CO2, abrupt 4 times, 2 times, doesn't matter. Same feedback parameter here. These are different models. This is now time, logarithmic time, and all models agree that initially they're more stable, and then they get less and less stable over time. This is being shown that this is due to the pattern effect. It's also a little bit due to radiative feedbacks becoming temperature dependent. But this only kicks in when the global warming is above 3 or 4 degrees. So how do we go from where we are to, do we actually trust the timing of the models here? How do we go here up? So in my group we developed 2 methods how to deal with this. One is convolutional neural networks, which I won't explain, and the other is Green's functions, which I also won't explain. I'm around the whole day, really happy to go into the nitty-gritty details, but I don't want to bother everyone with the technicalities. In very short, this approach is nonlinear. We train it on maps of surface temperature variability. All we train this network on is variations of global maps of variability, which is something, and we use models for this, which is something we could trust the models. There's issues with this, but we strip down the models of the forced response pattern, any forcing issue, right? It's as much stripped down of a model as you can get, I think. So we say from just that variability, predict the global mean radiation. And it works astonishingly well. So I'll show one example of an application of this, which is we train our network based on internal variability using a couple of models, these large initial condition ensembles, and then doing basically the same as these full GCMs, which took months to run, just with our network, which runs in a second, once being trained. And we apply different observed SST data sets to that network. And what we get out is this radiative feedback that is exactly the same as here. Some products do these swings in the middle of the century, and then they go down, so they go down here. And then we can do it a little longer now because it's so fast. Since the mid-90s, depends a bit on how you do this regression, timescales. This is the center of the 30-year window. So since the mid-90s, they shoot up again. Same timing as the Southern Ocean warming and the East Pacific warming. So this would indicate that based on the observed temperature pattern, we are already moving towards more positive radiative feedbacks. This is still looking back. Now we use this other method, looking forward. This takes a climate model. It's very expensive to run. Fixes the SST everywhere and perturbs just one location for SSTs, and then lets the model run to equilibrium, builds this very fancy matrix of the dependencies of any output variable of the model, the dependency on the sea surface temperature pattern. It's a linear approach, and it's really trusting the climate model's atmosphere, not the ocean at all, not the coupling. So we strip that down, not the forcing. It's really just if we have a local warming here, we trust the atmospheric response. And what we can do is, once we have this fancy Jacobian, which is basically a climate model in itself, a linearized version of that climate model, we can convolve it with any SST pattern. So what we do here is, again, radiative feedback terms. I apologize because most people probably don't think in that term. But again, negative is stabilizing, less negative is less stabilizing. We hope not to get over 0. The gray line here in the background is what the coupled model wants to do. So it already shows this fact that they get, through time, less and less stabilizing. This almost all models agree. So that's what the model wants to do. If we apply observed sea surface temperature pattern, we get the atmospheric model to be more and more stabilizing through time. This is just this last bit here. And now we do something. This is inspired by Ted Shepard's storyline approach. We make up SST patterns because we don't trust the climate models' SST patterns. If they didn't get them right in the last 40 years, why would they get them right in the next 40 years? This is the thinking. So we say we still know quite a bit about the physics. We know where we are now, and we can just make up as many patterns as we want to and convolve them with our stripped down versions of climate models, right? So one assumption, this black line here would be we keep in the pattern we observe currently. Why not, right? Assume that's the force response, and we just keep in it till the end of the century. This means the radiative feedbacks don't change because they only change with the change of a pattern. And in terms of temperature, this is a complicated figure, but now we translate this feedback back to temperature. This is surface temperature through time. And this would follow this dashed line under an RCP 8.5 scenario. It doesn't really matter. The point is, the gray line is where the coupled model wants to be. Just through changing the pattern, we can, at the end of the century, keep the model 1.5 degrees lower than it wants to be coupled, solely by forcing that temperature pattern. This would be great, right? This would mean that the radiative feedbacks just stay stable and hence drag down the surface temperature. It's quite unlikely, though. Why would we stay in that pattern, right? Because we already see the East Pacific switching. So alternative versions, these are storylines, right? We just say this is plausible. You can buy it or not. Tell me a better pattern, right? And I plug it in. This one starts from where we are currently and says we trust the model at the end of the century or at the middle of the century, and say we catch up from where we are currently to where the model wants to be. this is putting some trust in the climate models, right? We say maybe the force response is right, it just didn't come out recently because the internal variability is off. Or you can totally give up the climate models and just make up your own physically argued SST patterns. So if we assume the model is right in the future and we catch up to the model, this is what the feedbacks do based on these patterns we put in. This is also a little subtle here. By construction, we catch up to where the coupled model wants to be. But this means that in the next couple of decades, we have warming rates which are unseen by the climate models, because the climate models currently are already in the wrong state, and we want them to be in this state, which we are in, right? So this is, I love bets. If somebody wants to bet me, next 30 years, based on this can be overruled by tons of other things. We have higher warming rates than any climate model projects. So this would be what the coupled model wants to do. And the pink line here would be if we start on where we are and trust the model at some point in the future. Okay, that's it. Summary. The observed top of the atmosphere radiation is ugly. No, it's bad. Feedbacks are ugly, temperature's good, which is a problem because if one is off, the other also has to be off in terms of energy balance terms. The observed surface pattern evolution is good in some regions and sometimes, and is for sure off in all of the models. This is scary, right? We have hundreds of ensemble simulations. They have a lot of chances to be even right for wrong reasons, and they are not. If they stick in that state of being wrong in both, this has serious implications for our trustworthiness of the projections. And I think the implications are that, so climate models have likely two positive feedbacks which balance an either too weak forcing. There's some indications of this, that just what we plug in is already wrong, then why would we expect the radiation to be right? However, truly we won't know this. This is impossible to know from observations, right? Or they balance a too strong ocean heat uptake with a too strong atmospheric feedbacks. And in the observations, either we have a stronger forcing than we currently think and put into the models, or we have a much weaker ocean heat uptake, what we know from the models, balanced by rather strong restorative, rather negative radiative feedback. So the real world's feedbacks are more stabilizing than what we see in the models. Happy to take questions or suggestions or comments.
Thanks, Maria. This is a great talk, even if it is a little bit unsettling. You know, I'm kind of Peter Gent's question to the last speaker and the issue of using emulators to kind of, you know, tune the climate sensitivity of models. I guess the problem, it seems like you've raised kind of a concern with that, which is that maybe what's wrong with the models is not that, you know, the physics, you know, the properties of the clouds, the shininess of the cirrus, or, you know, those kinds of things are what needs to be tuned. Maybe what's really wrong with the models, if you think that their climate sensitivity is actually wrong, is this pattern effects. You know, so that if I wanted to tune a model to get the right climate sensitivity in present day climate, I would have to tune the specific SST pattern rather than any physics of the intrinsic physics of the parameterization schemes. Am I getting that right?
Mm-hmm. Yeah, I think it's, okay, I'm very opinionated about the hot models. I would just keep them until we understand them. I don't get why we have to converge to that 3-degree climate sensitivity. We do not know climate sensitivity, period. Yes, so when you try to tune to the observations, which came with a certain pattern, and to ECS should be 3, I think it just doesn't make sense. You should give up ECS and just try to get the past correct and understand the physics of how that pattern, which will very likely change, relates to ECS. And then this is what ECS is. Like, we do not know, the sampling the future is kind of, seems odd to me. Does it make sense? Especially, I think it's very interesting how ECS evolved through the IPCC reports in terms of we rely very heavily on the models. Two, we take paleo estimates more serious. The pattern effect, if you have your PDF of ECS, the pattern effect totally unconstrained the upper bound. Basically, based on what happened in the past couple of decades, we cannot say anything about the upper bound of ECS. That's the big problem. And I would say, just let's be honest and say, based on the observations we have, we do not know. And then actually what's interesting is what brings it down is the last glacial maximum. So I think this is where we should be heading, to understand what really sets the bounds of ECS on physical reasons and not push the models to be in there. And then it might be embarrassing to say, yes, they are hot, but then we should detrust projections, right? But why do we trust projections anyways?
So I think of lambda as a property of a quasi-equilibrium system, and for the atmosphere, the timescales are short, but the deep ocean, they're long. So is it even meaningful to define lambda on a 30-year timescale? Shouldn't it be multi-centennial, and that'll be consistent with looking at LGM as a true measure of these things. But lambda, is it meaningful to look at it on 30
I think it is if you stick with lambda. That's the core thing. And this is why I think the community moves from ECS towards feedbacks, because radiative feedbacks change through time dependent on the SST pattern. And they do make sense on a 30-year timescale. But translating this number to climate sensitivity, that's the big step. And this, the feedback over the last 30 years has basically nothing to do with climate sensitivity. And this was the big realization of the last 5 to 10 years, and is the core of the pattern effect research, which I didn't introduce at all.
Thank you very much. Really, really good and inspiring, and like you said, also a little scary. All right, so do we have Veronica online? Veronica, you try just saying a word, and so we can see if we can hear you before I introduce you. Great, excellent, thank you. So I will introduce Veronica. She intended to be here, and for family reasons, she was not able to attend at the last minute, but she has very heroically offered to give her presentation remotely under some difficult circumstances. So first of all, I think Veronica Eyring probably needs no introduction to most of us, certainly any of us who've been in the field for more than a few years, but for the early career scientists here in the room. She is the head of the Earth System Model Evaluation Analysis Department at the German Aerospace Center Institute of Atmospheric Physics, and she's professor of climate modeling at the University of Bremen. And famously, she was the chair of the CMIP panel for CMIP 6, which was a massive and really challenging effort, obviously, and it was really instrumental, not just in leading the whole effort, but instrumental in its design. I was there in the meeting when she and others came up with it. She's served as a lead author on several IPCC reports, and more recently, and what she's going to talk about today, she's become really interested in is pursuing the potential of hybrid modeling, bringing machine learning combined with physics to accelerate advances in ESMs, and that's what she's going to talk about with us today. So thank you, Veronica, for being here, and I'll turn it over to you.
Yes, we can.
Thank you, Veronica. And questions for Veronica or comments? Eric. One moment, he's coming to the mic.
Thanks. That's very interesting. You know, we always kind of think about fitness for purpose with these kinds of models, and you know, maybe one challenge that I was thinking about is, you know, there's some domain of applicability in terms of when you kind of go outside of the training set sufficiently, that the way that the machine learned version of the model behaves is not the way that the physical model that you use to train it would behave. And you know, I'm thinking particularly, you know, when you show those formulas, you know, you have clouds, and they're one of the sort of terms in the equation for the clouds is the temperature, and then presumably, you know, if global mean temperature changes quite a bit, then you would have to worry that maybe that formula isn't quite as good as it used to be. I think there's also specific humidity in there. So what is the kind of, you know, what is your thinking about, you know, how broadly you can apply these kinds of models given the training sets and the way they're constructed?
One more question.
Hi, Veronica. Thank you. I'm curious how you think, or what you think the best approach will be for solving stability challenges for these hybrid machine learning models. Great, thank you.
Great, thank you, Veronica, and thanks to all of our plenary speakers this morning. I think really thought-provoking set of presentations. So let's just thank everybody again there. We will be breaking for lunch and then return for working group sessions on the land, atmosphere, and ocean. I don't know which room is which, just have to figure that out. This room will be split up into three. Just so you know, some of the presentations are already getting posted online. I think some of the presentations this morning, in case you want to review what was said. So yeah, lunchtime, we have just over an hour and 5 minutes for lunch. You can go here and then outside, hopefully, if it doesn't start to rain, and thanks.
Hey, how are you?
Hey, I'm doing well. How are you?
Alrighty, I think we'll get started here. So welcome to the Atmosphere Model Working Group session here at the CESM summer meeting. So on behalf of the external co-chairs who unfortunately can't be here today, Kevin Reed from Stony Brook and Hui Van from PNL, and our faithful liaison, Cecile Hainé, welcome to this meeting. During the winter AMWG, we went through all the glory details of what we're trying to put into our CMIP7 model, and for the atmosphere that will be CAM7. And in consultation with the external co-chairs, we agreed that the summer meeting here should really focus on the community input, because a lot of you only come here during the summers. We want to give as many people the speaking slot as possible, rather than only the model developers talking about all the new stuff in the model. But if you want to know what's in CAM7, every new thing that's going in, there was a presentation on during the winter AMWG. Please remember, we have a group photo at the PM meeting, so please don't run away. Go out here, follow the instructions for the group photo. And for the speakers, you have 15-minute slots, so around 12-ish minutes, I'll give you a little sign that it's time to wrap up. Online participants, you can ask questions in the chat and in the Zoom that you're on, and in person, you just walk up to the If anything comes up after the presentation that you have questions about, there's also a Slido link that you can use. So with that, I'll give over the mic to Kyle.
Okay. Okay, cool. All right, thank you, Peter. So the main goal of this talk today is just to give an overview of some of the work we're doing currently at Penn State in support of Momentum Flux CPT. And this is something that we just started a few months ago, and we're still in the early stages of developing exactly the methodology we want to use. So if anyone has any comments or suggestions, I'd be happy to hear them. But the main question we're trying to answer here is, how does Club's new prognostic momentum flux formulation influence aspects of the mean climate in CAM6? So just as an overview, this is the new prognostic momentum flux formulation that replaces the old diagnostic formulation I'll mention in a second. But it's essentially a time tendency equation for vertical momentum flux, and it has various terms in here, and I'll step through them quickly. We have different advection terms, we have turbulent production terms, buoyant production terms, and then certain pressure terms that are added in, for example, this return to isotropy adjustment term. And this all replaces the prior diagnostic A diffusivity formulation that was essentially a product of this diffusivity coefficient and then wind shear. And the main goal of adding prognostic momentum flux is that it is meant to better account for counter-gradient fluxes that we see in the atmosphere. The old diagnostic A diffusivity formulation wasn't able to account for those. And the reason why this is important is because various studies within the momentum flux CPT have shown that counter-gradient fluxes exist in our atmosphere, for example, in shallow cumulus regions. So this here is an example from Vince Larson's 2019 paper over the BOMEX region using a large eddy simulation, and the red that we see there, those are areas where counter-gradient or up-gradient fluxes exist, and the prognostic momentum flux formulation will hopefully be able to account for those better. And also, one of my former group mates at Penn State, Skylar Gropp, he also found that these occur in the BOMEX region as well. And preliminary analysis by myself and also Ben Stevens has shown that when we implement the prognostic momentum flux formulation, we are able to uncover areas where counter-gradient fluxes do exist. So essentially here, the greens are areas where we have higher occurrences of counter-gradient fluxes in the atmosphere. And again, this is quite preliminary. So our main question is, how does implementing prognostic momentum flux influence the general circulation in CAM6? So to do this, we're starting out with a very simple scenario where we have these 10-year aquaplanet simulations. And I just pulled club settings from a recent tag that, with my own personal investigation, found that this produced a realistic baseline climate. But again, this is just
our initial stab at a baseline, and likely we will fine-tune whatever parameter setting. And we run one simulation with prognostic momentum flux turned on, and then the other with it turned off, so with the legacy diagnostic. And then we compare the simulation for years 2 through 10. I want to be very clear here that we are at the very early stages of tackling this question, and currently we're not focused specifically on tuning or bias reduction. Mainly, we just want to see how a reasonable baseline CAM6 configuration responds to adding prognostic momentum flux. First, I'll show momentum flux and effective A diffusivity average over the tropics for the two simulations. So in red, this is the profile for the diagnostic A diffusivity formulation, and then in blue, this is the prognostic formulation. One thing we notice is that the atmosphere becomes less diffusive, and here on the right, I'm talking about in an vertically integrated sense, we get a reduction in eddy diffusivity, and we also get a reduction in momentum flux. Now, with the old diagnostic formulation, the red curve could be adjusted by tuning the CK10 parameter, which in this baseline configuration is set to 0.5. And this is essentially a multiplier on the diffusivity. If we want to reduce the diffusivity profile, we could reduce that coefficient. If we want to increase it, we could increase the coefficient. But without prognostic momentum flux, with the eddy diffusivity formulation, CK10 was the primary mechanism for diffusivity. Whereas with the new prognostic formulation, there are various tunable coefficients. I also want to note here that we do get quite a difference in the shape of the profile for the effective A diffusivity. Plots here showing the change in the circulation. So this is these are zonally average cross sections of, on the top, zonal wind, and on the bottom, meridional wind. On the left here, this is the average cross section of zonal wind. For the diagnostic A diffusivity formulation in the middle, this is for prognostic, and then this is the difference here. One thing we notice that for the zonal wind, we get a decreased magnitude of the westerly jet and the low-level easterlies when we implement prognostic momentum flux. And then for meridional wind, the core of low-level equatorward flow, which is shown in the purple there, these purples get a bit deeper. So we're actually getting a strengthening and a contraction downward and equatorward when we reduce the diffusivity in the boundary layer. And I'll note that studies that we've done looking at the tropical cyclone boundary layer have found a similar response in radial inflow, essentially a contraction inward and downward when we reduce diffusivity in the boundary layer. And we also see that the poleward flow aloft, the greens there, get a little bit stronger and also move a little bit closer to the equator. So now looking at vertical velocities, this is omega and then the mass-weighted stream function. So the purples there near the equator imply upward motion, and what we see is that the upward motion strengthens and moves equatorward. Those purples get a little bit deeper in the middle, and they also get closer to the equator. And you can see that with the difference plot right here. And we also see that the downward motion in the subtropics tends to weaken a little bit. So those greens in the middle are a little bit weaker compared to those on the left when we add prognostic momentum flux. And then we also seem to get a similar story with the stream function. So the stream function's a little bit weaker here in the middle, implying that we might get a bit of a weakening of the Hadley circulation and also an equatorward contraction, which you can see here also in this difference plot. Now, if we look at things like sea level pressure and low level winds, we also see a response. So this is on the top, effective A diffusivity for sea level pressure, prognostic momentum flux in the middle, and then the difference is at the bottom. And what we note is that there is a reduced pressure gradient over the mid-latitude. So the climatological high has these blues here, so we're getting lower pressures there, and then for the climatological low, we're getting higher pressures, implying that we're getting a reduction in the pressure gradient over this region. And we see a similar response when we look at the bottom model level wind speed and also surface wind stress. Over that mid-latitudes region, we're getting these blues here, implying that we're getting weaker surface winds and also lower stress, which is consistent with this reduced pressure gradient. Now, if we look at clouds, we see an enhancement of the clouds over the equator, these reds here, when we add prognostic momentum flux. And we get a similar story when we look at shortwave cloud forcing, just the opposite sign. And then when we look at total precipitation, so large-scale precipitation plus convective precipitation, might be faint here, but we also do see an increase in precipitation over the equator here, and then decreases on the flanks. Fairly consistent with this idea of we're getting increased upward motions near the equator. Perhaps we're getting more convergence, more precipitation occurring, and more cloud cover, which is something we want to explore further. But I do want to, again, reemphasize that this work is in the early stages, and one critical thing to remember here is that the responses I'm showing here, that's all depending on what the baseline configuration is for the diagnostic formulation. Namely, what is that value of CK10 that we're putting in? Here, we were putting in a value of 0.5, meaning that we're producing a diffusive atmosphere. But if we had a baseline simulation that was maybe a little bit weaker with the diffusivity, those responses might not exactly be the same. And I can illustrate that here. So this is the same plot I showed before, but now this green profile here is that same configuration, but with CK10 reduced to 0.25. And what we see here is that we get this reduction in vertically integrated eddy diffusivity that's similar to what we see with the prognostic momentum flux. And really, we're trying to tease out several factors here. So first, we're getting a reduction in diffusivity overall, but we're also getting a change in the shape of the profile when we add prognostic momentum flux, namely this blue spike here. And I'll note that it's hard with just tuning CK10 alone to reproduce that exact shape for the blue curve, which makes things a little bit more challenging. But really, what are the contributions of the reduced diffusivity versus the change in the shape of the profile versus the accounting for of countergradient fluxes? All of those factors we're trying to really tease out, and we're still trying to get our heads around what the best methodology for approaching this really is. And I'll quickly show here that when we just reduce CK10 from 0.5 to 0.25, so essentially we're reducing the diffusivity, we get a very similar response that we did when we were adding prognostic momentum flux. Namely, we get strengthened meridional winds and a downward and equatorward contraction. Namely, that when we're reducing CK10, we essentially are getting the same response as to when we were adding prognostic momentum flux in this one particular situation. And then we also get these strengthened upward motions, similar to what I showed before. So I'll just go through a summary of my main points here. So we're finding that adding prognostic momentum flux, in particular for this baseline configuration, we are seeing that there is a response in the general circulation. And we're seeing that potentially the Hadley circulation is weakening. We're getting changes in meridional flow, sea level pressure, things like that, as I mentioned there. And then the main questions we're trying to answer going forward are, what are the physical mechanisms driving these responses? What's the relationship between reduced diffusivity and the changes in the general circulation? There's a lot of literature out there, and it's something we're going to try and understand over the next couple of months. And then also, as I mentioned in the last slide, what is the interplay between reducing diffusivity and the changing of the shape of the profile, and what are the countergradient fluxes doing when we add them in with prognostic momentum flux? So I just wanted to thank our partners. Again, this is part of the Momentum Flux CPT that's been funding my PhD work, and it's been going on for a number of years now. I just want to thank all of my collaborators with that. If you have any questions, you can contact me there. And I'll just leave my main takeaways up here. And if anyone has any questions or suggestions, I'd be happy to take them. Thanks.
Questions?
Two questions. First one is, how does it affect the runtime? And the second one is, have you done any tests with short-range forecasts?
So I've done a lot of tests for short-range forecasts for like the tuning, but not specifically for just adding prognostic momentum flux versus no. So that's a good suggestion, something we could look at a little bit more. In terms of the runtime, I, from my anecdotal experience, haven't seen really much of a change in the runtime. It seemed to be about the same amount of runtime. Somebody like Vince maybe would be able to answer that question in a little more detail, but I didn't see any major like computational expense difference, at least for these aquaplanet simulations.
I know your title is mean climate, but I'm curious if you've looked at like a probability distribution of precipitation, for example, and see how that's impacted by.
I have not yet, but that is something that's on our list. That's a very good suggestion. Again, so we're in the pretty early stages of this, just looking at some of these initial diagnostics, but something like that is something we'd definitely be interested in looking at going forward in the next couple of months.
On to the next speaker, which is Ben Stevens, and he's also going to talk about club.
Okay. Hi, I'm Ben Stevens. I'm a project scientist here at NCAR. Most of my time here at NCAR is spent on the Momentum CPT that Kyle was just discussing, but thought I would talk about something a little different. A couple of years ago, I was a postdoc at UWM with Vince Larson, and we did some work trying to parameterize some new terms in the club prognostic equations. This is work that kind of got put on the back burner for a little while, but we'd like to finish it up and see it through to publication. So the last few weeks I've been kind of digging back into it. Forgive me if I'm a little rusty, if you have questions, and I'm not quite sure. I've been trying to refresh my memory about it. But yeah, I would like to thank Vince and Dmitry Mironov, who is at the German Weather Service. He's done a lot of work in turbulence theory. And, oh, and I do also want to mention, this mentions third order turbulence equations, but I'm mostly just going to restrict the talk to the WP2 equation, the W prime squared equation, just to save time. Club is based on, largely on the Navier-Stokes equation. What you see here on the left here is the sort of full tensor expression of the pressure term in the Reynolds stress equation. So this is kind of complicated, but when you specialize to just the W prime squared component, in other words, I and J both equal 3, this is kind of a simplified version of the equation that you get, and you can see that it has these two pressure terms in it, pressure transport and pressure scrambling. There's a body of literature on how to parameterize the pressure scrambling term that goes back decades, and Club uses those closures. But the pressure transport term is typically neglected, and it's called a transport term because it has a derivative in front of it, and so if you integrate it, the idea is that it doesn't really act as a source or sink for W prime squared, but it really moves W prime squared around. I am not offhand aware of this term having actually been explicitly modeled before. It's usually either considered to be small, so there's a Stoll 1988 textbook where it's basically, he says it's small and kind of neglects it. So I think sometimes it's folded into this term and just kind of considered to be part of the third order transport term. But we decided to try and actually model it. The reason being that it does sometimes actually show a contribution in LES budgets. So this is the BOMEX case, this is the DICOMS case. They're modeled using SAM LES. And in the BOMEX case, you can see it is kind of a small, it's a minor term, maybe with the exception of the surface. But in the DICOMS case, it's a dominant term at cloud top. And so we just decided to try modeling it in the club equations. I wanted to mention we did create these plots with our own model, but we were sort of inspired by work by Rika Heinze, and I think Dmitry Mironov was also on this work in some 2015, 2016 papers. So that's kind of where we got the idea. If you ask me how we came up with this, I'd have to probably delay and go back and try to revisit the question. But we ended up using a proposal from a paper by John Lumley in 1978, where he proposes this identification between the pressure perturbation P prime and this expression, which is, we're using the summation convention here. So this first term is a sum over the 3 components of velocity squared. And then this is basically just the TKE. So we expect this term to be large, well, when it's put into the W prime squared equation, we expect it to be large when the third and fourth order moments are large. But we know that we also need for this term to be large at other times in like stratocumulus cases. So the third and fourth order moments, we expect those to be large in like a cumulus case. But we wanted it to make a contribution in well. So we combine it with this term in club, which is an eddied diffusion term. That term had actually been added to club previously for numerical stability, but here we're sort of reinterpreting it as a kind of physical effect. So when we combine these two terms, this is basically the model that we get. This is just the W prime P prime part. To go into the equation, we need to take the derivative here. And all of this kind of applies as well to the W prime cubed equation, so that it has kind of a corresponding term that's more complicated, but the same idea is there. And this has some additional, well, it has one additional tunable parameter, this, the weight of this, what we call the Lumley term. Okay, I just want to show this quickly. These are just budgets. These are the W prime squared budgets for SAM LES for these three cases, Bomex, DICOMS, and Wengera. Kind of ignore that. We were asked by a reviewer to include a neutrally stratified case, but that's still kind of a work in progress. We had to actually add it by hand to the LES and club. So it's there in my plots, but we're still. Bottom line is, if you compare the blue lines in the top and bottom plots, I mean, there are some features that we like. They, at least in Bomex and DICOMS, they tend to kind of have an approximately correct shape. The magnitudes can be questionable. In particular, we're worried about this peak here at cloud top in the club DICOMS case, where we don't really see that big peak. Wengera has always been trickier. The term kind of gets the bump here aloft, right? But over a good portion of the column here, we get the wrong sign. So we've been trying to see what we can do about that. Tuning hasn't seemed to have alleviated the problem much. So if we do actually end up revisiting the model that we're using, this may be this may be the reason for it. Here I just thought I would emphasize that, so on the top row you're seeing these are all club results. So the blue line is just that same total transport term. The orange line is specifically the Lumley term, and then the green line is the down gradient term. So you sum the orange and green lines, you should get the blue line. So what I wanted to emphasize here is just that this kind of aligns with our expectations in the sense that the Lumley term is more dominant in a sort of more cumulus-like case, while the down gradient term is doing more of the lifting in a stratocumulus case. And again, the Wengera case is a little bit more of a mixed bag. And then on the bottom row, you're just seeing direct comparison with LES. So here again, this kind of emphasizes that in some ways the shape looks pretty good, but there's some features that we're just not yet really capturing very well yet. So we want to work on that. And then this is totally new. We had never actually done anything in CAM with these terms before. I was working at UWM and mostly doing time. But I was relieved when I ran a couple of experiments. These are relatively short, they're 2-year experiments, but they ran stably with the new terms, and I'm not really doing any kind of, I'm just basically turning the terms on so that they're functioning in CAM. And you can see we do get some patterns in the response, so it seems to make layers more stratocumulus-like a lot of the time. To try to understand why this is happening, but just a couple of quick plots. So these are profiles that are coming from the DICOMS region, and what we're seeing here is kind of the terms seem to boost WP2 and reduce WP3. In other words, they're reducing the skewness of the layer, which would make it more stratocumulus-like. So that's consistent with what we're seeing in that Latlon map that I showed you. There also seems to be a temperature inversion developing here when we increase, and this is near the ground, when we increase these parameters. In particular, it's actually the Lumley term that's causing this, although we haven't really fully understood the mechanism why that's happening yet. But yeah, I mean, the takeaway, I guess, for CAM is that it's running stably and that it's actually making a difference. So it could potentially be a knob that would be available to us. And I think, but yeah, thank you very much.
Questions? I'm going to continue along the same line. What about precipitation when you add these extra terms?
I'll look at it. Yeah, I just ran these tests last week, so I haven't actually looked at that yet, but yeah, we'll be kind of exploring it. I mean, I guess the bigger question is whether we're going to make adjustments to the formulation of these terms. If we do, then that obviously would affect the CAM results. So I think that's the first thing we're going to revisit as we try to get this published.
Stabilize, like in the other versions where this is not on, there's been some stability issues. So are these stabilizing terms in club, or?
The gradient term was initially added explicitly for numerical stability. I mean, that's the only reason really why it was originally added, is my understanding. So partially, I mean, if you fold that into these new terms, then that part of it would act as a stabilizer, I think. The other term is really coming more from just theory papers that we've found from the 70s and 80s. I don't know that it has a direct connection to stability.
Running ahead of schedule here, which is good for the next speaker. So next talk is the incarnation of João Teixeira. Here's NCAR. Is Adam Harrington.
Adam Harrington, project scientist. This talk is the quest for unified turbulence and convection parameterization, recent results from the EDMF CPT project, which is the main project that I'm funded under. So I'm here, João Teixeira was going to give this talk, but he couldn't make it. I'm happy to give it in his place. It's a multi-institutional CPT project with all the collaborators listed here. Funded by NSF and NOAA, the main goal is to reduce key biases related to PBL clouds, deep convection, and both the NCAR and the GFDL climate models. The main tool for doing this is implementing an EDMF type convection scheme into these models. And we'll be looking at things like the transition from stratocumulus to cumulus to deep convection, and also transitions that occur over land, such as the diurnal cycle, that's so notoriously difficult to resolve at coarse GCMs. João is the lead, and the PIs are listed below here, where Julio is the end. So the idea is that GCMs have split up all these processes into different modular schemes that do all these different processes. And so this is, a pretty well-known schematic from IPCC, just showing an idealized meridional slice, showing the Hadley circulation and the different types of convection that occur as you move poleward. So typically, a GCM will have a separate PBL mixing scheme, a separate shallow convection scheme, which is usually based on non-equilibrium type closures. And then a deep convection scheme, which is almost always based on quasi-convective equilibrium or other type of large-scale balance closures. and then cloud macrophysics and cloud microphysics would handle sort of the grid scale clouds. And so we're going to show results where we're going to try to merge deep convection with shallow and dry PBL using this EDMF approach. We also utilize LES for helping to understand the phenomena better and also providing targets for our parameterization. This is just two examples. This top one is some snapshots of the liquid water path in the RICO case for different domain sizes, obviously. And one thing that pops out, which is a pretty well-known result, is that the degree of convective aggregation is sensitive to your domain size. And so at these larger domains, you're going to start developing these mesoscale circulations from the wet regions to the dry regions that you can't capture in the smaller domains. We're also looking at idealized stratocumulus cases. And so this is a idealized stratocumulus case, and this is the energy budget of the LES. We impose subsidence in this LES case. And the subsidence warming is primarily confined to the cloud top of the stratocumulus. And that warming is balanced at the very cloud top in the model by radiation. But just below the cloud top, that balance switches, and the cooling term is actually going to be your turbulence or cloud top entrainment. And so that occurs at a very small vertical length scales. That's important to understand if we want to parameterize this correctly in coarser grids. So for the NCAR model, we are implemented a EDMF type approach, a glorified EDMF type approach, where we take the eddy diffusivity term to actually be club, which is, we just saw two talks on it. It's a prognostic high order closure for the PBL mixing in shallow convection together. And so it's based on a assumed double Gaussian PDF. And so club is going to do sort of the double Gaussian mixing. And then what we were going to do is augment these club with a vertically coherent explicit ensemble of mass flux plumes, which is going to show a more realistic subgrid distribution of mixing, and I'll show in a second. The MF plumes are, right now we're initializing them using surface layer subgrid PDFs. We're currently trying to relax that assumption to allow connective initiation aloft. It's based on stochastic letter entrainment, uses TKE and some other stuff. And then we feed, we actually, ClubMF solves everything together, and that we basically feed in the explicit ensemble of mass flux plumes as an explicit term to Club's 5-diagonal solver for the, which solves for the mean fields and the turbulent fluxes at the same time. And so the mean state will, that's being solved by Club is basically given here, where you have the semi-implicit Club fluxes and then our explicit mass flux terms on top of that. So this is a result in the single column model for the BOMAX case. The LES results are given by the black. We're looking at cloud liquid, and then we're looking at cloud fraction. Club, and Club MF is in the red or brown, whatever it looks like to you. And it produces, you know, more cloud condensate and larger cloud fractions, and generally is just mixing more than Club is. And the individual components, the Club term and the MF term, are broken up here, but as you see, they sum up to be greater than Club. Just take a grid point in that BOMAX case and just look at what the subgrid PDF looks like. The bivariate PDF, which is total water on the y-axis and liquid water potential temperature on the x-axis. The Club double Gaussian PDF is given in black here. It looks like a single Gaussian, but it's just two that are basically sitting right on top of each other. The LES PDF is much more broader and is skewed towards these larger QT and smaller theta L prime values. And so our MF discrete plumes are plotted on top of here, and so sort of fill out that space that was not being represented by the joint double Gaussian PDF. So I skip on a whole bunch of stuff on how I made ClubMF do deep convection. I talk about that a lot in the winter meeting, about exactly what we've done to incorporate cold pool effects and other things on the entrainment rate to make these mass flux plumes not only do Boehmx type cases, but also evolve to do deep convection. And this is what the end product looks like in an AMIP case. And so I'm just looking at profiles averaged over a West Pacific box, 120 to 160 east, 10 south, 10 north. And this is an AMIP case. I apologize, there's a lot more curves on here than there needs to be. I'm not going to explain this whole figure, but in general, the CAM7, or I should say CAM7 alpha, which is what we're comparing it to in this situation, is in dark gray, and then also blue is another version of it. And then the ClubMF is in the pink and the purples. And this is a potential temperature bias with respect to ERA5 and the humidity bias. And we tend to be a little bit closer to the 0 line. We're certainly a lot warmer than CAM7. We provide a little more shallow mixing of, a little bit more moisture in the mid-troposphere than CAM7. And the big thing that I want people to recognize is that this is the convection tendencies of moisture. And so CAM7 has this big spike right here in the mid-troposphere, and that's ZM. So ZM likes to detrain in the mid-troposphere in a very narrow range. ClubMF is detraining over a much larger vertical extent and much higher. We tend to have more high clouds in ClubMF because of this. And then down here is the convective mass fluxes. Again, blue and gray is ZM. Purple and pink is ClubMF, so we have similar magnitude mass fluxes to the current deep convection scheme in CAM7. There's a lot of things to do other than just make a convection scheme. You have to make it do all the things that ZM does in CAM, such as tracer transport. Any of the tracers that we dynamically simulate in the model, which can include water species, maybe that's a numbered concentration, cloud, liquid, cloud, ice, chemical gases, and also aerosols. And so Club transports these, ZM transports these, and so if we want ClubMF to replace ZM, we need our mass fluxes transporting these. And I basically hooked up the mass fluxes to ZM's tracer transport scheme called ConvecTran. And that's pretty efficient and seems to have pretty ideal conservation properties for a GCM. And the impact is pretty obvious what it would do, but as an example, here's a zonal mean height plot of the primary aerosol concentration in a run in ClubMF. And then here's the difference of turning on the ConvecTran transporter tracers. And obviously you have a lot more constituents aloft. So what this is not doing is it's not incorporating aerosol cloud interactions. This is just passive transport. And so that's important to include in CAM2. And so this next slide addresses hooking up our mass flux plumes to aerosol activation and nucleation schemes. But I got to tell the story, so it'll take me a minute to get there. So this is the shortwave cloud forcing, which is the same field that Ben was just showing. So blues are going to be, shortwave cloud forcing is top of the atmosphere net clear sky shortwave minus total sky shortwave. And so that gives you the residual cloud effect, which often is negative. So it has a lot of blues. And this is the series EBAF. And the mean from observation is about negative 45 watts per meter squared. CAM7's over here, or CAM7 alpha, I should say. It's a little bit cooler, but generally has all the gross features that you want. And then if we skip over down here to ClubMF, I'm at negative 40.8 watts per meter squared, and my RMSEs are really high. And if you look closely, what we're missing is we're missing a lot of reflectivity along the West Pacific and along the equator. And so in order to solve this puzzle of what am I missing, I did two things. So I did an experiment with CAM7, and I said, let's run CAM7 and turn off ZM clouds, at least as much as radiation sees them. And to my surprise, it actually thinned the clouds by about 5 watts per meter squared globally to negative 42, and you had less equatorial brightness of the clouds. And so it turns out that the ZM clouds in CAM7 are contributing a lot to equatorial cloud forcing, and that the ZM clouds are much bigger than my MF clouds. ZM clouds can go up to 80% of a grid cell. They're also highly tunable with 2 parameters. So that's one part of the story, is my MF clouds aren't as big as ZM clouds. The other part of the story is, all right, so in this run I just decided let's turn off all of the club informs the aerosol activation routines in the model using its turbulent kinetic energy, which the aerosol scheme turns into an updraft velocity and uses that to activate nucleate. If you just say, I basically set that updraft velocity to 0, and you get a world that is not very reflective at all. And so the combination of ZM clouds and cloud aerosol interactions from club are primarily responsible for cloud forcing in CAM7. And so I came up with this one in the lower right called Club MF Aero. Here I've hooked up our updraft velocities to aerosol activation and ice nucleation that is used by club. Well, I should say it's MAM4. And then I also, we parameterized these marginal convective clouds to try to increase the area of our MF clouds, at least slightly start to match what ZM was doing. And those things together sort of give us a much more realistic cloud forcing, and our RMSEs are now better than CAM7 in this case. We have shown some improvements in other fields as well. This is total precipitation rate and low cloud fractions. And in the Club MF, you can see we do improve on aspects of the solution compared to the third from the top, which is CAM7 alpha. And so I think that we've demonstrated that we've shown that CAM can sort of ingest our unified shallow PBL deep convection scheme and come up with something competitive with ZM. So that's basically it. With all this good news, why aren't we just ready to replace CM? Well, there's a lot of due diligence you have to do. These legacy convection schemes fit these GCMs like a nice old pair of shoes. And so if you want to come in and try to replace it, there's a lot of things to take into consideration. Convective momentum transport is something that ZM does that we're implementing, but I don't think that we quite understand. We're not able. That's a work in progress. And then the other big work in progress that I didn't talk about is Club MF has a pretty pretty bad diurnal cycle over LAN, owing to the way that we initialize the plumes at the surface. And so like I alluded to before, we're going to be lifting that approximation and work on potentially some non-equilibrium closures that the GFDL partners and the CPT have been working on. And so that's the current focus. So that's the status of Club MF as of now, guys. I will, that's the end of the talk, and I'll take any questions you have.
I just wanted to ask about a clarification question for your Club No ACI. Club itself produces liquid, right? So presumably in your no ACI run, you still have this, well, you might still have the same amount of quote-unquote cloud liquid, but it just has no radiative cross-section. Is that true?
Well, yes, that's part of it. There's just a ton of cloud liquid with presumably very large particle sizes,
Right.
cloud droplet sizes, that would then fall out. And so the lifetime effect.
Okay, so it could be that the liquid is also gone.
Yeah, it's auto-converting faster. And
Okay.
yeah, so if, the way, you need to do some type of activation with our model now.
Thanks.
I have a question about the deep convection you mentioned here. In the tropics, deep convection is very important because for various reasons. One of them is in terms of the mean of the equivalent potential temperature. The profile of equivalent potential temperature is very heavily influenced by deep convection. They're equal top and bottom. That requires a deep overturning within the convective layer. I'm not aware that what you're doing there actually does that very efficiently. Could you comment on that perhaps? I saw the amplitudes were quite small for the deep convection compared, for example, with ZM.
Well, I think it's clear that Club MF is more able to vertically mix deeper than ZM. I thought that was pretty clear from the plots, but
yes, I have difficulty in understanding that point because the deep convection really in the tropics is really deep convection, the really powerful ones. I totally agree with you within the the stratocumulus layers. I think what you're doing there is quite reasonable. You'll get cumulus turrets going up and transporting heat and momentum. But I'm talking about particles going from the surface right up to the tropopause nearly. And that's quite a different thing from mixing within, cumulus mixing within the stratocumulus layer. And a very good example of what you're doing, I think, is the cloud streets within trade wind cumulus. I think that's really what you're posing here, not the true deep convection.
yeah, I mean, is that not just a limit of the entraining plume model?
For example, in the tropics, the effect of vertical shear on structure and organization of convection is hugely important. And I don't see it coming in there in your equations. It does in terms of the shallow convection, but the heat and momentum transport by deep convection, really deep convection, doesn't seem to be there.
Well, we got to move on here, but thank you, Mitch. I'm sure you can continue talking at the break. So we're going to switch gear a little bit more towards microphysics here. So Qing Niu is up.
My name is Qing Niu. I'm a PhD student working with Christina McCloskey and CGD Ankara and Greg McFarquhar, University of Oklahoma. Showing the bias of surface incoming shortwave radiation calculated using the CMAP6 model, mean minus the satellite product during the Austral summertime. The dark red color here representing the large positive bias of surface incoming shortwave radiation, which can be related to the not reflective enough clouds over this region. As a matter of fact, this has been a problem in the past history in CMAP3, CMAP5, CMAP6. In the study, we're using observation data from field campaign as a ground-based-ish reference to first identify and then understanding the bias of CCN. So the field campaign here we're using is called Marcus measurements of aerosols radiation and clouds over the Southern Ocean. This is a DOE-funded field campaign. They put aerosol probes and clouds remote sensing instruments on board of an icebreaker, which transfer back and forth between Hobart, Australia, and the Antarctic stations, including Mawson, Davis, Cassie, and McCoy Island during the 2017 to 2018 Austrian summer. So in the past, the updates of Morris and Gentleman cloud microphysics schemes has been updating from MG1 to MG3. In general, it has been applied over this region to accomplish the first to enabling a louder low cloud coverage over this region, and then more supercool liquid water clouds here. But now within MG3, the CMAP6 do see a really large bias along the coast of the Antarctic. Then my backseeing logic line would be, well, maybe for that poor performance along the coast, model is just part of the reason. Another part of the reason is the observation itself. Essentially, the real atmosphere do show a significant amount of more bright cloud by the coast of the Antarctic. This is exactly what is being shown on the right here. Mason 2021 is showing the density plot of the cloud with high cloud droplet number concentration during the Austrian summer using a long-term climatology from the satellite retrieval. Theoretically, the number of cloud droplet number concentration should be equal to the number of cloud condensation nuclei, CCN, and cloud base. So naturally, the following up question would be, before talking about clouds, are CCN well captured in the model? In the study, we're using the CAM6, using the configurations in the chart, and a quality control of observation data and relocation of the observation and modeling on the right. We are doing the apple-to-apple comparison in this scenario, and here is the result. So on the slide, I'm showing you guys the figure with latitudinal dependence of number concentration of cloud condensation nuclei, NCCN, with simulations in red and observations in black. You can see from the observation over the South Southern Ocean SSL, the CCN has higher number concentration. Typically, the supersaturation in this scenario can sit between 0.2 to 0.5% supersaturation level. So those two figures together give us a confidence about CAM6 really underestimated the CCN. To better quantify, we calculate the relative bias, which is defined as model minus observation versus observation, from 0.2% in purple, from 0.5% in blue. So we can see there's really high bias of underestimation of ACC and NCCN close to the polar region. So now we identified the bias, the question came into how do we understand this bias? The first thing came into the mind is, so we don't capture CCN well, does that mean we didn't capture the size of CCN well? So for aerosol studies, aerosols are clustered into 4 modes as a function of diameter. It is accumulation mode AC that has been most CCN active efficient, and we are plotting them in black. We also quantify the blue, which is a small AC, and the large AC in red. Except that, we're also calculating the total condensation nuclei, which is called CN, which including icon mode, accumulation mode, and a little bit of coarse mode in this scenario. So pure observation perspective, if you see this chart here, polarward, we see a increased amount of small AC in red and a decreased amount of large AC in blue. This is exactly the same figure except plotting the CAM result in solid line and observation in dashed line. In general, the solid line is below the dashed line, implying the full spectrum of AC is underestimated by CAM. Furthermore, the red color do point out the polarward decreased of large AC is captured by the model, but the polarward increased small AC is not successfully captured, which turns out to be the dominant reason for a biased CCN in this scenario. We also calculated the ratio between CCN, NCCN, and the NCN to quantify the CCN action ratio. So on this figure, the dashed line from observation show a polarward increase of activation of CCN, which is exactly the reverse from the model. So to take into account the previous take-home message, The previous figure is showing there are substantial small AC over the SSO. This figure shows there are also efficient, effective CCN for both supersaturations. Besides the size, chemical composition can also influencing the activation of CCN, and I'm plotting this hygroscopicity figure, which is directly related to how the CCN is activated. I'm plotting out the CCN spectral from simulation in red, from observation in black. The scenario are clustered by region into NSO and SSO, North Southern Ocean, South Southern Ocean, and in November for spring, in February for summer. To make life easier, a vertical line here is representing a hygroscopic group of aerosol, and the lines with scopes is representing less hygroscopic aerosol group. So if you compare the two colors together, the best performance show up over the NSO in November, the worst performance over the SSO in February. So to summarize to the previous slides, there are substantial small accumulation mode aerosol over the SSO in the summer, which is the primary reason for the biased NCCN. So following up, I'm directly showing the chemical composition given from the model. So this is the CHEM6 result of mass concentration on the left, number concentration on the right as a function of latitude. It shows the sulfate in red, the sea salt in green, and organic in yellow. Take-home message here easily is that NSO is dominated by sea salt in green. Red color is sulfate is dominating the CCN over the SSO. While the organic has been multiplied by 100, it's still not the dominant component from a mass concentration perspective. As you can see on the left, which is exactly how the hygroscopicity kappa is calculated in the model using the AR function. So if you refer to the chart here, you can see sea salt has a higher kappa compared to the sulfate. Then in the previous figure, on the right bottom figure, we're overestimating the hygroscopicity can be caused by two reasons: the overestimation of the sea salt or the underestimation of sulfate in this scenario. Then I would vote to the sulfate is the reason for this falling up figures. If we plot the similar CCN spectral, but clustered by sea ice condition over solid sea ice on the right, over complete open water on the left, we can see a worse performance for secondary CCN, where the sea ice prevents production of primary aerosols, for example, sea salt, which is produced using the wind surface interaction over there. So again, we confirmed sulfate is more suspicious to be the problem. So now we're talking everything about what is the patterns of the aerosols, what is the sources over there. Can we talk a little bit of the sinks? Because precipitation, which influences the wet scavenging, is also influencing the number concentration of CCN in this scenario. So I'm plotting the normalized histogram of surface cloud W-band radar reflectivity in the unit of dBz over the NSO on the left, over the SSO on the right, with the red line clustering non-precipitating event on the left and precipitating event on the right, just roughly for an idea. So the arrow here pointed out that both over the NSO and SSO, the CHEM6 in orange didn't really catch up the heavy precipitating scenario a lot, which essentially comes from this chart on the below showing the rain amount is largely contributed by the large scale instead of convective processes over there. Then here's the logic. The model is underestimating the precipitation. It's underestimating the wet scavenging. Theoretically, it should overestimating the CCN number concentration. But as a matter of fact, the CCN is overestimated. It's underestimated, so back a little bit. Theoretically, the underestimation of the wet scavenging should lead to an overestimation of the CCN. But as a matter of fact, the CHEM6 is underestimating the CCN almost to negative 100%, which is furthermore emphasizing the underestimation of the small accumulation mode aerosol, particularly over the SSO in the summer over the sea ice. Then this is the take-home message. So we're starting from identifying the NCCN bias over the SO. We see a larger bias over the SSO during the February, which is dominated by the underestimation of the small AC, which can actually be effective small CCN, including over the sea ice. Considering wet scavenging is underestimated for convective precipitation not triggered enough over the Southern Ocean, we are more confirmed about sulfate can potentially be the reason of the missing small secondary CCN in northern summer, particularly over the February's SSO when markets happened. I'm gonna stop here and take any questions, and I'm gonna pay special thanks to all the folks listed here. This incomplete list of people have been helping me a lot for this research. Great to spend the research at NHAR right now. Thank you.
Time for a quick question.
So where do you think the sulfate comes from? What's the?
That's a good question. So essentially secondary CCN is more difficult or complicated to be simulated compared to this primary CCN. And right now we think to quantify the sources of the secondary CCN is still challenging. The highly potential sources can be new particle formation, transportation, aggregation, a very complicated chain of reactions in the chemistry perspective. That is the source of the CCN, secondary CCN in over the SSO in the summer over the sea ice, which is kind of more in a dark area compared to the primary CCN that is essentially focused on sea salt perspective. Thank you for the question.
Alrighty, we're right on time, so we'll switch to Christina McCloskey.
Okay, hi everybody. I'm going to be talking about the Southern Ocean as well, a little different perspective. So specifically, I'm going to be talking about mixed phase clouds, which is a big challenge for the community at the moment. This work is funded by the Department of Energy Atmospheric System Research Program. So I'm motivating this with a paper that I've shown several times now. I really like this paper. They did a 150-year simulation using CAM6 and calculated the cloud feedbacks over the entire globe. You can see that here. And they point out that in the first 15 years of the simulation, there's this cooling effect that occurs over the Southern Ocean. And this is because the Southern Ocean clouds, which are mixed phase, they have clouds called ice and liquid. After some amount of warming, these clouds transition to liquid phase clouds. And this is an increase in the optical depth, which then results in a cooling effect. In the last 15 years of that simulation, they did the same exact thing, but you can see that now we have less blue over the Southern Ocean. And what's happened is that these Southern Ocean clouds have transitioned to liquid, and now you don't have this cooling effect. So after some amount of warming and some amount of increased temperature, these Southern Ocean clouds and their a really incredible way of buffering the climate system disappears. So this is, of course, a model, and one of the big questions we have is, well, at what point will those clouds disappear, or at least their feedbacks and their cooling effects? And how well are we able to represent the interactions and how they would react to things like changes in dust sources, changes in biomass burning amounts, things like this. So making sure that the physics are correct in these clouds is something that I'm really motivated to look at. We know that there are still some biases over the Southern Ocean. Ching pointed out some papers as well, and I'm just going to highlight this analysis from Brian Medeiros' paper last year using the ISCIP satellite data set and highlighting some of the remaining biases in CAM6 and just pointing out the Southern Ocean where we have quite a lot of cloud cover, and so perhaps we still have a lot of room of improvement over that region. And then thinking about more of a case study or at least a field campaign, here are some vertical profiles of low clouds measured during an aircraft campaign sponsored by NSF Socrates. These are vertical profiles of temperature, cloud water content, and ice water content, where the observations are in blue and models in orange. This is from Andrew Gettleman's paper a few years ago now. You can see that for the Southern Ocean, we're doing a pretty good job of representing some super cool liquid water now, which is fantastic. But when we look at the comparison against the ice water content, which you can probably tell from the spread of these observations, that's very difficult to measure. But what we do know is that there are ice particles in these clouds. We have high ice concentrations, and there are a number of studies that have highlighted that we're not getting enough ice in these clouds now. Okay, so I'm coming from this from a microphysics point of view. What we think about in the Southern Ocean in terms of sources of what's called ice nucleating particles, or particles that are responsible for freezing those cloud droplets that are in that mixed phase temperature range. 0 to negative 40 degrees Celsius. In the Southern Ocean, it's a little bit of a simpler region compared to other places in the world, where we really only have to think about marine organic aerosols and also long-range transport. And so we're going to be incorporating a new parameterization for ice nucleation that accounts for those two species of ice nucleating particles. And of course, there's a lot of downstream processes that can occur as well, including things like secondary ice production, which is a major source of uncertainty in our climate system. Here's 6 of the 8 recognized mechanisms for producing ice once that initial ice is formed. But in order to have this process go, we really need to have that first ice frozen, okay? Okay, so the working hypothesis here is that marine ice nucleating particles, which I spent a lot of time studying during my PhD, are responsible for the onset of ice formation in these Southern Ocean clouds. That's what we think is going on. And there's some studies that have shown this. So this is using the UK Met Office model. I think this is HATGEM 3.0 or something. I don't know. I'm sorry. A 2018 paper, so it's a little bit dated. But what they were able to do is update their microphysics scheme. So on the left is their case that they're trying to replicate, the shortwave flux from satellite. And then this is their initial simulation using the default microphysics. And the difference between the left and right of these two model simulations is changing the ice nucleation scheme to include dust, which is using feldspar as a proxy for dust, and then marine organic IMPs. And you can see the drastic change and improvement in their simulated shortwave cloud flux. Excuse me. Oh dear. Okay, so, all right, so I just saved that word for this slide. There's other studies that show that there is absolutely no sensitivity, okay? So here's a study by Xiao et al. Using CAM6, okay, so this is the same model we have here. And now they're changing, okay, they have a control simulation, and they have a new ice nucleation scheme. Okay, basically all the ice nucleation schemes are different in these simulations. And I will not try to convince you that there's a change here, right? These are all lying on top of each other. So this is a study that suggests there's no sensitivity to ice nucleation. The clouds don't care, okay? I sort of refuse to accept that. And so I'm thinking about this from, again, a microphysics point of view, where we wrote a great review paper that you should download that highlights why this is really challenging. So you have ice nucleation as a place that, a big community is searching and researching this area. But in order for us to simulate this process, we have to also get the aerosol processes correct and all of the cloud processes that would influence how that cloud would respond to that one process, right? So this is really complicated, and you can see why maybe I hopefully have job security for a while. Okay, so in CAM6, how do we form ice? Well, here is a list of all the different processes that go into forming ice in CAM6 at the moment. So we have auto-conversion of cloud ice to snow. This is not a physical process, right? But this is what we have to do for a two-moment microphysics scheme. So we have this process. Then we also have heterogeneous freezing of cloud droplets, which is the process I'm going to be modifying. There's also a process, heterogeneous freezing of rain, which I'll talk a little bit more about. And then, of course, secondary ice production or ice multiplication. And right now, we're only representing rime splintering. And then, of course, the collection or accretion of cloud ice to snow. So, like I said, I'm going to be modifying this heterogeneous freezing of cloud droplets. So what we've added is this new deterministic scheme for marine and dust ice nucleation, which I don't want to go into all the details of right now, but just know that it's more straightforward, and also we have measurements, so we can assess it, so that's a positive. I'm running 2-year simulations, course resolution, and I'm using a developmental version of CAM6 that has some updates to MG2, which includes removing an ice number limiter that was an issue, and also adding in output for number tendencies. This is really important because before, while we were calculating number tendencies, we weren't able to look at them. So we've added that so that we can actually assess where the number of ice and other hydrometeors are coming from. So I repeated a very similar experiment to that Xiao et al. Paper using this implementation of these two parameterizations. Same exact story. So we ran different simulations, and again, this is looking at ice-water path, but it was also the case for the shortwave and long-wave cloud radiative effects. There's really no sensitivity in the model to this process. So why is that? So I'm going to go down a little bit of a rabbit hole, and hopefully you can learn something. Come find me if you want to talk more about microphysics. Okay, so here's number of concentrations as a function of temperature for cloud ice, rain, and then cloud droplets. There's no snow in this case. This is looking over the summertime in the Southern Ocean region. My latitude, longitude box is there. And then now looking at the process rates related to ice formation, they're all listed here. But the three main ones to focus on is, again, this emergent freezing of cloud droplets. So that's the process that we're perturbing, which really doesn't go into effect in these clouds until negative 25 degrees Celsius, so very cold. Whereas we also see emergent freezing of rain as the dominant primary ice formation process in these clouds. And then, of course, the secondary ice production or rime splintering gets kicked off. And what's interesting is that basically this emergent freezing of rain is a process that we haven't paid a lot of attention to because on previous versions, Cam 5 and previous, we didn't have to worry about this so much because we had a really active cloud droplet freezing scheme. And so this is kind of a new result. So what is emergent freezing of rain? Well, this is the parameterization that we use is from, well, a really long time ago, and it's from one precipitation sample. And the idea here is that emergent freezing of rain, the concept is that every cloud droplet has particles in them, right? And the larger your cloud droplet, and as you move to a rain droplet, the probability of that droplet containing an ice nucleating particle goes up. And so this is supposed to scale with INP, or ice nucleating particle number concentrations. So our first attempt at trying to modify this ice nucleation scheme of rain is to simply use a scalar. So what we did is we looked at simulated INP number concentrations near McGill University, because we are assuming that they're not shipping rain samples back in the early 60s. And we're scaling that to the INP number concentrations of the Southern Ocean, getting us a scalar of around 0.05. So then we've modified the emergent freezing of rain, and these are profiles showing the different ice number tendencies associated with the different processes. So we have emergent freezing of cloud droplets, heterogeneous freezing of rain, rime splintering, and deposition freezing. So I'll point out that there's no change. As you can see, there's very little sensitivity to the ice number concentrations. We do see that increase in the emergent freezing of cloud droplets when we change the factor for marine ice nucleating particles by a factor of 10, so that's working. And then we see a dampening of that emergent freezing of rain droplets when we add that modification. So I guess this is also to show that we're actually making changes to the microphysics, but also to show that the scale of these processes, so emergent freezing of cloud droplets versus the heterogeneous freezing of rain, there's no way for this process to compete with this rain process. So the next question really is, why is there so much rain? And when we look at the process tendencies associated with rain, we see that autoconversion of cloud droplets to rain is what's dominating this process. And this is where my work starts to link up with Qing's work, where we see that we know that the model has a low cloud droplet number bias. This is from an analysis from Isabel McCoy looking at cloud droplet number concentrations from the Socrates data set, and that's in this solid line compared to, in the lighter colors, the CAM output. These are just sampling the model output in different methods. And basically, you see a lot of these situations where cloud droplet number concentrations are less than even 10 per cc, but in general, they're lower than the observed amount. And this is directly related to influences the autoconversion process, which is inversely related to cloud droplets. So you can imagine if you have a low bias in cloud droplet number, this would drive a really rapid autoconversion process, producing a lot of rain. We also know from CAM6 PPE results that the autoconversion parameters score in the top 3 of the parameters that influence the short-wave cloud forcing and long-wave cloud forcing. So autoconversion is now kind of a focus. Okay, so thinking about whether or not precipitation is represented well in the model, I've already pointed out that this autoconversion process is dependent on the cloud droplets, which we know there's a low bias, but what does precipitation look like? Precipitation is a really difficult thing to measure, and so what I'm going to do here is I'm just showing from this micro data set, which was a land-based project. There was an amazing grad student, Emily Tenzi, who looked at all the data from this and provided a great data product, and we gathered from that that the average rain rate in this region-ish is about 0.2 millimeters per hour. And so what I'm showing here are just the rain rates that the model produces, and also how frequently the model rains at a rate higher than that average amount. So this really just starts to try to demonstrate that it's raining often in the Southern Ocean in the model, and it's raining at pretty high rates compared to what we would typically observe. We typically observe low drizzle rates of sometimes supercooled liquid. And here's another example highlighting that bias. So this is size distributions of cloud hydrometeors, and the observations are in black, and the model is in the different colors in the beautiful curves that you could never measure. But okay, so this is from Andrew's paper as well, and this is really awesome because we're comparing a size distribution of a GCM to observations, and it highlights that this yellow curve here, rain, is quite a lot higher than what we would observe from observations. And it also, again, highlights that the model is not producing enough cloud droplets compared to the observations. Okay, so just to kind of summarize, the Southern Ocean is a really unique environment, but also a place where we can learn quite a lot. The challenging pristine conditions are really hard for GCMs, okay? We have really low cloud droplet number concentrations that could be due to the low CCN biases that is being highlighted by Qing's work. We also are in need of assessing the subgrid vertical velocity, and that's linked up to Adam's work, and thinking about how our subgrid resolution of vertical velocities and supersaturation could be impacting this. But in general, we're seeing that this is a challenging region. And since we have such low cloud droplet number concentrations, we form a lot of rain. And this rain, the rain number concentrations that are in CAM are far exceeding any sort of IMP number concentration. So there's basically no hope for ice nucleation to matter in these clouds. And then ultimately, those are treated with a very dated heterogeneous freezing of rain parameterization that then triggers that secondary ice production. Okay, so there's a lot to do still here in this work, but I'm hoping to finish this up in the next few months. But the idea moving forward is to continue to assess the cloud activation process. So this includes the vertical velocity and supersaturation, and thinking about how well that's being represented. And also to think about how we can actually address this cloud droplet number bias, so actually increasing that value, and to see if we can get some different physics going on. And then of course, revisiting this heterogeneous freezing parameterization for rain. But I will leave it there. Thank you so much. I don't know how fast I was.
We got time for a super fast question.
And sorry for my potty mouth.
And a super fast answer.
It's a good memory.
You didn't talk too much about the ice rime shattering, the rimed ice shattering.
Have I talked about it?
No, you didn't talk too much about that. Is that does CAM6 do a good job of that? And what's the exact process? I've never really.
Yeah, so the rime
collision
splintering
based?
process, the concept is that as particles rime the supercooled water, they become very easy to fragment and collide and things like this. The parameterizations we have are based on laboratory studies that recently a group tried to replicate and were unable to do so. I would say that secondary ice production is probably the biggest source of uncertainty in cloud microphysics at the moment. And so in terms of how well CAM does at representing that process, I would say we don't know, but probably not very well. Sorry. Thank you.
So, and up next is Geethma.
Hello everyone, I'm Geethma Veerapitia from University of Wyoming, a PhD student. Thank you for this opportunity to present our work on constraining climate model exotropical cloud feedback using cloud sources and sinks in cyclones. The recent study by Zelinka et al. Shows a positive shift of negative exotropical cloud feedback in the Southern Ocean from CMIP 5 to CMIP 6 models, and this has led to high equilibrium climate sensitivities in several CMIP 6 models. And amongst these models, CSM2 has an equilibrium climate sensitivity of a little over 5 kelvins. So this is concerning, and what our study does is we are trying to constrain the Southern Ocean cloud feedback and trying to see whether we can rule out this high equilibrium climate sensitivity of a CSM2 model using the atmospheric model of CSM2. So in our study, what we examine is the contribution by shortwave cloud feedback driven by the intensification of hydrological cycle specifically in the Southern Ocean. And a robust feature of a hydrological cycle is a net moisture divergence in the subtropics and a moisture convergence in the exotropics. So since we are looking at the Southern Ocean exotropics, we thought cyclones play a huge role in this hydrological cycle, and we consider the warm conveyor belt as the source of moisture convergence that transports warm, moist air from the subtropical latitudes to exotropical cyclone systems. And in this study, we calculate the warm conveyor belt moisture convergence as the product of a 10-meter wind speed, water vapor path, and a constant. This is the same calculation that was used in Field and Wood 2007 study. Here I'm showing the variation of AMSR rainfall rate with the warm conveyor belt moisture convergence in Field and Wood 2007. There is a one-to-one relationship here, and so we can expect a warm conveyor belt moisture convergence to be a good product of the rainfall rate. So in my study, I'm constraining the Southern Ocean cloud feedback using this precipitation efficiency in the exotropical cyclones. When I say precipitation efficiency, the idea is that this moisture convergence into the cyclones is balanced out by the precipitation. Here there is a positive monotonic relationship between the warm conveyor belt moisture convergence and the cloudiness in cyclones. So if you look at the blue plot over here, in a world with inefficient precipitation processes, there is a higher slope in this plot. There is a higher slope between liquid water path and warm conveyor belt moisture convergence. And if you look at the red plot, when there is an efficient precipitation processes, there will be a shallower slope between liquid water path and warm conveyor belt moisture convergence. Anyway, in this situation, with warming, there would be a shift to the right in all of these plots, driven by Clausius-Clapeyron relationship, where water vapor path increases with the temperature, and hence the warm conveyor belt moisture convergence increases with it. So in a warmer world, we can expect more exotropical cloudiness. And in respective to the shortwave cloud feedbacks in this relationship, when there is an inefficient precipitation process with a higher sensitivity of liquid water path to warm conveyor belt moisture convergence, we can expect strong negative shortwave cloud feedbacks, whereas in efficient precipitation processes, we can expect weak negative shortwave feedback. So what I'm basically doing is I'm taking this regression between liquid water path and warm conveyor belt moisture convergence in cyclones in the Southern Ocean. And so it tells something about the precipitation efficiency of the cyclones. So it should tell something about the shortwave cloud feedback of the Southern Ocean. So for this, the tool that I'm using is a perturbed parameter ensemble, PPE. So I'm talking about all kilometer scale processes here, cyclones and feedback, but ultimately they are all driven by microphysical scale parameters which need to be parameterized in a global climate model. To give a very brief introduction on the PPE, imagine a model with a single parameterization. For this talk, I assume this single parameter to be auto-conversion, where A is perfectly defined and we are only uncertain about the B and C exponents. In that case, we can vary the B and C exponents in their plausible ranges and get a plot like this for, let's say, for an observable, for example, cloud fraction. So from this observable, we can take out the values that are not possible. So from that, we can constrain an unobservable, such as aerosol forcing. So a PPE is where many such parameters are perturbed to get different models. In my study, I'm using the CAM6 PPE. This is the atmospheric model of the CSM2, where 45 parameters are perturbed in 262 ensembles. And this has a fixed SST and ICE. This was developed by Trudy Eidhammer and Andrew Gettleman at NCAR, and my advisor Daniel McCoy and my colleague Sir Song also participated in this. You can find the preprint of this CAM6 PPE in this QR code. To constrain this, I'm using observations from the MAC-LWP dataset. MAC-LWP is the acronym for Multi-Sensor Advanced Climatology of Liquid Water Path. This is a microwave radiometer-based measurement dataset. This was developed by Greg Alcesa at NASA GIS, and I'm using precipitation from the iMerge version 7. And I'm doing a cyclone compositing in my study. For that, I'm using MERA2 reanalysis data. So to do the cyclone compositing, I'm doing this over oceans in the region 50 degrees south to 70 degrees south over the summer. And I'm using the method that was introduced in Field and Wood 2007, which uses sea level pressure anomalies, and each composite in my study are 4,000 kilometers across. So basically I have composited cyclones in the 262 CAM6 PP ensembles and in the observations. These are results from these composited cyclones. Here I'm showing the liquid water path variation with the warm conveyor belt moisture convergence for the Southern Ocean cyclones. The black dashed line is for the observations. The blue dashed line is for the CAM6 default model that goes into the CSM2. And all the solid lines are for the other CAM6 PP ensembles. So we see that the cloudiness is scaled by the warm conveyor belt moisture convergence, similar to the behavior that I showed in the Reustick figure earlier. And also, these are colored by the shortwave cloud feedback. And even in this, we can see where the sensitivity of liquid water path to warm conveyor belt is high. There are more negative exotropical cloud feedback, and when this slope is shallower, there is more positive exotropical cloud feedback. So I used that regression between the liquid water path to warm conveyor belt moisture convergence in present day cyclones, and use a Gaussian process emulator to get 1 million emulates from the CAM6 PPE. And here I'm showing the response, like the variation of precipitation efficiency response with warming, with the precipitation efficiency of the cyclones, and the shortwave cloud feedback. For the response in warming, I'm using SST plus 4K models in CAM6 PPE. So we can see with lower precipitation efficiencies, we can expect a bigger liquid water path response to warming and more negative cloud feedback. And one interesting result that I got from this is that I looked at the moisture convergence responses to warming and liquid water path responses to warming in CAM6 PP ensembles. And even irrespective of the parameter variations in these ensembles, all of these have a robust behavior where the exotropics moistens and the subtropics dries out. I find this very fascinating. And I'm looking at this zonal mean liquid water path response with the Southern Ocean shortwave cloud feedback. There is a nice correlation between these two, but it's quite spread out. So I scaled the liquid water path response with the radiative efficiency, and it linearized the relationship very nicely. So this shortwave cloud exotropical shortwave cloud feedback is a product of this macrophysical liquid water path response and radiative efficiency. Here I'm looking at the variation of precipitation efficiency and radiative efficiency with the present-day liquid water path. The radiative efficiency, there's a saturation with increasing present-day liquid water path, and there is a positive monotonic relationship between the precipitation efficiency and present-day liquid water path. So we can also see that when the present-day liquid water path increases, there is a compensation between strong sensitivities of liquid water path to warm conveyor belt and weak sensitivities of albedo to liquid water path. So from this, I thought maybe I should integrate the precipitation efficiency and the radiative efficiency to get a better constraint on the Southern Ocean cloud feedback. And these are the final results by the 1 million emulates that I got from the Gaussian process emulator. The red line is for the prior, and the blue line is for the liquid water path to warm conveyor belt sensitivities plus the radiative efficiency posterior, and yellow line is the posterior for liquid water path sensitivity with precipitation and albedo susceptibility, like radiative efficiency. And the left plot here shows the precipitation efficiency response in CAM6PP, and the right plot is the shortwave cloud feedback. And the black dashed line is for the CAM6 default. So the tables right below shows the reduction of 95% confidence interval range in these parameters. So if you look at the shortwave cloud feedback plot, more positive exotropical cloud feedbacks are constrained by that, and even the CAM6 default, which has an equilibrium climate sensitivity of 5 Kelvin, is to the lower end tail of this constraint. So yeah. These are the take-home messages from my presentation. I would like to acknowledge the NASA PMM grant that supports my research, and I would take any questions, and feedback and comments are welcome. Thank you.
We've got time for a very quick question, if there is any.
Do you think there's any hope of this constraining across CMIPS models?
So here I've just only looked at the CAM6PP. So we are thinking of including the CMIP6 models in here to see where that range is applicable. But in this study, I've so far done only for the CAM6. And I'm actually hoping to do this for the GIS E3PP, but funds are enough for the CAM6 right now, yeah.
Okay, thank you. So we'll have a 30-minute break now, and please don't forget that the organizers would like to take a group picture somewhere close to here. Please follow the instructions. Hey, Vince, can you hear me?
I think you're muted. You might want to try unmuting yourself.
Vince, can you try and speak?
We
Yeah,
don't
we
hear you.
can't hear you.
Try speaking now. No, we don't hear you in the space.
Is Margaret Duffy here?
Sorry.
Outside, no? But she's not in here.
For those
Okay.
joining us remote, we're going to try to debug.
How about Rich? Would you be willing to give your presentation now since we have technical issues? Or do you need to do some meditation? And okay, alrighty. Okay, we're having some technical issues, so trying to figure that out with Vince. So Rich Neal will give his presentation now. Yeah, I didn't get a hold of Margaret, so it's Rich Neal. Oh, you're here. I didn't see you. Okay. Well, let's do Rich. I asked Rich.
I'm prepared now. Yeah, I think you can. Oh. All right. Okay, so this is, as Adam said, I'm the comfy pair of slippers on this one because I'm going to look into, and specifically I'm going to look at how can we use a very simple framework for total energy to augment and improve the vertical extent that convection goes in CAM. So why is this important? I think one of the big things that has been identified recently, increasingly through model versions of CAM, is that it's not deep enough. And one of the problems with it not being deep enough, there's not kind of convective overshoot and really elevated convection. And as we can see here, oh my gosh, move. Oh, there we go. So convection occurs, and it's a very simple schematic here. There is an outflow that would be considered in ZM. But a component of that in terms of elevating convection is kind of missed. And part of that is this is, in some sense, a stable layer in which convection detrains. But there are some issues in terms of that process not really being represented in CAM. A couple of examples of the tape recorder we've been kind of wrestling with recently through CSM development. So these are kind of ascending regions of dry and moist regions above the tropopause, and this is underestimated in CS3 compared to OBS. And also trying to get a sense of understanding the MGO-QBO teleconnections, and they kind of depend on, it's a little gray here, they kind of depend on convection really having an impact on that near tropopause region to get the connection through stability changes in different phases of the QBO, which is important for prediction. So essentially, the Zhang-McFarlane framework cannot really represent this kind of overshoot, this non-stable dependent, stability-dependent framework. It just works in this CAPE framework. So this is just a summary of the existing problems with CAM that we've kind of wrestled with over many years. And essentially, what we're looking at here is simple single-column experiments. I should stay close to the mic. The Toga core region, so ostensibly a convecting region of the ocean. And we can see here, this is kind of, we have gone from a point in CAM 3 many, many years ago to a point in CAM 6 where we have convection, which is too shallow in most circumstances. Not always, but most circumstances. And we can see when we look at the mean and the total convective heating, it's very clear that we have gone from this kind of mean profile in this particular configuration of CAM 3 green, and we're all the way down with 58 vertical levels in CAM 6. This was kind of the worst kind of setup for a convection that doesn't seem like reasonable. And we can see also that the depth of convection has shallowed somewhat, which is also kind of in poor agreement with observations. So what we do, and I won't go into a ton of details about this, but it is a simple kind of augmentation of the way that the plume dynamics are considered in the ZM scheme. And essentially, as it exists right now, it's a purely convection stability, a stability CAPE kind of framework. And there are many ways to kind of augment that with more of a total energy, considering kinetic energy, kind of aspects that will enable the plume to be considered from a total energy perspective. And just briefly, the total energy of the parcel essentially is the total kinetic energy that's added to the parcel is the total potential energy, so the buoyancy, and you convert that with a particular efficiency that you prescribe. And then you add, essentially, considering an ascending plume, the kinetic energy of the parcel below, plus the kinetic energy of the total large-scale ascent or descent. And then we use that to kind of construct an addition to the scheme. So if we look, when we implement that, we can see here a couple of figures. ZM mass flux, again, this is for that. The Toga core, and then the parcel kinetic energy. So if we think about the mass flux, we have a couple of configurations here, the red and the green, that don't have this kinetic energy modification to it. And we can see that the mass flux has a low maxima way down deep in kind of the mid to lower troposphere. And when we make this augmentation with the kinetic energy consideration, we can see that now the mass flux has a much more top-heavy profile. It seems to go further, so it's going above levels that we see in the previous model versions. And if we think about what is the consideration of the parcel kinetic energy, when we do this, we can see that when you make that calculation near the surface, you give the parcel a specific initial energy. And then this very simple equation means your parcels increase velocity, and as they kind of consume the CAPE, if you like, convert the potential energy. But then towards the top, when it's a stable layer, then it loses kinetic energy. And when that hits zero, that's the top of your convection. Whereas before, it's where the buoyancy is zero is the top of your convection. So that's how it's different. And I think to note here essentially is if you add that augmentation by itself, you get pretty strong response. This blue. Is that me? But if you kind of include something that's going to be included in CAM 7, which is a parcel mixing in the boundary layer, that is essentially meant to kind of offset some of the slightly extreme behavior we see with 58 levels, then you get a response that, as you'll see later, seems a little bit more realistic. So take that, and then this goes back to our previous plot that I showed you. It was too shallow. So that's where we were before, CAM 6, 58 levels. Yeah, it really is hitting essentially these shallow layers early on in this quite organized period. And so we can see when we make this change, we get deep convection that seems much more realistic from the perspective of increasing heating, a maximum heating, and decreasing heating along the whole of the profile, whereas with the CAM6 L58, there's a lot more kind of sporadic behavior. And when we look at the vertical heating, the key things here are the purple and the blue one, we have a much more, a greater increase in heating in the upper troposphere. You also contrast that with what Club is doing, so the kind of the other part of the condensation physics in CAM. And we can see previously, in the cases without this KE augmentation, the red and the green, they play a nearly as great a role as ZM in terms of heating the atmosphere, which of course it has to if ZM is not doing enough. But the contribution is much more limited when we turn on this scheme. This is just a good summary of, oops, sorry, so incompetent. So this essentially gives you a sense of, again, for that Toga core period, kind of this Goldilocks behavior. With L58, we have this, the red, we have occasionally deep, but mostly this super shallow here. With this parcel addition, we're overshooting all the time, so much deeper than you ever really get with the existing scheme. But then, the kind of compromise is the purple here, whereas it's mostly deeper than before, but in periods where it's not raining here, for example, then it's moderated, so it's much shallower. So that's kind of the behavior you want. And so I just have a few plots now of, I had grand plans to put all this into the most recent version of the model, CAM7, et cetera. But I got all the code going, but it runs about a year every year, so it's a little slow. But if you just do 32 levels in CAM6, the behavior is quite similar. So we're going to use this kind of configuration. So you can see that even with a coarser resolution, we get this deficit in heating in the upper troposphere, and we kind of correct that with this parcel method. And so this is, of all these plots here, will be kind of the default. It's 2 degree on the left, just adding this kinetic energy augmentation is in the middle, and then adding these both these pieces, this PBL piece in CAM7 together on the right. This is total precipitation for the seasons. In general, it does a similar job. We do have problems. It's hard to tell here, but typical problems, as always, is West Pacific in summertime is always a challenging problem, and there's a little bit of a hole there. So it's not perfect, but if you look at the behavior, the depth of convection, again, these are the 3 kind of configurations here. You can see if we looked at deep convective moistening at 200 millibars, where we thought we had a deficit, tape recorder, et cetera, of humidity, we're really punching through a little higher. So the tendencies from humidity, these are parts per million, but we're getting up to the levels where it's kind of covers the range of the tape recorder range. When you add these two together, it's kind of moderated, but you still do get this increase in humidity. And associated with that is the pressure of the mean convective cloud top. And you can see that, in CAM6, it's pretty low when you average it for ZM convective cloud top. 500 millibars is pretty low, but that's consistent with the Toga core. But then when you add these two methods of, considering kinetic energy, we're really punching up to 200, 300, and higher. This is probably too high, of course, all the time going up to 200, 150 millibars. But one could imagine that 300, 350 is more reasonable. And also, in concert with that, it's no surprise that the top plot here is the same as before, but the second one is convective precipitation. So in the tropics, of course, the convective precipitation, accounts for most of the precip. I was kind of surprised it was this much. I guess at 2 degree, it's going to be more than 1 degree, but we're approaching 80, 85%. You add just this KE piece itself, then it really starts to dominate 90% precipitation, which makes sense. You have deeper heating, etc. I can't talk to the triggering frequency per se. And then it's, like I say, consistently it's moderated with this PBL component to the scheme. This is really the final plot, and this is kind of going back to the convective heating. Is that consistent with what we saw in Toga core in the single column experiments? And it is. We added a new experiment here. It's essentially 1 degree CAM6 in the blue, and then 2 degree in the yellow, and it has this deficit. If we take an average over the West Pacific, it has a similar deficit to the single column model. But then with these two additions at the expense of club heating again. I'm not saying necessarily that this is too little now or too much, but I think that the fact that ZM is able to kind of add to that and go deeper than before, it says the scheme is kind of working how we expect. So, in summary, with the comfy shoes by the fireplace, Adam, this is actually the wrong way around, but our motivation here essentially was, ZM is not going deep enough, the heating maxima is too shallow, and it's essentially too sensitive in ZM because it's designed that way to stability, sometimes single layer stabilities. And so we've implemented this kind of PA plus KE ZM plume viability. And in Toga, it performs well in the tropics. It kind of beats down some of the noise. I'm not exactly sure why that is. Has deeper heating and a deeper convective top. I didn't go into this, but it's more complex in non-tropical convective regions, middle of the US in June, July, August. But the same kind of paradigm can hold. It's just that you have much deeper boundary layers, and considering the dynamics of the initial plume are important. And, low-res CAM6 simulations kind of consistent with that, and, there's no doubt it'll be tunable based on the way it's implemented. And just finally, there are different, obviously more complex ways you can consider the plumes are initialized, for example. It goes back to those more complex vertical velocity equations that I showed in that table. And just to finalize, this is not a future for ZM, but it may help in the short term, I think, to help with some of these problems that we see in the upper troposphere, et cetera. Thanks.
Okay, we got time for a very quick question.
One of the challenges in the tropics has often been moistening the mid-troposphere because the convection goes too deep. Have you not made that worse or anything, or is Club sort of cleaning all that mess up?
Yeah, a little bit. I mean, from the convection's perspective, we didn't shallow the convection by accident over the years. It helped a lot with a lot of moist mode physics in the tropics. But that's a kind of early phase sensitivity in any kind of cycle. The latter stage sensitivity is deep, and we don't have that with respect to being kind of explained by ZM mostly, as opposed to ZM and Club. Yeah.
Mm-hmm. Okay, thank you, Rich, for jumping in with seconds notice. So for those of you who joined just now, we had some technical issues, so Rich Neal gave his presentation now, but now we'll go back to Vince. I think the technical issues have been resolved. Can you hear me, Vince? Yes. Yep.
sensitivity. And you can see these green circled metrics. These are regional metrics, although actually in this case they're global averages. They have moderate bias but very low sensitivity. And so they're basically unbudgeable. You could treat these points, imagine them as being like a scatter cloud of points in a linear regression, and we want to fit a best fit line. If we fit the green points, well, that line is not going to fit the red points, and no regression method would do that. It would fit the red points, and it would leave these green points essentially unbudged. So these points here are stubborn biases. Let's look at another type of problem that we have, what I'm calling a tuning trade-off. The tuning trade-off between different metrics occurs when changing the parameter values improves some metrics but worsens others. So this is a classic dilemma that developers have. We can develop a metric which can look and try and detect some of these tuning trade-offs, and we can use a similar methodology as before. So we look again at this matrix equation. Again, we dot the parameter vector into the rows of the matrix here, the sensitivity matrix. We consider the first row like we did before, that's the stratocumulus region. But now let's also dot the vector into the second row, which I'm saying, let's suppose a cumulus region. So now we have two equations. We want the same delta P to be able to, satisfy both equations. We can subtract the cumulus equation from the stratocumulus to form this equation here. And then we can use a Cauchy-Schwarz again to get another bound on delta P. This bound is a little bit different. What it says is, if these two sensitivities are similar, but the biases are very different, then we're in trouble. And that makes sense. If, say, the stratocumulus is too dim, cumulus is too bright, but those regions are affected the same way by the parameter perturbations, well, then we can't improve one without worsening the other. So in any case, we can develop diagnostics like this, and we've done this for this EAM run. And what this plots basically is the sort of minimum delta P. Again, we want this to be small, and we see that it's large for the vocals, near coastal vocals region. So in other words, that means if we try and match near coastal vocals clouds, we're not going to be able to match the other regions. So that is a problem. So let's see what happens when we actually tune given this sort of situation. This is where we started off, 12.66 with this little dim region here. If we tell quad tune, okay, we insist on matching that dim region, we can remove it, and we actually do improve the RMSE because we've got other parameters working, but it's not as good as what Jun gets when he just does hand tuning. He gets 10.1, quad tune gives 11. Okay, here's the key thing though. Jun has produced this very good result, but he's ignored the near coastal vocals region. And so he gets a better result, but that's kind of expected. This is telling us if we insist on matching near coastal vocals, we're not going to be able to match the other fields in general. So this is kind of information that you can get from these metrics. What do we learn? We learn that EAM has some stubborn biases. We learn that there are tuning trade-offs. If we try and match near coastal vocals, we can't match it simultaneously with the other fields. What can we learn from quad tune in general? Well, one thing we learn is when to give up. In other words, the tuner helps distinguish this parametric from structural model error. So if the tuner is actually working properly and it can't find acceptable results, then either we should find new parameters or else change the model structure. And it's nice to know when we're at a point where we can just stop tuning and try and rethink the problem. The other thing we learned about is which parameters matter in which regions. So we saw this C inverse tau shear parameter, or surface parameter, mattered in the near coastal regions. That doesn't tell us exactly what the problem is. It doesn't tell us exactly how to fix it, but it gives us a hint. So in any case, that's all I have. Thank you.
Questions?
Hey Vince, just a quick question on the tuning. Do you see any application for this to auto tuning? So having, a machine learning algorithm, for example, try to figure out what the tuning parameters would be?
Ideally, yeah. So this was designed for people like me who don't have computer power, and so it's just sort of a guide for someone who's tuning manually. But in principle, yeah, if the system could work well enough, then you could imagine just trusting the result from QuadTune. In practice, we're not quite there yet.
Did you use short runs or long runs to identify the bias? Because if you use long runs, the physics errors and dynamics errors would couple and make it more complicated, right?
Yeah, we used long runs, not long runs. We used 14-month runs, so it was sort of a compromise. I've talked with Colin Zarzicki about using shorter runs, but it's not clear that we get exactly the same answer between, let's say a 3-day run or a 5-day run and a 14-month run. But mostly we're determined by computational expense. If we were to do a 10-year run, then it would just take too long.
Righty, thank you, Vince. We'll move on to the next speaker who is also online. That is Itai Griniasti.
All right, thank you very much for having me, and I'm very sorry I couldn't do it in person. Can you see my talk?
Yeah, we can see your talk and hear you.
Okay, excellent. So thank you very much. I am Itai Griniasti. I'm a postdoc at Cornell, a statistical physicist, and I've been working with Angie Pendergrass, who's also at Cornell, on trying to see how we can employ the geometry of parameter space and PPE using both standard and really ultra low resolution CSM BPEs to try and tackle the following question, which is how to constrain climate projection with observations, given that there is such a huge dimension to parameter space. So just like Vince discussed, you can tune a few parameters and follow them around to sort all kinds of, bugs that you have or errors that the model produces, but I can't see you, which is sad. Now I can see you. But you can't derive the uncertainties of the model predictions from this, because there could be a model which, or a set of parameters which conforms with observations, but you haven't looked at. And there's this notion that has been observed when we look at complex systems that we don't really need to explore all of parameter space, all of these thousands of parameters that are contained inside CSM. There's only a few of them that really matter. And this concept is dubbed sometimes sloppiness. And it goes as follows, approximately. If there is a very high dimensional parameter space, and you're going to explore a ball of those parameters locally, then there are going to be some stiff directions and some sloppy directions, just like the sensitive and non-sensitive directions in Vince's talk. But importantly, there's going to be a spectrum of how sensitive things are generically. And that spectrum is going to be exponentially dropping, and it's not going to be along the parameters, but along some combinations of them. So that spectrum can be derived by essentially taking that sensitivity matrix and looking at singular values or dotting it with itself, getting the Fisher information metric, which really discerns how much can we locally discern between cross correlations of different models. And the spectra of this metric is, as shown here, generically exponentially decaying. So there are directions that really contribute to how much we can tell the difference between models, and there are directions which don't. Now, this generic behavior is observed only when you ask kind of simple questions. So if you ask what are the global annual means, this is the kind of behaviors you should expect. Much like if you look at a gas and you ask what it is, pressure of the gas or the temperature, it's going to depend on only a few parameters and not on where every molecule is. If you want to predict a very spatially resolved behavior, then you're going to depend more stiffly on a lot of parameters. Now, this has been shown to be true for a host of complex systems, essentially any that has been analyzed using this technique, from biology, including cell signaling or circadian clocks, the behavior of molecules using quantum wave function calculations, or analyses of the US power system. So it's a very generic behavior that we should expect from the model, also hopefully from climate models. There's a second feature to sloppiness. There's this local description, which I told you about, but then there's this global kind of behavior that one should expect, which is that if you look at the output of the model, when you vary all of the parameters, then it should follow a hyperribbon. It lives in a very high dimensional space, right? But it's not going to be fat in all directions. You could try and imagine that you have this cloud of points and you could try to envelop it in an ellipsoid. And that ellipsoid is going to have diameters which are also exponentially thinner. So there's a long direction, a shorter direction, following a geometrical series. This is also reproduced in a host of models. Now, what the two of these mean together, this local and global sloppiness, is that we can identify a low-dimensional set of directions in parameters that we need to follow in order to change behavior, and that those are not going to change through the model's predictions likely. And that means that we can explore the model's behavior by using only a few parameters. And that means that we can quantify uncertainties by exploring only a few dimensions in parameter space, only a few combinations, and constrain them with observations. Now, it's a kind of dimensionality reduction technique, if you'd like, which to first order and also to second order is much more rigorous than the kind of tricks we usually use using VAEs or other machine-learned dimensional reduction techniques. However, it does require estimating the gradients of the model, and for fancier versions of this, you need to estimate also the second derivatives with respect to all of the parameters. And that sounds kind of awful, I think, to many of you, and certainly to me. It just doesn't seem computationally feasible. And so what we have been exploring is using a low resolution model, the ultra low version of CSM with 10 times 15 degrees. Now, unfortunately, I can't see your faces, but I bet many of you think this is completely useless. It might not convey the right physics. And I would like to claim that this is not the case. That when you ask global questions, this low resolution model actually does a decent job, an adequate one. So I'm going to try and benchmark it and compare it. And I'm going to use the same PPE mentioned before, led by Trude Eidhammer, which was a high resolution, standard resolution ensemble of models with perturbed parameters. And I'm going to reproduce it, and this was really done by a junior here at Cornell, Ben Moose, a fantastic student, with the low resolution model, the ultra low resolution. And you can just reproduce the results and compare the low resolution to the high resolution model. And you see that there's a linear relationship between any quantity predicted by the low resolution to the high resolution. So it's not a unity, it's not an identity mapping, it's not predicting exactly the same thing, and it should not. We know that when we coarse on a model, there is a renormalization flow of the parameters, which means that there's going to be a shift and a rescaling of the behavior. But locally it's linear, so this factor of 10 that we've taken in every dimension has only been a perturbative variation of the scale as far as the predictions are concerned, which is a very promising relationship. It means we can map easily between the low resolution predictions and the high resolution ones. This holds not only when you change ensemble members, but when you follow a specific parameter and you vary it within that PPE. And what I'm showing you here is both the low resolution and the standard resolution on the same plot and the corresponding linear approximations. And it's just very hard to tell them apart. They're so similar. To be fair, we have rescaled here by the overall variance. So there is a shift in scale, but that's it. It's a linear relationship. This is true both for present day and for forced 4K SSTs. So this shows that the model seems to be very adequate in predicting what's going on. It also preserves what was very nicely demonstrated by that PPE, where if this is CMIP6 variability in the feedbacks, which is very wide, it's reproduced by the high resolution or standard resolution PPE, but it's also reproduced by the ultra low resolution PPEs throughout. So we can really explore the wide range of performances. There are some caveats. You can't expect this model to predict correctly spatially resolved behaviors, and indeed, it does not. So it's adequate only for global kind of questions. There are some shifts. For example, there's a substantial tough model radiative imbalance, but this is because we're looking at the ensemble average over the parameters tuned around the mean of the standard resolution model. And you need to shift the parameters for the low resolution model by this linear quantity that we can predict. So this is almost a feature, not a bug. Moreover, looking ahead, we are planning, because this is such a cheap model, this took only about 8,000 hours to run, core hours, to move to a slab ocean one, should fix this discrepancy. Finally, when you try and measure what is the sloppiness of climate models, just using this PPE, we see a very nice result. We see full orders of magnitude spanned by the outputs of the model as a function of varying the model index or the principal directions, which means this is a very thin hyperribbon, essentially. And so it's going to be hopefully amenable to the kind of tricks we can borrow from information geometry to explore the model. So to summarize, climate is sloppy. Many of its predictions, global annual ones, depend on only a few parameter combinations, which I bet you know better than I. And the ultra low resolution CSM model is adequate for exploring global behaviors. I hope I have slightly convinced you, and I'm happy to hear any critique or suggestions. With that, I'd like to say we're going to look ahead for exploring now the gradients using this technique to analyze robustness by projecting the observables onto these interesting directions. And thank my collaborators and funders, especially Angie, who has led me into this work of climate. Jim Setna, who's a mentor at Cornell and also a world expert on the relationship between very coarse-grained and high-resolution models. Ben and Josh, students working with us. Thank you.
Any questions? Another application of this low resolution model could also be just in our software testing to check if a commit to the code has messed up stuff. So a
Yes,
very cheap chest with some real world climate stuff in it will be really nice.
I think it can. So essentially, once we have this map between the low resolution and high resolution parameters, or standard resolution parameters, and even high resolution parameters, then one can use it to explore what happens. And given it's such a nice linear map, it seems, it would be a very effective tool.
Alrighty, thank you. We'll move on to Margaret Duffy.
Hi, everyone. Today I'm going to be talking about the mechanisms of the pattern effect in KM6. And this is the same pattern effect that Maria was talking about earlier. And so if you kind of put your mind back to this morning of several talks ago, you'll be in the right mindset to digest what I'm about to talk about. And I'm Margaret Duffy, and this is work I've done with Brian Medeiros and Andrew Gettleman. Okay. I want to just spend a little bit of time going over what the pattern effect is and why it's important, even though we heard a little bit about this morning. And that is that the pattern effect relates the pattern of warming, so like the SST pattern of warming, to radiative feedbacks. And this is kind of the, canonical kind of point here. Oh yeah, okay. The really commonly used figure that we use to quantify this. We've seen it already this morning, and I just got back from CFMIP in Boston last week, and we all checked this figure off of our bingo cards pretty quickly and pretty frequently. So let me just go through with you what this figure is showing. It's showing the change in the global mean radiative feedback for a change in local SST. So if you change the SST, if you warm the SST in the tropical West Pacific Indian Ocean region, that tends to have a stabilizing effect on the global feedback. And so what this is telling us is that the pattern of warming is extremely important for getting our feedbacks right. And of course, those feedbacks are important because of their implications for climate sensitivity. Okay, in case it's not obvious to you that this is important, here are a couple of implications. On the left, I'm showing the implications for the radiative feedbacks over time. So a lot of times people talk about the pattern effect, not so much as this relationship between SST and radiative feedbacks, but the fact that the radiative feedbacks tend to evolve over time, for example, in 4 times CO2 simulations. So we can see that here. And we can see that, panel E over here is showing that the ECS in the first part of a 4 times CO2 simulation tends to be lower than the ECS later in the simulation, meaning that the climate sensitivity is increasing over the course of the simulation, which is a little bit scary. And this is attributable to this pattern effect. Another thing relevant to our modeling community is that the pattern effect is a big reason why we care about biases in SST and SST patterns. So Maria told us that SST is maybe the good, but actually if you focus in on the patterns, we can see some biases in potential biases in climate models. This is a figure from Rob Wills. The 2 panels are showing very similar things. I'll focus on the bottom one. This is the ratio of warming in that tropical Pacific warm pool region, which was blue. That's that blue region here, to the tropical average. And we can see the observations are the red dots here, and then the models are these kind of rainbow dots. And we can see that there tends to be a difference between what the observations are showing and what the models are doing. And there's a lot of discussion about whether that's forced response or internal variability, but this is one of the reasons why we care so much about the pattern effect. Okay, this is a busy slide, and you don't have to understand all of this, but this is just to bring models, explain why models are so useful for understanding the pattern effect. This is a figure from the GFMIP protocol, Green's Function Model Intercomparison Project, which is an informal MIP where modeling centers, including our own, are submitting simulations where the SSTs are perturbed in these patch experiments. So you add something like this to your background SST field many times over, so you vary the location of your perturbation, and then you can use a Green's function approach to sort of stitch together those different simulations to get something like the map that we saw on the first slide, or something that looks something like this. Okay, so this is showing how useful climate models are for understanding this problem, and I have done this. I've made a contribution to the GFMIP protocol using CAM6, and the results are over here. They're on the right. I'm comparing this to the figure that we saw on the first slide, which was CAM4. Sorry, these have different plotting conventions, but you can see that this tropical West Pacific region lights up consistently, and I didn't put all of the many models that have done this kind of analysis on the slide, but this tends to be robust across models, this idea that the West Pacific is extremely important. Okay. So like I said, this is a very common type of figure that we look at in the feedback community, but I've been a little bit unsatisfied by the explanation, the mechanistic explanation for how this is actually working. And so today's talk is to show you some preliminary results in my quest to better understand the mechanisms. Okay. So this is just a restating what was on the previous slide, which is how is that global mean radiative feedback influenced by local SST anomalies? And here's that map again from Camp 6, in case you wanted another moment to look at it. So what I'm going to do is I'm going to evaluate some of the proposed mechanisms for how this is working in a unified statistical framework. The three mechanisms are here on the slide, and I'll go through each of these three one by one. This is just to orient you as to where we are in the talk. Okay, so the first is lower tropospheric stability, and we can understand why lower tropospheric stability might be important in communicating an SST anomaly to the radiative feedback when we think about the stability of the lower troposphere, and that the strength of the inversion can control how much cloud there is in the lower part of the troposphere, and those low clouds tend to be reflective and have a cooling effect, so you can imagine that an SST anomaly could impact the top of atmosphere radiation via the influence on the lower tropospheric stability. Another mechanism that we're going to be evaluating today is the Walker circulation strength. So I sort of put two figures on top of each other here, but the Walker circulation, just as a reminder, is the zonal overturning circulation over predominantly over the tropical Pacific, with ascent over the warm West Pacific region and subsidence over the cool East Pacific region. And this large-scale circulation is balancing the zonal SST gradient over the tropical Pacific. So you can imagine in a patch experiment where we change the SST, that might have an impact on the Walker circulation strength, and of course that large-scale circulation may impact the feedbacks. Okay, and then another thing is this. This turned out kind of funny. This circus tent picture, which is this idea that free tropospheric moist static energy is communicated kind of laterally through the atmosphere via gravity waves. It's the same mechanism that gives us the weak temperature gradient approximation. And so if you have an SST anomaly in a convectively active region, like the West Pacific over here, there's supposed to be this is supposed to be an up arrow, but the top turned out really small. Don't know why. Then that SST anomaly will be communicated via convection to the free troposphere, and then the gravity waves in the free troposphere will communicate that SST anomaly laterally. And we can see that in this pink line here. This is the saturation moist static energy from an actual patch experiment, and we can see, so we can compare the pink line to the 0 line, and we can see that the warming in the West Pacific does increase the free tropospheric moist static energy, and that not only locally over where the patch is, but everywhere throughout the tropics. Okay, so those are the three mechanisms. How the heck am I going to sort through how they are each influencing the total delta R? And I do this just with a statistical approach, a linear regression. And I do this in each patch experiment across the seasonal cycle. And then I can take those regression coefficients, put them back into our Green's function machinery, and create maps of the contribution of each of these three mechanisms to the total delta R. This is a regularized regression because, as you can imagine, these three mechanisms are not separate from one another. They're correlated with one another, and so we have to deal with that via regularization. But the takeaway here is that this circus tent picture that I described on the previous slide is pretty important and tends to dominate and explain in large part why this tropical West Pacific region, why an SST anomaly in that region is so efficient at altering the radiative response in these models. Okay, so this has been a statistical approach to doing this. And when we do statistical approaches, when we make a linear regression model or other kinds of models, we as scientists have choices that we can make. right? So for example, I used a regularized regression. I could use a lasso regression or a ridge regression. I am calculating the lower tropospheric stability. I could change my region of averaging. I could use a different measure of lower tropospheric stability. There are any number of ways to measure the Walker circulation strength. So what I've done here is I've actually used what's called a specification analysis or a multiverse analysis and just done this regression analysis. The version I'm showing you here is 24 times. Actually, I have a bigger version where I did it like 70 something times, but I didn't want to subject you to that. So I'll show you this 24 version. So I ran this regression model 24 times, making different sets of choices each time to look for robustness in the results that we've seen so far. Let me walk you through this because it's a little bit confusing at first, but I think that this is very broadly applicable and something that we could be doing in our research, not just in the pattern effect world. So what I've plotted here is for each model, so the 24 models are on my x-axis here, and for each model I've plotted the root mean square error with the most skillful model on the left and the least skillful model on the right. The most skillful model is the one that I showed you results from on the previous slide. And we can see that in that most skillful model, the circus tent mechanism in blue is dominant, followed by this stability mechanism in green, followed by the Walker circulation in pink. And then we can see that if we vary our specifications or the version of the model that we're using, whether or not that finding that the circus tent picture dominates is robust. And we can see that indeed it is. And this bottom panel here is a guide to the various specifications. So we can see, for example, in number 1 that I showed you, the orange square means that I used a ridge regression. The orange triangle means that I used a stream function metric to measure the Walker circulation. And the orange circle means that I used lower tropospheric stability as my metric. And so this is just telling us that the finding from the previous slide is robust, at least like within this statistical framework. Okay. So I'll just wrap up here. The pattern effect is important. I think we've heard that a couple of times today, but I was wanting to better understand the mechanisms of the pattern effect, and so I decomposed it statistically into contributions from 3 different mechanisms and found that this circus tent picture was dominant, and then I did this specification analysis to show that that finding was robust. And that's it.
Questions? Rich.
Yeah, nice talk. I'm wondering how kind of dependent is it on the magnitude of these SST anomalies? Was it 1 Kelvin? I can't remember what you...
A 2 Kelvin anomaly.
I'm wondering whether, if you do 1 Kelvin versus 3 Kelvin, you kind of trigger in different processes that, that will give you a different answer maybe.
Yeah, so okay, well, let me back up and say this circus tent mechanism was initially proposed to explain why there's asymmetry between Green's function analyses where there's a positive versus a negative anomaly. And so I'm actually basically taking a mechanism that was used to describe more or less what you're asking about and applying it to this. So I think, basically, I do expect it to be robust. For CAM6 specifically, I've only looked at 2K warming anomalies, but this comes from literature about the different magnitudes.
One thing that I've been thinking about looking at these plots of the feedback parameter, the map, is why the really equatorial E-specific, where it does rain quite a bit and is convective, also shows up as a positive feedback area. I'm curious if your decomposition of mechanisms clarifies that somehow.
Okay, sorry. So you're talking about this E-specific region?
Yeah.
Which was negative on the first. It's not showing up as well here, but on the first slide it was very negative.
Yeah.
Yeah. So I think that's actually a region where the mechanisms that I've thought of and used for this analysis aren't necessarily doing a great job. But I think the basic explanation for that is that that is a subsidence region. Hopefully I get this right, with a lot of low clouds, and so if you warm that region and lose some of your low clouds, which have a cooling effect, then that loss of the cooling clouds has a warming effect.
So that's for the off equatorial, like the south, a little bit south of the ITCZ is where I think that explanation would hold. But right at the ITCZ, like basically what I'm sort of expecting intuitively is blue to go all the way along what would be like the ITCZ, but it doesn't really appear so clearly in these maps. So yeah, I was just curious if you understood why.
Yeah, that's a great question. So I don't have a great answer for that. I think just having looked at this in a couple of different models, that's maybe an area where the results are not as robust. Like this idea that the West Pacific dominates is tends to be very robust, but then kind of what the spatial pattern of that looks like and what's happening in the Atlantic are not as robust across models. So I think that's maybe an open question. But thanks. Yeah.
Okay, thanks, Margaret. So next up is TU Prize Pranchutia. And this talk here is kind of joint between the software engineering group and AMWG.
Right. Seems like it works well enough. Yeah, my name's Teo Price-Pranchutia. I'm a PhD student at CU Boulder, and I've been working at NCAR as a visiting researcher for the last couple of years. I'm going to be talking about UFECT, applications to different models in realistic bug scenarios. And as you heard, talk is a little bit in a slightly funny context here, but I think this is a good audience for maybe the pitch that we're trying to make. So thanks for hanging with me. So this is collaborative work. These is just a sort of a short list of collaborators of the work really specifically presented in this paper, but the ECT method has been getting developed for a really long time with Alison Baker as one of the lead folks on it, along with Dorrit Hammerling, Michael Duda, and Rebecca Morrison, my advisor at CU. So what is the UFECT? Stands for the Ultra-Fast Ensemble Consistency Test. It is an approach designed to identify changes in model outputs exceeding internal model variability. So basically in scenarios where bit-for-bit equivalence is not a feasible standard, which is a lot of scenarios, it turns out. So and the goal, there's a number of different sort of approaches from other groups and in the literature to achieve sort of overall to ask the same question, but sort of a goal of the UFECT as its design is to require minimal computational expense to test new model configurations. And so we'll look at that a little bit. So how does it proceed if you're not familiar with it, which is great that you're here. Thank you so much. So the idea is we want to characterize sort of the spread, the distribution of model variability using a large ensemble of some accepted configuration of a model, so accepted model runs. And so this will be where the bulk of computation occurs. These will be quite a large ensemble, and maybe just to put some sort of exact numbers, since ensembles and also what is a fast model run varies a lot in the community. We're talking thousands of model runs, maybe hundreds of thousands of model runs, but very short, less than a day. So the computation is relatively large. The bulk of the computation occurs here, but it's not so large as to be unwieldy because they're very short. And so this will sort of be the first part of the test. This characterization of the distributions will be saved, and basically we'll be able to reference against it. So then anytime we want to test new configurations, we only need to test, because we've really accurately characterized the distributions, this small set of model runs from our test configuration, and we can use that to basically get a pass or fail, saying does this configuration result in values that lie outside of the distributions of our accepted ensemble. So testing a new configuration sort of looks like this. We perturb our initial conditions the same way we make our large ensemble as well. Usually the temperature field is perturbed by some machine epsilon perturbation. This passes through the model. Then we actually spatially average in the case of CSM and other atmospheric models I'll talk about. Spatially average those outputs. One of the key steps of the ECT approach is this PCA transform. So this is something that I calculated with the large ensemble and is now used again to transform the outputs. The PCA does a couple important things. It allows us to get an orthogonal basis, or the goal of PCA, which allows us to reason sort of statistically about how likely a new run is to have fallen in or out of the distributions, and also allows us to identify relationships between variables, which is key. So it could be possible that two independent variables from an output, like cloud cover and precipitation, they both fall in distribution, but maybe their relationship has flipped or something. It would not be good, right, if they totally, their relationship changed in some new configuration. And so then finally, these transformed outputs are tested against the characterized distributions with some criteria, and you get a pass or fail. There's lots of literature up to this point from Allison and others sort of on this approach, and I'm happy to answer more questions as well, but sort of recent work has been focused, stuff I've been working on has been focused on this approach really came into being sort of specifically around CSM, and thus a lot of sort of the decisions and parameters were associated with CSM specifically. So we've sort of been trying to build a little bit of a framework to set up this approach if you have a different model that you want to use, maybe how do you select the parameters for the test in sort of a coherent way. And so this is some recent work we're publishing soon. And as part of this, we've been looking at other models, and a lot of our work has been with MPAS-A. And over the course of time, this work has generated quite a lot of examples sort of showing, how this test can detect unwanted changes. It's been used especially for large configuration changes like moving to a new cluster, the move to Cheyenne, use the ECT method sort of as verification, as well as the move to derecho, new compilers, things like that. But we sort of a different kind of example that we've looked at with MPAS-A is sort of a more just like an everyday case that I wanted to share with you today. So how can we maybe avoid just the kind of bugs that as model developers maybe get introduced all the time? So I'll present one test scenario. We have lots of other test scenarios, and always looking for more too if you have other examples that you think would be interesting. So this is a fence post error example, and it's based on sort of a realistic error that came up in MPAS-A development, also known as an off by one error. It'll probably look familiar to any of you who've written code. Fun fact, off by one errors are like really old. They've been described by Vitruvius. It's like you mess up the number of columns for your temple, and that's no good. So, so they're common and easy to occur. So it was a nice example. And so this specific code change that we're sort of testing is to enforce a lower bound on eddy viscosities. And at the uppermost layers of the atmosphere, and these get used in this horizontal Smagorinsky type filter. Hopefully that pronunciation is not too bad. I'm not really a climate scientist by training. So in this example, originally this filter was applied across a fixed number of layers, and this lower bounding was applied across this fixed number of layers. But the goal was we want to refactor it to use a variable number of layers. So this is an example of a code change where, done correctly and set to n filter equals 3, this should be like mathematically equivalent. But due to the vagaries of computation and floating point arithmetic and all that, even without compiler optimization, this correct refactoring doesn't result in bit-for-bit equivalent results. And so it can be a little tricky in a lot of these cases to be confident that your change has been applied correctly. You haven't introduced some kind of unwanted bug. So some examples of the algorithms that we tested here. So this is the baseline approach. So we have this like mu parameter, this bounding parameter, and it applies over 3 layers. This is the baseline. This is going to be like our accepted configuration. And now someone wants to refactor this. They go to this generalized version. You don't need to read every single line, but hopefully take my word for it, though if you do see a bug, maybe let me know. That this, if you put in n filter equals 3, that this should be mathematically equivalent to the baseline code. here we have a generalized version, but where someone has introduced this off by 1 error. You can tell because I put it in red. So you can see that the error is here, and this is no good. And so this is sort of our goal. Can we identify the bug? These kind of refactorings are very common in code development generally, especially for these large models, and we expect will only become like more common as different computational architectures become more in use. We heard some about code modernization this morning. We'll probably have to do more and more of this, and so as we do it, we would hopefully like to ensure that we haven't introduced errors. But can we do this when neither of these options can give us bit-for-bit equivalent results? So maybe a classic approach that you might do is, let's say, we'll look at some fields, we'll look at some metrics on those fields. And so here we look at the horizontal and vertical wind speed fields at cell faces in MPass-A. So this, it's got a sort of a different grid than like CSM classically, but so here we look at the root mean squared error between the original code and the correctly generalized code, and we see that they are not bit-for-bit equivalent, so we do see a difference. And we see some magnitude to this difference. It might be hard to say, like, is this the correct magnitude of these errors or not? Maybe if you were really an expert in this particular part of the code, you might say, like, oh, that's a reasonable sort of difference. But now if we look at the differences between the original and the buggy version, we see the magnitudes are roughly about the same. So maybe it doesn't help us get too much information. If we look at sort of a different metric, this maximum point-wise difference, there's maybe slightly more of a difference between those values, but certainly they're still on the same order of magnitude. It might be hard to use these. And this is not to say that an expert in this code or this field could not find evidence that this bug has been introduced. Almost certainly they could, but it might require some expertise and maybe some more work to find the right field, to find the right visualization to show that this has introduced the code. So can this ensemble consistency approach do this in maybe a more automated way that requires a little less expertise? And so this is what happens if we run this approach using the UFECT sort of calibrated to MPass-A, and you basically can report a test failure rate if you run the test multiple times. For the correctly generalized code, basically fails like 1 out of 500 times, so that's a pretty good false positive rate, whereas we fail the buggy version 100% of the time. So a relatively strong signal. That wasn't even meant to be like underselling that or something, but yeah, so this is sort of just the pitch. We have a lot of other examples, and if you're interested in using this, we'd be happy to talk with you. So hopefully you got a little bit of background on like what the UFECT is if you're not familiar with it. Some people in the CSM community have been using it for like almost 10 years, so there are parts of the community that are familiar with it, but I know not everyone. If you're part of a different community, not CSM, we developed a setup framework. It's going to get published soon, but the code is actually already available as part of the PyCECT GitHub repository. And so there's some examples basically of how we went about doing this for MPass-A, so it could hopefully is a recipe that's easier to follow for other model developers in the future. And hopefully I gave you a little pitch of how this might help model developers in the course of their normal work as they go about trying to make, this is a little bit funny in this like context of this group of talks. This is when you're trying to make your changes not affect your models as opposed to make them affect your models. So, but we need to do that too. So hopefully this will help users identify bugs in a little bit more of an automated way, and that's just like easier, requires a little bit less brain power, but still with high accuracy. Thank you. Happy to answer any questions.
Okay. Yeah, thanks for the good talk. I was just curious how, like, for those initial ensembles for creating the ECT, how many kind of model configurations does that cover? Like, I know, for example, right now we're like trying to port the code to GPUs, for example. And so do you need an ensemble for GPUs and an ensemble for CPUs, or can like one ensemble cover those tests?
I guess the idea is if you have in a configuration that you are confident in and that you think mathematically equivalent changes should not change those distributions, then you could use the same accepted ensemble to test against. You could test multiple changes against that same configuration. If you think the GPU version is going to give different results, then that's going to have to be a different accepted ensemble. So I think the goal would be that you'd be able to sort of have one. But so in addition to moving to providing an approach to adapt the ECT for MPAS A, another example in our work recently has basically been the updates to CSM. So as lots of code changes have been made to CSM since the ECT was originally developed, it is almost like effectively a different model. Lots of new physics has been introduced, and some of this recent work is sort of showing just how much, from the perspective of the ECT, it has basically changed to be a whole new model. Like sort of the parameters and certainly accepted ensembles that were used originally are just like no longer valid. So yeah, hopefully I guess you want the GPUs, and that's been a use case I know some people have been using this for, is testing the new GPU code against. So hopefully that accepted ensemble sort of holds for GPUs as well, I would think.
Thanks.
Yeah.
Alrighty, thank you. So last but not least is Sean Santos, who will be joining us remotely. Can you hear us, Sean?
Yeah, can you hear me?
Yes.
Great. All right, so this talk is going to be, in a sense, a follow-up to an issue I raised at AMWG way back in 2021. So I'm going to start off by just giving a brief reminder of what that issue was. So when I was doing my PhD work using E3SM v1, I noticed some odd fog that was occurring in the boundary layer over the Amazon, well, really close to the surface in some of those runs. And when I investigated a little further, it became clear that the near surface wind was oscillating up and down really wildly with a period of twice the model time step. In the surface layer here, the dynamics and the PBL scheme dominate the momentum budget. Really, it's a tug of war between the dynamics and the surface stress, with the PBL scheme doing the diffusion that really causes those to meet in the middle. And just to show this old, or explain this old plot that I have on the right, from when I first found this issue. So on this is just a time series of U10. And so the black line is the default model configuration. The purple is reducing the model time step just for the MACMIC loop. So it was club and MG2 at the time. You can see that doesn't really help much. And the gray here is, if you reduce the entire model time step, you get rid of those oscillations. So there's a bunch of questions about why this happens and what we can do about it. So some initial observations that we made was that these oscillations occur in particular regimes and locations, particularly where the surface is rougher, so mainly over land, particularly mountainous or forested regions. They're more likely when the surface is colder, really because of the boundary layer is convectively stable. So over a lot of the land, it only occurs at night. It's worse when the wind speed is higher, and it tends to be worse when the atmosphere's vertical resolution is finer. So in fact, there was an issue in CAM4 that we think is basically a symptom of the same problem. It was sort of fixed by using averaging and having more diffusion in the boundary layer effectively. But when E3SM reduced their boundary layer resolution, we saw this come back really strongly. And so I'm going to focus on E3SM because that's what I have experience with recently. But I know that this issue has happened in CESM and some other models. And I think most of this is pretty generalizable. But here's one exception. We did find an E3SM specific bug that was affecting this. Unfortunately, fixing the problem makes the problem, or sorry, fixing that bug makes the problem a little bit worse at default settings, mainly because it increases mean wind speeds. In the first year that I was looking at this, I did hack together this implicit atmosphere-land coupling scheme, essentially trying to find a more stable atmosphere-land coupling, and also try changing the process order of club and dynamics. So instead of having essentially after the coupler runs, then T-Fizz AC, then dynamics, and then the PBL scheme is club, moving club before the dynamics, which CAM has actually done now. With E3SM, found that helped, particularly both of these last two changes together, but changing the process order affected wind speeds quite a bit. So this left us with some questions to answer about this problem. One question is, what time step size would we need to use to avoid this issue entirely, or to what should we expect in the future if we have model changes? How might that affect what our maximum stable time step is? It's a big question why process order seems to matter, or what the mechanism is specifically. So the standard explanation is sort of that the land scheme is calculating surface fluxes, and then you let the dynamics run, and then you have club run. That's not so good because the dynamics has changed the winds in between when the fluxes are calculated and when club applies them. But that's a bit hand-wavy, and it doesn't really explain why oscillations in particular is what comes out of this. Also, we had a lot of trouble with moving club. The model became less stable in the sense that it would moving club before the dynamics caused intermittent crashes. It also causes significant enough changes to the boundary layer that we have to retune. And then in the future, we'd like to move to higher order process coupling, or higher order process coupling in the atmosphere, where we don't even have a set process order. Maybe because we're using something like string splitting, or we're using another bit of a more sophisticated method. So we don't want to rely on just having a particular process order in order to fix this. And all these questions just come under the umbrella of why is the problem occurring at all? We'd like a simpler test case to reproduce this, that maybe will give insight into generally future versions of the model, or if there's future numerical method changes, whether they might reintroduce this problem, or even changes in vertical resolution. If we refine that further, is that going to make this pop up again, like it already has in the past? So my main focus in the past year has been working on this simplified boundary layer model. When we look at stability of atmosphere surface coupling methods, standard is to use basically the heat equation, especially for people who are interested in instability from the other side, for instance, like heat diffusion through the snowpack. But there's a couple issues with using that for momentum. One is that wind is much more of a vector quantity. You have the Coriolis effect causing rotation of the winds. Also, it's pretty nonlinear, the way that the surface stress depends on the wind speed. So I came up with this somewhat different differential equation as a simple 1D model to try to understand where these oscillations are coming from and to reproduce them with much simpler physics than is in all of a GCM. So I've written it just to save space in this case, and because it makes the analysis a little bit easier. I've written the wind speed as a complex number where the two directions are their real and imaginary parts. And in this case, you can write down there's a vertical diffusion term effectively, and then there's a dynamics term, which involves relaxation of the wind towards the geostrophic wind and the Coriolis parameter. And so this is used for the simplified model within the atmosphere. And then at the lower boundary, we have this requirement that the flux, the momentum flux is equal to some surface stress divided by the atmospheric density. So this tau can be any nonlinear function of the surface wind, and then you can introduce whatever initial condition you want. So looking at this model, first of all, analytically, we can introduce the effect of explicit flux coupling, basically a finite land atmosphere coupling time step, by holding tau constant over some given time step size. So we say we only recalculate tau every half hour, say, but otherwise we can solve that equation that was given exactly. And then if you linearize tau around the sort of steady state solution to the atmosphere, you can actually do this solution over multiple time steps and do a long-term stability analysis. And the upshot of that is that the parameters of the model can be combined to get a maximum stable time step. With the Coriolis parameter included, this is a kind of complicated formula that involves infinite sum, but if you just look at equatorial regions, you just set f to near zero, then this is a effective upper bound on the time step. So this is useful, and except that this dynamics relaxation timescale, which I called eta here, is a little bit artificial to this simplified version of the model. So there's like a little bit of a looser upper bound that is just in terms of the friction velocity and its derivative with respect to the surface wind and the approximate eddy diffusivity of the in the boundary layer. So that's there's some other analytical results, but that was just kind of an idea of what you can get out of this model. Numerically, we can also reproduce these oscillations. So one thing that, so I'll just explain what's going on the right here. This black line is what you get if you don't have any explicit coupling, if you're just solving those system of equations by enough resolution that it's basically exact. And then as you go to the blue and then green and then orange lines here, those are with increasing explicit coupling time step sizes, and you get these really wild oscillations that look like what we see in E3SM and CESM when you go out to 30 minutes. It demonstrates that this problem, at least qualitatively, can be reproduced with no sequential splitting. So the only numerical approximation of any kind here is just the explicit coupling, and then to get actual numbers here, I have to have some model resolution. But you can also get analytic results where there's really is no approximation. And so that means that the process order, there is no process order here because the dynamics and PBL scheme are solved together. And so that is sort of evidence that you don't actually necessarily need a particular process order to fix this. But more than that, this gives us a test problem to try different numerical methods on. And just to go back to the model a bit to show a little bit more about what this instability looks like. This is basically a hodograph type plot where over here we have the geostrophic wind, and you get something that looks a little bit like an Ekman spiral. If you go down down towards the surface. And the bottommost level that I'm plotting here is the 5 meter wind speed effectively. You kind of spiral around towards 0 wind. But then if you use a finite time step, the wind speed near the surface oscillates quite wildly, which is why those spirals look very different. Or here's just the sort of v direction of that wind speed as a function of altitude. So I'm short on time here. So a couple things I'll note. First of all, you can introduce sequential splitting of this model. And so these are the two different process orders with sequential splitting. And you can see that they both have significant oscillations. The one on the left is the CAM order. The one on the right is the E3SM order. And so the left one looks better, but partly because there's a limiter that prevents the wind from being completely reversed within one time step. And that saves the model from crashing. Otherwise, that would blow up. So it's just sort of showing that nonlinearities and limiters can sort of hide some of these problems, but they'll still be around to some extent. And then last, I finally started running E3SM runs with some of the alternate methods that were developed using this model. So this is just a control run here. And you can think of this as basically a plot of how bad the oscillations are from a very brief run. This is a test run. I have longer climate runs running right now, but don't have results from those yet. So this is just a 10-day test run and looking at how prevalent the oscillations are for the first 10 days of January. You can see Northern Hemisphere, where it's winter, unsurprisingly, the oscillations are worse, and Greenland is just terrible, which in previous versions of the model, I had not noticed such an effect. So there may be something specific to recent versions of E3SM that make that a problem. I'd like to redo this analysis with CSM. And then just to show, there's a couple of different interventions you can do. One is to just reduce the model time step. Another is to use this implicit stress method. There's a few different versions of this, but this is the one that I've got data on already. And so I'm looking at a particular one of these very bad points in Greenland. So the black just shows the reason it looks solid is because it's just oscillating up and down faster than the plot resolution, really. And so really severe oscillations all the time, much higher maximum wind speeds, much higher variability of wind speeds. And then if you either reduce the model time step as in green or use this implicit method to calculate the stress as in red, those issues go away. And I'm over time, I think, so I'm not going to really read through these, but there's a bunch of tests going on this summer. Basically, we've got a bunch of possible interventions and just trying to figure out which ones have the best looking climate to fix this. And also just testing some changes that CAM has already implemented in E3SM to see if they work with the different physics and vertical resolution in that model. So thanks everyone for listening.
Okay, is there a quick question for Sean? Is there any numerical method that will solve this, or is it more time stepping?
Well, I mean, I think of this implicit coupling as basically a numerical method. But yeah, there's two ways that you can solve this essentially. One is to try to have a more reasonable stress by taking into account more than one atmospheric time level, or using approximate derivatives of the atmosphere. The other reverse situation is to try to get the atmosphere to guess what the land is doing and update the stresses based on how it thinks the land would react to changes in the winds, which is, in a basic sense, what CAM is doing right now to try to fix this.
Alrighty, thank you. So this concludes the oral session of the AMWG, but we also had 8 poster submissions to the AMWG, so please make sure you go and check those out, and the poster session starts now. So let's thank all the speakers one more time.